So in this introductory video, I don't just want to cover what the course covers, but how the course is different. So of course, we're going to cover things like arrays and linked lists and trees and graphs. But what makes the course different is these graphics, these animations. So I'm going to turn this back into a linked list and shrink this down to show you what I mean. So I'm going to bring in head and tail here, and I'm going to bring in a node that we're going to add to the end. And I just want to walk through how I will use these animations in the course. If we're going to add that node, the last node in the list needs to point to it. Tail needs to point to it, and that adds it into the list. So the last node and tail need to point to that node. But what if we don't have any nodes in the linked list to begin with? We can't have the last node and tail point to it. We need to have head and tail point to it. And in the videos throughout the course, I will go through this process of going through the steps, and then you can code it. But now you have this visual in your mind of how this is all going to work. Then we're going to get into the code. We're going to call this method push. We'll pass it a value. And the first thing we need to do is create a new node. And we'll go through the details of how it is that this creates a new node in the course. But with the animations, I can do things like this to focus in on certain areas of code. So I can pass this value down here, and visually you can see that these two are connected. And let's say we pass this a value of 4. That creates a new node with a value of 4. So let's look at putting this into an empty tree. We want that to look like this. But in order to do this, we need an if statement to determine if head and tail are in fact pointing to null. So we'll say if this.head with the exclamation point. That means if the head is pointing to null, we're going to set head equal to new node. That does this. And tail equal to new node. And that does this. And then we'll add this in with the rest of our code to see how this fits. So this if statement was for if we had an empty linked list. Then we have to write the code if we actually have items. So we'll say else, and we'll build this out. Then we'll say tail.next equals new node. That is tail.next equals new node. And then we'll say tail equals new node. That moves tail over like that. And that adds that into the list. Let's put this else code back in with the rest of the code like this. So we have created a new node. This is if we have 0 items in the list. This is if we have 1 or more items. Then we just increment the length and return this, which returns the entire linked list. So by doing it this way, you don't have to watch me type out all of this code. And you can read 10 times faster than I can type, so this makes it where we can get through the material a lot faster, and the animations make it where it is easier to understand. But you might be saying, well, that's great, but I actually want to see this code being run. So when we get done looking at the code like this, we will flip over to DevTools and take a look at the code over here. This is the push method that we just created. And I'm going to scroll up to show that this push method is part of the linked list class. So I'll scroll up a little here. So right here, this is where we create the linked list we were just working with, where that last item is 44. And then I'll zoom out here, and I'll come over here to this play button, and then I will click on this, and it will run this code. So let's zoom in down here and open this linked list. So this has a length of 4, tail points to 44. We'll close this. And at the command line here, we can just push on the number 4. And it returns the linked list. I'll open this. And now it has a length of 5 and tail points to 4. So now our linked list is going to look like this. So we were able to go through the code very quickly because of the graphical nature of this, but we're still going over and running the code and looking at all of the technical detail. When learning is made more visual, it makes the material easier to understand. You can learn it faster. The comprehension is deeper. The retention is greater. So I hope you can see the difference that this approach makes. I am looking forward to working with you in this course. Okay, now I'm just going to walk through how to bring up the code editor that I'm using. It's Chrome DevTools. So it's a part of Chrome. So if you're going to use this as your editor, you will just need to download the Chrome browser. In order to open it, we just come up here to the three dots, click on that, come down to More Tools, and DevTools. So I'm on a Mac, but it will be the same steps on Windows or a Chromebook. So I'm just going to click on this, and it'll bring up this side window. And what we want to do is get this in its own window. So I'm going to come up and click on these three dots, not to be confused with the three up here that are part of the browser. This is the Customize and Control DevTools. So I'm going to click on this, and dock side. We are docked to the right. You can also dock this at the bottom or the left, or undock into a separate window. And that's what we're going to do here. I'm going to open this up. Now that we have this in its own screen, I'm going to go ahead and make this full screen. Like this. So we're going to come up to Sources, like that. And this is where we're going to spend all of our time in the course, is on this tab, Sources. So let's open up Show Navigator. And what you can do is you can have snippets. And in order to open this, it might be under this double arrow in this menu for you. And it probably is if it's not already open. So you just click on that and it will bring this tab up here. And this is where all of these snippets is all of the code that I have written for the entire course. And I'm just going to create a new snippet here. And I'm just going to call this temp. Then I'm going to paste in some code I already have copied here. And then I'm going to close the navigator. So all this is a very simple function that says output string. We pass it a string, and then we return the string that we just passed to the function. And we're going to call it here with hello world. And the way we run this is we come down to here, and there's this play button. You can see it says run snippet. So this is Command Enter on a Mac. It will be Control Enter on Windows or a Chromebook. So I'm just going to click on this play button. And down here, we can see that it output hello world. So we can call a function up there in our code. But I'm going to clear this and show that we can also call a function with another string down here in the console. So I'm just going to call it with another string, and it outputs another string. So you can call functions or methods up in the editor, or you can do it down here in the console. One other thing I wanted to point out here is this is in dark mode. So they have a dark mode and a light mode. So you come up here to the gear, settings, click on this, and then you can come over here and change this from dark to light mode. And notice it says requires reload. So I'll close this, and then right up here at the top, we can reload DevTools. And it causes DevTools to look like this. So if you want your DevTools to look the same way that I'm going to have mine throughout the course, and yours came up in light mode like this, just come up here, change it to dark mode. It will require the reload. Close the window, click on this box, and it will put this into dark mode. All right, so that is our quick overview of Chrome DevTools. It is essential that you understand Big O when you go into a technical interview, because this will absolutely come up. Understanding this will also make you a better coder. So what is it? So think of it like this. We have two sets of code. We have code 1 and we have code 2. How do we determine which one is better. Now, both of these are going to accomplish the same thing, but they're written differently. Is code 1 better? Maybe it is easier to read. Or is code 2 better? Well, maybe there are other things about that make code 2 better. Well, Big O is a way to mathematically figure out which of these two is better, which one runs more efficiently. So obviously we can't measure this with a scale, so I'm going to bring in a stopwatch to make the point. Let's say we run code 1, and when we run it, we start a stopwatch, and it runs for 15 seconds. Then we reset the stopwatch, and we run code 2, and code 2 runs a lot longer than 15 seconds. Well, obviously we want our code to run as quickly as possible, be as efficient as possible. So by this measure, code 1 is the better code. This is what is called time complexity. But we don't measure time complexity in time. We measure it in the number of operations. And the reason we do that is if you took the same code and we ran it on a faster computer, obviously it would complete in less time, but the number of operations would be the same. So either way, on the fast computer or the slow computer, the time complexity would be the same. The number of operations would be the same. Also with Big O, we measure what is called space complexity. And space complexity is the amount of memory that something uses. So let's say code 1, while it's very fast and runs in 15 seconds, or comparatively fast, maybe it uses a lot of memory. And then we reset all of this and we look at code 2, and while that runs a really long time, the full minute, maybe it uses less memory. And if this is what's most important to you, maybe code 2 is better now. We are going to look mostly at time complexity, but space complexity will come up in interviews. They'll ask you, okay, you wrote this code in such a way, maybe during a whiteboard session or something like that. And they say, great, you've optimized for time complexity, but what if we care about space complexity more? How would you write it then? You will have to understand both concepts. But what we will focus on mostly in this course will be time complexity. So when you're dealing with this kind of notation, there are 3 Greek letters that you'll consistently see. They are omega, theta, and omicron. Omicron is better known as O, as in Big O. And Big O is the one, of course, that you're going to see most often. So to explain this, I'm just going to bring up an array. Let's say we're going to build a for loop to iterate through this array until we find a particular number. If we're looking for the number 1, this is our best case with the least number of iterations through the array. This would be our worst case. And 4 would be our average case. So this best case is represented with the Greek letter omega. This average case is represented with the Greek letter theta, and our worst case is represented with omicron or O. So Big O is always going to be worst case. And I want to point this out because it is very common for people to say things like, okay, that's your worst case Big O, but what's your best case or average case Big O? Well, technically there is no best case or average case Big O. That would be omega or theta. So when we measure Big O, we are always measuring worst case. So now we're going to look at our first Big O notation. And I start with O of n, not because it's the most efficient or least efficient, but because I think it's the one that's easiest to get your head around. So I'm going to explain this with a function. And I'm going to call this function log items, and we're just going to console log out some items. So we're going to run a for loop, and the for loop is going to run n times. And then we're going to console log out I from the for loop. And that's it. Pretty simple code. So let's go look at this in Chrome DevTools. So there is our function. We're calling it with the number 10. And let's run this. and you can see that we've console logged out 0 through 9. So let's go back over to our other screen. So this is an O of n operation. So to put it another way, we pass the function the number n, and this ran n times. So we passed it a 10, and it ran 10 times. It output 10 things. That's what O of n is. So let's take a look at this on a graph. O of n is always going to be a straight line. It is proportional. The number of operations is going to be proportional to whatever n is. So on this graph, this axis represents n. This axis represents the number of operations. Okay, so that is our first big O notation, and we'll be adding to this graph with the other big O notation so we can compare one against another. But for now, that is O of n. Big O has several ways in which we simplify the notation, and it makes things easier. The first that we're going to look at is called drop constants, or you'll see it referred to as remove constants. You'll see it both ways. So to explain this, I'm going to start by bringing up the code that we had in the last video on O of n. But I'm going to add a second for loop that's identical to the one above, except that we're going to use j instead of I. And both of these for loops are going to run n times. So let's take a look at this in DevTools. There's our code, and we're going to call this with a number 3. Okay, so let's run this. And our output is 0, 1, 2 from the first for loop, and then once again 0, 1, 2 from the second for loop. So let's go back over here. So our code ran n plus n times, or 2n. So it would make sense to say that this is an O of 2n operation. But this is where that simplification comes in. It doesn't matter if it's 2n, 3n, or 100n. If there's a constant, we drop the constant, and we say that this code is O of n. So our first rule for simplifying our big O notation, drop constants. So now we're going to look at our next big O notation, which is O of n squared. So we're going to start this off with the code that we used in the last video, where we had a for loop followed by another for loop. But I'm going to change this, and we're going to remove the console logs, and we're going to nest one for loop inside of the other. Then our console log is going to be for I and j inside of the two for loops. So let's go over to DevTools, and there's our code, and we're going to call this with the number 10. So let's run this, and if we scroll up to the top, we start with 0, 0, and if we scroll to the bottom, we go to 99. So we output 100 items. So let's go back over here. The number of items that were output in this case is n times n, or n squared. And that's where we get our O of n squared. Now let's take our code and add one more thing to it, because I want to point out a thing that we do for simplifying this notation. Let's take our for loops one layer deeper. Then we'll console log out the variable for that for loop. And let's take a look at this in DevTools. Okay, there's our 3 for loops. Once again, we're going to call it with the number 10. And we'll run this. So we end in 999 at the bottom there. And if we scroll all the way to the top, we have 0, 0, 0. So we had 1,000 things that were output in this case. Let's go back over here. So we had n times n times n operations, or 10 times 10 times 10, since we passed it the number 10. So this is n cubed. which would be O of n cubed. But it doesn't matter if it's into the third, into the fourth, into the 10th. We are still going to write this as O of n squared. We're going to simplify this. So let's take a look at this on a graph. So if we had two sets of code that accomplish the same task, and one was O of n squared, and the other is O of n, the O of n code is better because it's going to complete the task in fewer operations. So this is our first opportunity to see how it is that we could compare one code set against another. And O of n squared is generally considered an efficient code. If you can write your code in a way that is going to become O of n, it is going to be much more efficient. So that is O of n squared. Different terms for inputs is a very popular gotcha technical interview question. And to explain it, I'm going to bring up some code that we've seen before, where we have a for loop followed by another for loop. And if you'll recall, each of these ran n times, and it was O of 2n, and we dropped the constant and it became O of n. So the trick interview question is that instead of passing this in, we're going to pass it two variables. And the for loops run, the first one is going to run a times, and the second one is going to run b times. Now here is the kind of knee-jerk reaction if you don't know how to do this, is, well, this one is a for loop, and a single for loop is O of n, and this single for loop is O of n, and we're going to add these together, and that becomes O of 2n, and we're going to drop the constant, and this becomes O of n. But that is not correct, because you can't say that A is equal to n and B is equal to n. You can't have both variables be equal to n. Because what if A is 1 and B is 1,000,000? Those are very different for loops. So what you have to do is say the first for loop is O of A, or whatever the variable might be, and the second one is going to be O of B, and when you add these together, O of A plus B is as far as you can simplify this. Similarly, if these were nested for loops, this would become O of A times B. You can't use n, you actually have to use different terms for inputs. Drop non-dominance is another way that we simplify big O notation. So to explain this, I'll bring up some code here. This is our nested for loop that we saw from before. What I'm going to add to this is an additional for loop that comes after the nested for loop. Let's take a look at this in DevTools. So there's our code, and we're going to run this with the number 10. Okay, I'm going to scroll to the top to begin with. So we have output here is 0, 0, and this goes through to 9, 9. This is our nested for loop. That second for loop that follows it goes from 0 to 9. So let's take a look at this over here. That nested for loop ran O of n squared times. The second one ran O of n times. When we add these together, this becomes O of n squared plus n. So if you think about this in terms of if n was 100, n squared would be 10,000, where the single n that's added to it in this equation is only 100 more. It's not really affecting the number of operations. N squared is the dominant term, and n by itself is the non-dominant term. So we just remove it. So we drop non-dominance. So our next big O notation is O of 1. So let's start out with some code here. We have a function called add items. And all we're going to do is we're going to return n plus n. There's only one operation here, and that's the addition. So it doesn't matter if n is 1 or n is 1,000,000, the number of operations is going to be 1. And that is O of 1. Well, what if we add another addition? Well, now that's 2 operations, right? O of 2. And as you may have guessed, we're going to simplify this and make it O of 1. So O of 1 a lot of times is referred to as constant time. So this situation here where we have 2 additions, it's 2 operations. That is constant, no matter what n is. The number of operations does not change as n changes. So let's take a look at this on the graph. It's just a flat line across the bottom. It is the most efficient big O. Nothing is more efficient than O of 1. Remember, you will also hear this referred to as constant time. So if you hear that phrase, that is O of 1. So the last big O that we're going to look at is O of log n. So I'm going to explain this with a sorted array. And in order to do what I'm about to do here, you have to have sorted data. Let's say you want to find a number in this array. And we're going to look for the number 1. What would be the most efficient way to find that? What we're going to do here is we're going to take the array, we're going to cut it in half, and say, is the number 1 in the first half or the second half? Well, it's not in the second half, so we don't even have to look at any of those numbers. And that may not seem like a big deal when you have an array with 8 items in it. But if you have an array with 1,000,000 items in it, you just made it where you have 500,000 items that you don't have to look at. So then we do this again. We cut this in half. It's not in the second half. We're going to remove that. And then we do it again. And now we have found the number 1. This is a technique called divide and conquer. So let's bring everything back here and count the number of steps that we went through to find that item. It was 1, 2, 3. And remember, we had 8 items in the array, and 2 to the 3rd power equals 8. So I'm going to turn this into a logarithm. And if you're not a math person, don't worry. We're not going to go deep into this. But look at the 3 numbers we have here, the 2, the 3, and the 8. Log sub 2 of 8 equals 3. I'm going to back this up, and we'll look at this again. Log sub 2 of 8 equals 3. We're basically saying 2 to the what power equals 8. 2 to the what power equals 8. Well, that number is 3. To put it another way, if we take the number 8 and we repeatedly cut it in half, we divide it by 2, how many times do we have to divide it by 2 to get down to 1 item? And that is 3 times. And the real power of this is when we get to very large numbers. Let's say we have log sub 2 of this number, and this is over 1 billion. How many times would you have to cut this number in half to get down to 1 item? And that would be 31 times. To put it another way, 2 to the 31st power equals this number here that's over 1 billion. So if you had an array with 1 billion items in it, and you were going to iterate through that array linearly to find something, and say what you were looking for was the last item, you would have to look at 1 billion items to find it. But if you use divide and conquer, you could find any item in that array in 31 steps. And that is the power of O of log n. So now let's look at this on a graph. And see that this is very flat. Not as flat as O of 1, of course, but very flat, very efficient compared to O of n and O of n squared. At this point, I want to show one other thing on the graph. I'm not going to talk about this in a lot of detail, but I just want to show this. And that is O of n times log n. that is used in some sorting algorithms. And this is the most efficient that you can make a sorting algorithm unless you're sorting only numbers. But if you're going to sort multiple types of data, you're going to sort strings, this is as efficient as you can make a sorting algorithm. We will talk about this and how we came up with n times log n when we get to those sorting algorithms, because it'll make more sense then. So that's why I'm not going to talk about this now. I'm going to take this back out. So for the rest of the course, everything that we look at is going to be one of these four. So that is O of log n. So now we're going to talk about the big O of arrays. And it's important to understand this so we can compare arrays to the other data structures that we're going to build. So I'm going to start with an array, but I'm going to present it like this. So we have the indexes there, because this will be important for explaining the big O of arrays. So we're going to start with an array that we've already created that we call myArray. And then we're going to push an item onto the end. So myArray.push is going to push this number 17 onto the end with that index of 4. The important thing here, though, is that we do not have to reindex this or this or this all the way down to the beginning. Likewise, when we remove this item with a pop, and we pop that off, we don't have to reindex anything. And because of that, push and pop are both O of 1 operations. But it's different on the other end of the array. So let's bring up myArray, and we're going to shift that first item off of the array. When we remove this, the problem we have is that this index is incorrect. The first item in the array should be 0. So this has to be reindexed to 0. And the next item has to be reindexed, and the next item. Likewise, if we do an unshift and we bring that 11 back, we have to reindex everything in the array all the way down just to be able to bring this back. Not a big deal when we have a small array like this, but if we had one that had thousands of items, that's a lot of reindexing. So this is O of n, where n is the number of items in the array. Very important with arrays to understand that on this end, adding and removing are both O of 1. On the other end, removing, because of the reindexing, and bringing it back because of the reindexing, are both O of n. Now, let's look at adding something into the middle of this array. So we'll say myArray.splice. And if you haven't seen this before, what we're saying with this is we're going to put something in at the index of 1. This 0 means we're not going to remove any items. And this means we're going to add an item with a string that says hi. So let's open up that index of 1, drop that new item with that string in there at the index of 1. And when we do, this index is incorrect. We have to reindex this and this and this all the way down. Since we have to reindex all of this, this is O of n. Now you might say, hey, we're putting that in the middle. Wouldn't that be O of 1/2 n? Well, there's two problems with that logic. First is that big O always measures worst case, not average case. The other problem is this. Even if this was a 1/2 n operation, 1/2 is a constant. And we drop constants. So either way, this is O of n. So likewise, when we go to remove this item, we're going to have to reindex everything all the way down. So it doesn't matter if you're adding or removing somewhere in the middle of the array, that's going to be O of n. Now let's look at finding an item. Let's say we're going to find the number 7 in this array. To do that, we'd have to start at the beginning and say, is that 7? No. No. And then we finally get to 7 and it's yes. That means that if you search by value, this is O of n. But if you search by index and you say, tell me what's at the index of 3, those indexes allow you to go directly to that place in memory as an O of 1 operation. This is one of the big advantages of arrays, is that we can find something in an array with 1,000,000 items in it and go to item 400,000, say, and it is an O of 1. But those indexes are also a disadvantage for the arrays if you're adding something to the beginning, as we just saw, because you're going to have to re-index everything. So the big thing that you have to look at when you're looking at a data structure is, what are you using this for? If you need to access things by index, arrays are a great data structure. But if you're going to be adding and removing a lot of items from the beginning, maybe not the best data structure for you, and maybe you should look at a different data structure if that is your use case. But either way, you're making your decision based on Big O. So I just want to wrap up our section on Big O by looking at how these time complexities compare to one another. So I'm going to bring up the graph, and let's say n is equal to 100. If n is equal to 100, what are all of these going to be equal to? Well, O of 1 is always going to be equal to 1. O of log n is going to be approximately 7 if n is 100. Obviously, n is going to be equal to 100, and O of n squared is going to be equal to 10,000. So you can already see a big disparity between these numbers. But let's say we increase n to 1,000. O of 1 is still going to be 1. O of log n is going to be approximately 10. So 2 to the 10th power is 1,024, which is close to 1,000. So O of log n of 1,000 is going to be approximately 10. O of n is going to be 1,000, but O of n squared is 1,000,000. So you can see that one is going to grow very, very fast. So there are different words and phrases that you'll hear used with each of these. So O of n squared is going to be a loop within a loop. O of n, you'll hear the word proportional. O of log n, you'll hear the phrase divide and conquer. And with O of 1, you'll hear the phrase constant time. So these are our big four that we're going to look at in this course. So now I'm going to take us over to a website that I think is a great resource for learning Big O. It is bigocheatsheet.com. So at the top of the page, you have this graph. These two we're not going to see in this course. In fact, O of n factorial is really something that can only happen if you're writing bad code on purpose. So unlikely that you're going to see that. But you can see that O of n squared is in the horrible category. Remember, O of n times log n is going to be when we are using certain sorting algorithms. And down here is where we want to stay most of the time. So let's scroll down a little bit here. It has these tables. So these are common data structures. So we have time complexity here, and it's broken into average. Notice these are all beginning with the Greek letter theta, and worst, which begins with the Greek letter omicron or O for big O. And space complexity over here, notice they're all the same, except for one of them, which we're not going to build in this course. But everything is O of n, except for that one. So everything that we're going to build for data structures have identical space complexities. And this is one of the reasons why we're going to spend more time on time complexity than space complexity, because for data structures, it's all going to be the same. But it's different when we scroll down to the sorting algorithms. This one, for the time complexity, we have best, which is omega, average, theta, worst, O. But see, the space complexities are all over the place. So you have something like selection sort that has a terrible time complexity, but a great space complexity, versus merge sort, which has a great time complexity and not nearly as good of a space complexity. So these time complexities down here only work if you're sorting numbers. If you are going to sort strings or different kinds of data other than numbers, the best time complexity you can get for a sorting algorithm is O of n times log n. I will also include a link to this site. This is a great resource, and I encourage you to go check this out. And with that, that wraps up our section on Big O. So now we're going to look at classes. And if you're not familiar with these, a class, the analogy I like to use is it's like a cookie cutter. So I'm going to put this over here. And we're going to say class cookie. So when you create a class, you always capitalize the name of the class, in this case, cookie. Classes always have something that is called a constructor. This is what creates the new cookies, if you will, from the class. So in this case, we're going to pass this a color, and that's what this is referencing. And then we're going to pass it to the particular cookie that we are creating. And we will talk more about this keyword that is being used here, but it's for this cookie that we are creating. And that right there is a valid class. It doesn't do much, but it is a valid class. So now that we have that created, we can create new cookies. So this first part looks like declaring any other variable, but we set it equal to a new cookie. There's a new keyword in here. So cookie 1 is the specific instance of cookie that we are creating. And we do that by using the new keyword that calls the constructor. And we are passing it a color green, and that is going to create a green cookie. So we would say that this cookie is green. This one right here that is called cookie 1. That's where the this keyword applies, because we can have multiple cookies that are created by this. That this keyword is going to refer to a specific one. So to expand on this, let's create another cookie. So we'll say let cookie 2 equal the new cookie that is blue. So cookie 2 is a specific instance of cookie. This one is blue. That is, this cookie is blue. So now we have created a class, which is like a cookie cutter, and then we've created a green cookie and a blue cookie. Let's drop the cookies out of here and expand this class. So far, we have created a constructor, but now we are going to create getColor and setColor. And these are the two broad categories of methods that you create. They are getters and setters. So let's bring our cookies back here, and let's look at all of this code in DevTools. So there is our simple class and the creation of our two cookies. I'm just going to run this and clear this, and then zoom in at the bottom here. So if we say cookie1 dot get color, this is where this keyword comes in. We are getting the color for this cookie. And you can see that this is green. And we can do the same thing for cookie 2, and this one is blue. And I will clear this. And then we're going to do set color for cookie 1. And we're going to change the color of cookie 1 to yellow. And we'll clear this. Now we can do get color again for cookie 1. And now cookie 1 is yellow. So this is roughly how you can use classes. Okay, so let's flip back over. And we have changed cookie 1 to yellow. So how are we going to use this in this course? Let's say we're going to build a linked list class. In fact, all of our data structures are going to use classes, and this is why I want to spend some time on this. So as we discussed, we're going to have a constructor. So we're going to pass this a value to create the first node in the linked list. And the curly braces here, I'm just putting a ... to show that there would be code here to do whatever, in this case, the constructor would need to do. But I'm not going to build this out. Just going to do a quick overview of this. So some of the other methods that we could create for a linked list would be push, unshift, insert an item at an index with a particular value, remove, pop, and shift. And we'll create all of these in the linked list section and a few more. But let's just go over what we could do with this. We could say, let my linked list equal a new linked list. We'll pass it a number 23, and now we have a node with 23. We could say my linked list dot push with the number 7. We could do that. Unshift with the number 3 and do that. Insert at the index of 1 the number 11. Like that. We could remove the item at the index of 1 and remove that 11. We can pop an item. We could shift an item like that. So these are some of the things that we can do by building out the linked list class. And we have all of this ability to do all of these very specific things with these data structures by using classes. Pointers are important to understand because we're going to use them in, I think, all of the data structures that we're going to build in this course. If you already understand pointers, you can go ahead and skip this section. To explain pointers, I'm going to start by explaining something that does not use pointers. So I'm going to have a variable. We're going to let num1 equal 5. And then we're going to have another variable where we let num2 equal num1. So let's take a look at this in DevTools. So here's that code here. And I'm going to run this. And then I'm just going to clear off this undefined here and show that if we do num1, that equals 5. Num2 also equals 5. But if we say that num1 equals 10, now when we look at num1, num1 is equal to 10, but num2 is still equal to 5. That's what happens when we're not using a pointer. Let's go back over here. So when we set num2 to be equal to num1, this isn't permanent. This is just making num2 equal to 5 at the time that we declare the variable. But if we later change num1, it doesn't change num2. That's what happens when we're not using a pointer. Now let's compare this to when we are using a pointer. I'm going to say let object1 equal this value. When you set a variable equal to an object, you are saying object1 points to this object. It is a pointer. And then when we say let object2 be equal to object1, it might look as though what we're doing is we're saying, hey, let's set object2 equal to another object with the same value. But that is not what we're doing here. When you set object2 equal to object1, you are literally saying, make object2 point to the exact same object in memory as object1. So let's look at this in DevTools. And we will run this. And if we say object1, that equals that object with the value of 11, same with object2. But if we were to change object1 dot value and make it equal to 22, now when we look at object1, obviously that's going to have the object with a value of 22, but the same is true for object2. Both of them are now equal to the value of 22. Okay, so let's go back over here. Now we've changed this value to 22, and object1 and object2 are both pointing to that same object. That's why they both come up as 22. That's a big difference in how pointers work versus what we saw before when we just used numbers. So now I'm going to bring up another object here because there's a couple of other points that I want to make. When we say let object 3 equal this object, we're saying let object 3 point to this object. So now we could say something like object 2 equals object 3. Now these pointers can be moved to a different place. So if we do this, object 2 is going to point to this as well. And then I want to make one more point here by just having object 1 point down to that other object as well, like this. Now all three are pointing down here, but we don't have anything that is pointing to this object. If you have an object that nothing is pointing to, you have no way of accessing this because you can only access this through a variable. So this is just taking up space in memory, and it can't be used. So periodically, what JavaScript is going to do is it's going to clean up things like this through a process called garbage collection, and it will remove that. And that wraps up our section on pointers. Welcome to linked lists. This is going to be our first data structure that we build, which is kind of exciting. And in order to introduce linked lists, I'm going to compare this to the data structure that it is most often compared to, and that is arrays. So I'm going to take this array and I'm going to turn this into a linked list. So one of the things that arrays have that linked lists don't are indexes. So I'm going to remove the indexes. Also, arrays are in contiguous places in memory, but linked lists aren't. They can be all over the place. So I'm going to spread these out. And then one of the things I like to do when we move to a new data structure is represent it graphically in a different way. So instead of green squares, I'm going to use purple circles. Linked lists also have a variable called head that points to the first item and one called tail that points to the last item. Then each item in the linked list points to the next, to the next, to the next, and the last one is going to point to null. So you will hear the phrase null terminated list. So this is an example of that. So I had mentioned before that arrays are in contiguous places in memory. Linked lists are not. They can be all over the place in memory, where an array is going to be in a contiguous place in memory. So that's just a quick overview of linked lists and how they compare to arrays. So here we're going to look at linked lists, big O. So we're going to look at the big O of all of the things that we do with a linked list. So I'm going to bring up a linked list, and we're going to bring a node in from the right, that for node there. And if we were going to add that to the end, if we look at the steps that we're going to have to do in order to do this, we could just have that last item point to that node. And now that we have something pointing to it, we can say tail is equal to that pointer, like this, and then it's added into the linked list. And it doesn't matter if the linked list had 4 items, like it did here before we added this, or if it had 100 items, the number of steps would be the same, which means this is constant time to push something onto the end, which means O of 1. Now let's look at removing that item. It looks like all we're going to have to do is just do those steps in reverse. And we're going to take that off and move tail over, and we're done. But the problem with that is this. In order to have this pointer point to that 7 node, we have to set it equal to something that is pointing to the 7 node. And the only pointer that is pointing there is this one. And we can't go backwards in the linked list. So in order to get to that pointer, we have to start at the head and iterate through the entire list to finally get to this pointer and set tail equal to that pointer. And because we had to iterate through the entire list, that is an O of N. So popping something from the end of a linked list is O of N. Now let's look at doing this on the other end. Let's bring that 4 in over here. So we have to have the 4 point to that 11 node. And we do have something already pointing at the 11 node. That is head. So we set the pointer from the 4 node equal to the pointer from head. And that points the 4 at this node. Then we just set head equal to the new node. That's O of 1. How about if we take it off? Well, we need to set head equal to the 11 node, and we do have an item that is pointing at the 11, which is the 4 node. We're going to set head equal to head dot next, and we'll get into that when we get into the actual code, but that moves head over, and then we can just remove the 4. So removing from the beginning is also O of 1. Now let's look at inserting something into the middle of the array. So let's bring our 4 node up down here. And if we're going to insert this at the index of 3, we're going to insert it after this node here. That's at the index of 2, 0, 1, 2. In order to do that, we have to start at the head and iterate through the array to get to this point. Now we want the 4 to point to the same node the 23 is pointing to, right here. So we set those equal. Now the 4 is pointing to the same node as the 23. Then we have 23 point to the new node, and this is inserted. But because we had to start at the head and iterate through the list to be able to get to the point where we were going to insert it, this is O of N. Let's see if we're going to remove that same item. We would say, let's remove the item at the index of 3. We start at the head, go 0, 1, 2, 3 to be able to get there. Let's drop this out down here. We want to have the 23 point to the same node that the 4 is pointing to. So we set the 23 pointer equal to the 4 pointer. We drop this out. That is O of N because once again we had to iterate through. Now let's look at finding an item. We could find something by its value or its index. Let's say we're going to find the number 23. You have to start at the head. Is this 23? No. That one's not 23, but that one is. And because we had to iterate through, obviously that's O of N. But what about by index? This is at the index of 2. If we're going to find something at the index of 2, once again, we have to start at the head and iterate through. So whether we are looking for something by value or looking for it by index, it is O of N. This is a difference between linked lists and arrays, because arrays, we can go to the index as an O of 1. So now I want to bring up a table. Let's get that out of the way and bring the table over. And this just shows all of these operations and how linked lists and arrays compare. All of the gray items are going to be the same. But we have a couple here that are better for arrays. Pop and looking up by index are O of 1 for arrays, but O of N for linked lists. And then we also have a couple that are better for linked lists and not as good for arrays, which is adding and removing items from the beginning, shift and unshift. It just depends what you're going to be using your data structure for. So I will include this table as a PDF, as an attachment, so you can download this if you want to be able to have this as a reference. And that is our overview of linked list, big O. So now we're going to look under the hood of a linked list. What is this thing really made of? So I'm going to start by bringing up our diagram that we've seen, and we're going to bring in a node from the right. And when we add this, when we say the 7 node points to the 4 node, and that tail is going to be set equal to that pointer and point at that 4 node, and we add this into the linked list, what's really going on there? In order to answer that question, let's pop this 4 off. and take a closer look at it. In order to understand this, we have to know what is a node made up of. It is this entire thing. It is both the value and the pointer. It's not just the value, it's the whole thing. So this node is actually an object that looks something like this, that has value and next. So this is what we're adding into the linked list. We represent it graphically like this because this is easier to look at, but this is what's really going on. So when we say the 7 is going to point to that new node, the 7 looks like this. So how do we have the 7 point to this other object? We do it by just having it be equal to this object, that the next value in the 7 node is equal to the other node. That is how the 7 node will point to the 4 node. And the same is true, of course, of the 23 node and the 3 node. Let's just build this out. And the 11 node. And the 11 node, since this is the first node, that is what head points to, like this. And then we have tail pointing over here. A little harder to put that into the diagram of nested objects, but it's going to point to the last item. And we made it point to the last item by saying we're going to set it equal to the next value of the 7 node. And that points it here. So this set of nested objects is what this diagram is made up of. So let's move back over here. And this is what a linked list looks like under the hood. Okay, now we are going to build our constructor for our linked list. So let's start our linked list class like this. And before we get into the code of creating the constructor, I'm just going to do this like this without the code and the curly braces built out, because I want to point something out before we get into building the constructor. The constructor has a couple of things in common with a few of the other methods that we're going to build for the linked list, and they are push, unshift, and insert. So the first thing they have in common is they each get passed a value, but they have something else in common. So let's look at what each of these do quickly. The constructor creates a new node at the time that you're creating the linked list. Push creates a new node and then adds that node to the end. Unshift creates a new node, adds the node to the beginning. Insert creates a new node and inserts it wherever that's supposed to go. So you can see the thing they also have in common is that they all create a new node. So we don't want to rewrite this code 4 different times in each one of these methods. So we're going to create a separate class for creating nodes, and we're just going to call that class node. And then when each of these methods below for the linked list needs to create a node, it's just going to call this class in order to create the node. So just to review here, when we're creating a node that looks like this, which is actually this is what we're creating with the node class. So let's bring back our node class and build out our constructor to build that node. So the first thing the node has is a value. And what I'm going to do here, so we have a little bit more room, is I'm just going to focus in on the constructor portion like this. So we pass the constructor a value here. That's what this is equal to, like this. And then we're assigning that to the node. So let's bring in our node here. And there is the this keyword again. So we are specifically saying that this is the value for this node. So let's convert this to an object so we can see what we're doing here a little bit easier. So it is this object that we are giving it a value that we pass to the constructor of 4. Then we have to say this dot next equals null, because this is not pointing to any nodes yet. So we just say next is equal to null. So let's bring in the rest of the code here, and that is our class for a node. So when we create a node, we would use a line that looks like this. Const new node, that's the name of our variable, equals new, which calls the constructor for the node and creates a node with the value of 4. So now we're able to create one of these for our linked list, and that's step 1. So now let's start building out our constructor for our linked list. Let's bring back our linked list code, and we're going to start this with the constructor. And I'm just going to focus in on this constructor code and take the rest of that off the screen for now so we have more room. So the first thing that the linked list constructor needs to do is create a new node. So we're going to do that here. And the value that we passed to the linked list constructor is passed to the new node constructor, and then we have a new node. Then we're going to have head point to that new node. We do that like this dot head equals new node. So this is specifically the head for this linked list. So head equals the new node that we just created in the line above, right? Like that. And the equals, remember, is a pointer to that node. Then we're going to bring in tail, and we're going to say this dot tail equals this dot head. In other words, have tail point to the same thing that the head is pointing to. You could also write this line of code as this dot tail equals new node, just like we did with head in the line above. But if we do it this way, we're saying that it's going to point to the same thing that head is pointing to, like this. And then with the linked list, we are also going to keep track of the length. So we'll say this dot length equals 1. So let's bring back in the rest of that code for the class. And you would create a new linked list by doing something like this. And when you do this, you say new linked list, we're going to pass it a number 4. What we're doing is creating a linked list with one node with a value of 4 with head and tail pointing to it. So let's bring back in all of the code here and go over to DevTools and look at this code in DevTools. So let's zoom in here. And this is the line of code where we create our linked list. This keyword here, linked list, is going to call the class linked list. The new keyword is specifically calling the constructor in the class linked list. Then if we look at this constructor, here it is creating the new node. So this calls the node class here, and the new keyword is specifically calling the constructor. So let's run this. And it comes up with undefined because none of this code returns anything. So I'm just going to clear that off. And I'm going to type in my linked list. And I press enter. And you can see that we have a linked list with a head that points to a node and a tail that points to a node with a length of 1. But if we open this up, we get a little bit more detail. You can see that node that head points to is an object with a value of 4, and next is null. The same thing with tail, where node is an object with value of 4 and next is null, so they're pointing to the same object, and then the linked list has a length of 1. So it looks like we have a working linked list constructor. So now we're going to do the push method. And to explain this, what I'm going to do is I'm just going to walk through the steps first. So there's our linked list. Step 1 is we need to create a new node. So I'm going to bring one in from the right-hand side there, like that. Then we're going to have the last node in the list point to it. And then we're going to have tail point to it as well, and that adds it into the list. That's all simple enough. We do have an edge case that we have to account for, and that is what if we're inserting this into a linked list that does not have any nodes yet? In this case, instead of having the last item and tail point to it, there is no last item. And we're going to have head and tail point to it. As always, after we walk through these steps, I encourage you to pause this and give this a shot coding it. Now we're going to get into the code itself. So we're going to start out with push. We're going to be passing it a value. And as I just said, our first step is to create a node. And we do that with this line here. And that creates our node. And I'm going to start out with our edge case first. Our situation where we have head and tail pointing to null. We want those to point to the new node like that. So I'm going to change this back to these pointing to null like this and bring up our if statement. So we can see if head is equal to null. Now this, if this is true, that means head is pointing to something. So we need to do the opposite of this. So we're going to use that not operator, that exclamation point there, and that makes it the opposite. This is the equivalent of saying if this dot head is false, or if this dot head is equal to null, because null is false. So that's this situation here. So then we say this dot head equals new node, like that, and this dot tail equals new node, and now they both point to the new node. Now let's take this code and put it in with the rest of our code so far, like this. The next thing we need to do is say, well, what if we're putting this into a linked list where it does have nodes? So we're going to say else, and now let's focus in on the else. So we're going to say else this.tail.next equals new node. So if you haven't seen this before, tail up here at the top is equal to this node. So when you say tail, you are saying this node, but the next, let's turn this into an object and look at what this means. So this is tail.next, which is the next pointer in that last node that tail was pointing to. So you're saying have next point to the new node. And we pointed to the new node by setting it equal to the node like this. Okay, so let's switch back to looking at this graphically like this. That is just going to point that arrow to that new node. Then we say this dot tail equals new node. We'll move that over there, and that inserts this into the list. Now let's take this code and put it back in with the rest of our code. So far we have created a node. We have this if statement to check to see if the linked list is empty. And then we have the else to insert the node if the linked list is not empty. The only things left to do are to increase the length by 1. And then we're going to say return this. And when we say return this, we are returning the entire linked list. And we'll talk more about that here in a second. So let's flip over to DevTools. So just scrolling through this, we have our node class up here at the top. The linked list class has a constructor and now has our push method that we just created. Down here, we're going to say let my linked list equal a new linked list with a value of 7. And then we're going to push an item on with a value of 4. And this is going to return the entire linked list because of this line of code here. When we say return this, what we are saying is return this linked list because the push method is part of that linked list class. Now, it's not just returning any linked list, it is returning the particular instance of linked list that we named my linked list. Okay, let's go over here and run this. And it has returned the linked list. So let's open this up. And we can see that head points to the 7 node. Up here, that is what we created the linked list with. And then we pushed on the value 4, and that is what tail is pointing to, and we have a length of 2. So it looks like we have a working method for push. So I'm going to create two different videos for pop. In this one, we're just going to go through the logic of it, the steps that we would have to go through to create a pop method. In the next video, we'll actually go through how to code that. It's a little bit more complicated method than push, and we'll see why here in a minute. So with pop, we're just going to remove the item from the end, move tail over to the previous item, and return the item that we removed. So we do have a couple of edge cases. The first edge case being that we might have a linked list that does not have any items in it, and obviously we can't pop something from this linked list. But the other edge case is if we have one item, and we'll go over this in some more detail in the coding video. But if you want to try to code this, understanding that these are our three scenarios, we might have a list with some items in it, one with no items, and one with one item. You have to code for all three of those scenarios. You can pause the video here and try to code this. Otherwise, I'm going to go into some more detail about what we have to do the pop method. So I'm going to bring our items back here. And when we move tail over to the previous item, this is a little bit more complicated than moving it the other direction, because you can see in the linked list, all of the arrows are pointing to the right. We're moving tail to the left. But once we've done that, it's pretty simple to return this item. So let's bring this back and look at what we have to do to make the tail move back one. And in order to do this, I'm going to convert this from the graphical way that we're looking at this to looking at this as nested objects. So we are going to have tail point to the previous item, and then we'll say tail.next is equal to null, which removes that for node, and then we can return the for node. So let's bring everything back to the way it was, just like this, and look at what we have to do to make tail move up to the previous item, because we want to have it point here. Well, we need to set it equal to something else that points to this node, and the only thing that points to this node is the next value in the previous node. The only way to get to this node is by the next value in this node, and so on, and so on. And this is why we have to start at the head and then iterate through this until we get to this node. Once we've done this, we can have tail set equal to that, and that moves tail up. But we have to iterate through the entire list to make that happen. And that's why a pop is an O of n operation, where push is O of 1. And once we have moved tail up here, we can say tail.next is equal to null, and then remove the node. So now let's put this back in graphical format like this. So how do we keep track of the node before the end? So the way we're going to do this is we have two variables, and I'm going to call them temp and pre. Temp is going to be the variable that once we iterate through this list is going to be pointing to that last item that we return, and pre is going to point to the item that is next to last. In other words, pre is going to point to the 7 node, and then we're going to set tail equal to pre. So for now, I'm going to remove head and tail. I'm going to move pre underneath here so it's a little easier to look at. And what we're going to do is we're just going to iterate through the list, and we're going to say temp.next, and that's going to be that arrow off of the 11 right here. If temp.next is pointing to another node, in other words, if it's true, then we're going to say pre is equal to temp, and in the first iteration it already is. And then we're going to say temp equals temp.next, which moves this over. And then we're going to do it again. Is this point to a node? Then we're going to have pre move up, temp move over. And again, until we get to the end of the list. Now, this is going to be the last time we move these up, where we have pre move up, temp move over. Now this is going to be equal to null, which equates to false. Temp.next is now false. It stops our loop. And this is where temp and pre end up. So for now, I'm going to remove temp. I'll bring this back in a minute. And then we're going to say that tail is equal to pre. And the only thing we were using pre for was to be able to set tail equal to it. So we're done with that. And then we say tail dot next is null, which removes that last item. And I had mentioned that we're going to bring the temp variable back. It was pointing at this node. And then we return temp. So that walks us through how to do the pop method. And this is for if we have a bunch of items. Obviously, it's going to be very easy to write the code for if we don't have any items. If head is equal to null or length equals 0, however you're going to measure that, we just say return undefined. And then the more complicated one is going to be if you only have one item, how is it that you're going to write the code for if you have one item? Because that is one of our other edge cases. But that is how we're going to solve the pop method. And in the next video, we're going to pick up from here and we're going to code this. So now we're going to code our pop method. So we'll start it out like this. And remember, we had 3 scenarios where we had 0 items, 1 item, or 2 or more items. So I'm going to start with the easiest one, which is an empty linked list. And the way we deal with this is just to test to see if the list is empty. We can do it like this, or this dot head equals null, or this dot length equals 0. We'll return undefined. So we'll drop this out of here. And now let's look at if we have 2 or more items. So we showed in the last video we were going to create 2 different variables, temp and pre. We'll create them like this. Let temp equal this dot head, and let pre equal this dot head as well. And then we're going to loop through this. I'm going to use a while loop here. You could use a for loop here because you're just going through the entire length of the linked list. So you could use the number that you have stored in this dot length. But I like using the while loop here because we're just doing this while temp.next is true. And since this is a null terminated list, we are going to go until the pointer is going to be null. So temp.next, if you look at the diagram, the 11 node there, that's that arrow there that I just highlighted. And then we're going to say pre equals temp. And for the first iteration through the loop, pre is already set equal to temp. So this doesn't change anything. And then we'll say that temp equals temp.next, which is going to move temp over. So let's move this down like this, and we'll walk through this all the way to the end of the list. So we'll say, well, temp.next is true, which means there is a node that that arrow is pointing to. We'll set pre equal to temp. It's already equal to temp. So in this iteration, it's not going to do anything. And then temp equals temp.next, which moves temp over. And let's just walk through this all the way to the end, highlighting the line of code that is being used as things are moving on the diagram. So while temp.next, we're going to move pre up and temp over. And then check to see if there's a node there, and we'll do it again. And then this will be the last time that this is going to come up true. And we're going to move pre and temp. And this time, this is going to be false. And this is where pre and temp are left after we run the while loop. So for now, I'm going to remove temp. I'll bring this back, but that's going to be pointing at that for node. And we want to set tail equal to pre. We do that with this line of code, this dot tail equals pre. That was the only thing we were using pre for, so I'm going to just drop this out of the diagram. We'll say tail dot next is equal to null, and that breaks that for off of the list there. So let's take a look at this code. Remember, we created these 2 variables. And now let's look at this with the rest of the code that we have so far. And next thing is to decrement the length. And remember, we do have one edge case that we haven't addressed, and that is if we have one item in the list. And if we do have one item in the list, head and tail both are going to point to it. And we had said that temp and pre were going to be equal to head. So those are both going to point to that one node. So let's just walk through the rest of the code here, just from the while loop down. Okay, so I'm going to back up here. So those first 3 lines, we've already run those. So these are the ones that are left. And let's run through these and see what happens when you only have one item. And it'll become obvious what we have to do when we have one item in the list. So we're going to run while temp.next. Well, temp.next is null, so the while loop is not going to run at all. So we can remove that. And that's all that we're going to use the temp variable for, so I'm just going to drop that out of the diagram there. So this .tail equals pre, well, they're already pointing at the same item, so that doesn't really change anything. So we can remove that line. Okay, then we have this .tail.next equals null. So tail.next is already equal to null. That's not going to change anything, so we're done with that line of code. And the only thing left is this .length minus minus, which decrements the length. It was 1, and it decrements the length to 0. But notice that head and tail are still pointing to that one node. And obviously, if we've popped that off, head and tail should be pointing to null. So let's go back to our code here. And the thing that we have to change here is to say if this .length equals 0, and remember this is 0 after we've decremented it here, then what we need to do is we need to set head and tail equal to null, which gives us this, which is exactly what we want. The only thing left to do is to return temp, which is the item that we popped off, and we return that. So let's go back and look at our code. And let's flip over to DevTools and look at this code over there. Okay, so here is our pop method. This if statement here at the top is for when we have 0 items in our linked list. The code from here to here works if we have 2 or more items. And then we have this if statement here for our edge case of only having 1 item. So what I've done here is I have a linked list that is just going to have 2 items, and the nodes are just going to be 1 and 2. And I'm going to run this. So let's take a look at this linked list real quick. I'm going to make this a little larger here. Let's open this up. So the head is pointing to the node with a value of 1, and tail is pointing to 2. We have a length of 2. So this is going to make it easy for us to test having 2 or more items, pop that off, then having 1 item, then 0 items. So we can run the pop method 3 different times and test all 3 of our different scenarios. Okay, I'm going to clear this off. So I'm going to say myLinkedList.pop. I press enter. And as we would expect, it's returned the 2 node. Now let's type in myLinkedList. And what we have remaining in the linked list is the 1 node has both head and tail pointing to it and a length of 1. So that works for having 2 or more nodes. So let's clear this off, and we will run pop again. And we press enter, and it returns that 1 node. If we look at my linked list, now we have an empty list. Head and tail both point to null. The length is 0. So let's run pop one more time to see if this works correctly when we have 0 items in here. And it is indeed returning undefined. So all 3 of our scenarios are working, which means we have a working method for pop. Okay, so now we're going to write our method for unshift. And this is what unshift is going to look like. We're going to create a new node. We're going to want to have that new node point to the first node in the linked list. In other words, we're going to set it equal to head. We have head set equal to the new node, and that adds it into the list. So you could have a linked list with some items in it like this, or the linked list could be empty, in which case you're just going to set head and tail equal to the new node. So if you're going to code this, go ahead and pause this here. Otherwise, I'm going to jump into the code. So we're going to start it out like this. It's unshift. We're going to pass it a value. And the first step with unshift is that we need to create that node. So let's do this, and that'll create that new node that we're going to use. And as always, when we're going to add a node to anything, we want to start with this situation where we have whatever data structure is empty. So we're going to say if head is null with that exclamation point, we're going to have this.head equal new node, and now head is pointing to the new node. And then this.tail equals new node. Now they both point to the new node. So let's put this if statement in with the rest of our code and have a look at that. This is what we have so far. So our other option is that we are putting this into a linked list that already has items. So we're going to say else, and let's build out this else statement like this. Else new node.next equals this.head. And that does this, points that at that first item in the linked list. We'll say this.head equals new node. That moves that over and adds that into the list. So that's everything for our else statement. And let's put this in with the rest of our code like this. Only things left to do are to increase the length by 1 and then return the entire linked list. So we'll look at this code in just a second in Chrome DevTools. And when we go over to DevTools, we're going to create this linked list. Then I'm going to do an unshift with the number 4 and add that into the list. So let's flip over to DevTools and have a look at that. Okay, so there is our unshift method. And this is going to create the linked list that I just showed in the diagram. Let's run this. And that's going to create the linked list with a length of 4. Okay, so let's open this up. And we have a linked list with head pointing to 11 and a length of 4. So I'm going to clear this. And then I'm going to run unshift with the number 4 like that. And we press enter. And now our linked list has a head with the value of 4. That's the item that we just unshifted on to the linked list. And the length has been increased to 5. And that is our method for unshift. Now let's do our shift method. Shift, we are going to move head over to the next item. We're going to remove the first item and we're going to return it. So same terminology as we used with an array when we are removing the first item. So we have a couple of other scenarios that we have to code for. The first one being if we only have one item in the linked list, and the other one being if we don't have any items in the linked list. So if you want to code this, go ahead and pause the video here and give it a shot. Okay, so we'll start our code out like this. This is going to be our first scenario that we code for, is if we have an empty linked list. And we'll just do this like this. If head is null, we're going to return undefined. And our next scenario is going to be if we have 2 or more items in the linked list. And we'll code this. So remember, we're not only removing this item, we're going to return it. And if we're going to return it, we have to have a variable set equal to it. And we have head equal to it now. So we'll have this variable be set equal to head. We'll do that like this. Let temp equal this.head. Then we want to move head over to the next item. So we're going to set head equal to head.next, like that. We do that with this line of code. This.head equals this.head.next. Then we need to remove this item. It's not good enough just to return temp as it is, because if you do, you're not going to just get that 11 node, but the 11 node has the 3 node connected to it, and so on and so on. You'll get the entire linked list. So you have to set temp equal to null to actually break that connection. So temp.next equals null will do that for us, and we will be returning temp at the end of this, but for now I'm just going to go ahead and remove it like that. Then we just need to decrement the length by 1. Now we're going to code for when we have one item in the linked list. So what I'm going to do is I'm just going to keep those last 4 lines of code because that's all that's going to be relevant here. That if statement's not going to be relevant. And show what happens when we run this code when we have one item. So let temp equal this dot head. That's going to have temp point to that same node that head is pointing to. Let's remove that line of code. Then we're going to say this dot head equals this dot head dot next. So head dot next is null. So this sets head equal to null. Then we say temp dot next equals null. Well, temp dot next is already null, so that doesn't do anything. And then the only thing left to do is to decrement the length. Well, the length was 1, and this changes it to 0. So we've run all this code, we've gotten the length to 0, and tail is still pointing at that node. So what we need to do is say, if the length is 0, have tail equal null. And that fixes that problem. Let's put this code in with the rest of our code and have a look at this. And then I want to emphasize that this if statement for the length being 0 is after we have decremented the length here. It was 1, we decremented it, and then it's 0. And now the only thing left to do is return temp, which is the item that we shifted off. So we'll look at this code in a moment in Chrome DevTools. And when we do, we're going to create this linked list. And the reason for that is we have 3 different scenarios. So we can test shifting one off with 2 or more, then we can test with 1 item, and then we can test running this with no items, which should return undefined. So let's flip over to DevTools, and we'll start out by creating this linked list here. Okay, so let's zoom in here. Here's our method, and this is where we create our linked list with our 2 items in it. We'll zoom back out and run this. And that has created this linked list here where head is pointing to 2 and tail is pointing to 1. So let's clear this off. And then we'll say myLinkedList.shift like that. And now we've removed that 2 node. So if we type in myLinkedList, now the linked list only has 1 item in there with a value of 1. Let's clear this off and try this out with only 1 item in the linked list. Make sure that works. And now that's returned that 1 node. And let's clear this and try this with our empty linked list to make sure that this is working correctly as well. And that is indeed returning undefined. All right, that is our method for shift. Okay, so now we're going to build our get method. The get method is pretty simple to explain. We're just going to get the node that is at a particular index. And that's it. So if you want to code this, go ahead and pause this and see if you can write this code. This is one of our simpler methods, so this is a great one to try. Otherwise, we'll get into this. So I'm going to bring up a linked list here, and I included the indexes here because they're relevant since we're searching for something by index. So we could get anything from 0, 1, 2, or 3. But what we can't do is we cannot return a node at the index of -1, or we could say anything less than 0. And we can't return anything at the index of 4 or greater. We could say greater than or equal to this dot length. So we could do it like this. If the index is less than 0 or it's greater than or equal to this dot length, then we're going to return undefined. Let's bring back our linked list here. In order to be able to return a node, we're going to have to set a variable equal to that node. We're going to call that temp. We'll just set it equal to head. We have to start at the beginning of the list. Then we can iterate through the list however many items we need to get to the item at the index that we're looking for. So we do that by saying let temp equal this dot head. And then I'm going to remove head and tail here and just leave temp here. And then we have a for loop to iterate through this list. And all the for loop does is move the temp variable forward. So say we're looking for the item at the index of 2, it would run the for loop 1, 2 times, and then return the item that it's pointing to. It would return temp. So that is all of our code for get. The only tricky part of this method is to remember to write this if statement for anything that's out of the acceptable range. But other than that, it's a pretty straightforward method. So when we flip over to Chrome DevTools, we're going to build out a linked list that just looks like this, where the index and the value is going to be the same for every node. So let's flip over to Chrome DevTools. So there's our get method, and this is where we build our linked list 0 through 3. So let's run this. And let's open this up, make sure our linked list looks the way we expect it to. Head is pointing to a node with a value of 0. Tail is pointing to a value of 3, and we have a length of 4. So that is perfect. So we'll say myLinkedList.get, and I'm going to pass it a value of -1. And it returns undefined, just like we would expect. And then I'm also going to try a value here that is greater than our range. So let's try the index of 10, and that also returns undefined. So that's perfect. And then let's have a valid index. So the node at the index of 2 is going to have a value of 2. And that is exactly what we expect. So that is our method for get. Okay, so now let's do our set method. So it's very similar to get, and I'm just going to bring this up like this. But instead of just getting something at an index, we're going to go to that index and change the value of the item at that index. So there's not much more to explain than that. So I'm going to say if you want to code this, this would be a good place to pause this, but I would give you one clue before you do that. You can use other methods inside of a method. So you can use the get method here, or you can do the entire set method without doing that, either way. The way we're going to do it is by using the get method. So I'm going to bring up a linked list like this. And one of the things that we know is if we are going to iterate through the list, get to a particular index and change something, in order to iterate through the list, we are going to need a variable. So let's say we're going to go to the index of 1 here, and we're going to change the value of this item from 3 to 4. It would look something like this. For now, I'm just going to change this back. So for now, I'm just going to say let temp. In the get method, we set temp equal to this dot head. I'm not going to do that here. I'm going to show you why here in a second. So there's a lot of similarities between the set and the get method as far as all the steps that we need to do. So just like the get method, if we have an index of -1, or we could say anything less than 0, we want this to be undefined. Anything that's greater than or equal to this dot length, we want that to be undefined. Otherwise, we want temp to point to the appropriate node. So we can do that by just saying let temp be equal to this dot get and pass it the index that we're looking for in the set method. And that's going to either take temp and make it where it is undefined. Temp is going to be equal to undefined in this case, or it's going to be equal to the node that we're looking for. So what we have to do at this point is determine, is temp undefined or is temp pointing to a node? So we'll do this with an if statement. We'll just say if temp. And this is true if temp is pointing to a node. And then we say temp.value equals the value that we passed to the set method. And in this case, we had this equal to 4, and that changes that 3 to a 4. But there's one other thing we have to do inside this if statement. We need the code to stop running at this point, so we need to have a return statement, and we will return true that we were able to change that value. Otherwise, temp is undefined, which is going to cause that if statement to not run, and we're just going to return false. And that is all of our code for the set method. It's very clean because we are just reusing the code that was in the get method, and we don't have to write all that out again. So we will look at this code in a second in Chrome DevTools. But first, I'm going to bring this up, and this is going to be the linked list that we create when we go over to Chrome DevTools. And what we'll do is we will run the set method with an index of 1 and change the value to 4 at that index. Okay, so let's flip over to Chrome DevTools. There is our set method, and this is going to create that linked list that I just showed the diagram of. I'm just going to run this, and it returns the linked list, and I'm just going to open this up, and I really want to look at that second item since that's the one we're going to change. So that's this item here has a value of 3 for now. I'm going to clear this. I'm going to say my linked list dot set with an index of 1 and a value of 4. And it returns true. So I'm going to clear this. And now let's look at our linked list. And I'm going to open this up and look at our second item. And the value has now been changed to 4. All right, so it looks like we have a working method for set. Okay, so now we're going to do insert. To describe what this does, I'm just going to show this. We're going to insert a new node with a particular value that we pass this at a particular index. Pretty self-explanatory. So if you want to code this, go ahead and pause this. Otherwise, we'll get into this. All right, we're going to start out with this linked list, and we're going to create this node. So there are a few possibilities for different places where we can put this, and we will handle these situations differently. Say we want to put this at the index of 0. So that's going to go right there. So we have seen this before. This is unshift when you add something to the beginning of a linked list. So we can just say if the index is 0, return this dot unshift and pass it the value that we had passed the insert method. So a couple things I want to point out here is when we're doing this, we're using the this keyword. And what we've seen when we call a method before is we would say something like my linked list dot unshift and then pass it a value. But this has to apply to any linked list that we are going to use with the linked list class. We have to use the this keyword. The other thing is we are using return, which makes us stop running code. It's just going to return whatever unshift returns, which is going to be the entire linked list with that new node added. Another possibility is that we put this at the other end, and we've seen this before. So we can say if the index is equal to the length, return this dot push, and we just use the push method. Another possibility is that we try to insert this out here at an index that does not work on this end or on this end. So we can say if the index is less than 0 or if the index is greater than the length, we'll return false. So let's go ahead and look at our 3 if statements here and what we've done. Here is what we would do if we were putting this at the beginning of the linked list. This is for if we put it at the end, and this is if it's out of the possible range. Now let's look at putting this in somewhere in the middle of the list. Let's say we're going to put this in at the index of 2, just like that. How would we make that happen? So let's back this up and look at the steps to make that happen. So one of the things we're going to have to do is have a variable that's going to iterate through the list to where we're going to insert this. And we're going to bring this to the spot that is one spot before where we're going to insert this. So let's look at the code to create these 2 items. That's our new node there. And then temp, we're going to say that temp is this dot get of the index where we're going to insert this minus 1. So it's going to be to the previous spot. So let's look at this code. So now notice on our first 2 lines of code, we are calling other methods. And now we just use the get method. So this is our 3rd time using another method inside of this method. All right, so let's bring this back up. So the first thing that we want to do is we want that new node to point at that 23 node at the index of 2. So we can set that pointer on the new node equal to temp.next, just like that. And we'll do that with this line of code. New node.next equals temp.next. Then we want to have temp.next point to the new node like that. We'll do that with this code here. Temp.next equals new node. And that will insert that node into the linked list. So now let's look at this code with the rest of our code, just like this. The only things left to do are to increase the length by 1. And then what we'll do is we will return true, because we used a return of false in the third line of code up there in that if statement. So we'll look at this code in a moment in Chrome DevTools. But this is going to be the linked list that we create, a 0 and a 2. Then we're going to insert a node with the value of 1 at the index of 1. So it's going to be insert 1, 1. So now let's flip over to DevTools and have a look at this. Okay, so there is our insert method that we just created. And this is our linked list with 0 and 2. So let's zoom out here and run this. And this creates our linked list with values of 0 and 2. So let's clear this off. Then we'll run our insert method. So this is with an index of 1 and a value of 1. We'll run that. It returns true. And we'll clear this and look at my linked list. So now my linked list starts with 0 and then goes to the value of 1. And then you can see here that tail has a value of 2. And that is our method for insert. So now we're going to do our remove method. And it's just going to be removing an item from a particular index. So that's pretty straightforward. If you want to code this, go ahead and pause this here. Otherwise, I'm going to get into how to create this method. So I'm just going to bring up a linked list here. So one of the things that we can do is we can remove the first item, and we've seen this before. This is a shift. So if the index equals 0, we can just return this dot shift. Also, we can remove the item from the other end, and we've created code for this one as well. So if the index is the length minus 1, we can just return this dot pop. Also, we can't return an item at an index of -1, or we could say an index of less than 0. And we can't have an index that is greater than or equal to the length. So we can create an if statement that says, if it's less than 0 or greater than or equal to the length, we're going to return undefined. So here are those 3 if statements that we just created. And we'll remove those. Now let's try removing something at an index that is somewhere in the middle of the linked list. We'll do the index of 2. So we know that if we're going to return that item, we're going to have a variable pointing to it. And we're going to have another variable that points to the previous node, to the one we're removing. I'm going to call this before. Now let's just create these variables. And we can use this with the get method. So we could say before equals this dot get of the index -1, the index that we're removing. So the temp variable, we could use the get method again and just say get the item at the index that we're looking for, but that is an O of N operation, and there's a more efficient way to do this. We just say temp is equal to before, not next. All right, so let's take a look at this code. So we have our if statements and we have our two variables. Let's bring our linked list back up here. And this is the item we're going to remove. I'm just going to move this up here. So we want to have the item at the index of 1, the one that before is pointing to, point to that 7 node over there. So we're going to say before dot next. We're going to set it equal to temp dot next, since that arrow is pointing at that node. We'll do that like this, before dot next equals temp dot next, and that moves that arrow down to there. And that's all we're going to need the before variable for, so I'm going to remove that. And then we'll say temp dot next equals null to break that off of that list like that. We'll do that with that line of code there, temp dot next equals null. Now that it's out of the list, we'll go ahead and decrement the list by 1. So we're done with the list, so I'm going to remove those. And then we can say return temp, which returns that item that we removed from the list. So now let's look at this code with the rest of our code here. And that's all of our code for our remove method. And we'll look at this in a second in DevTools. Also, we're going to create this linked list, since this is the one we've been looking at for this example, and we're going to remove the item at the index of 2. So now let's flip over to Chrome DevTools. Okay, there is our remove method there, and here's our linked list, 11, 3, 23, 7. Okay, let's run this. Let's just open this up. And we have head pointing to 11 and tail pointing to 7. Okay, let's clear this. Okay, and let's run our remove method. And we're going to pass it the index of 2. And that returns the 23 node, just as we expected. So I'm going to clear this. And we're just going to have a look at our linked list, make sure that it all looks the way that it should. And it has a length of 3, and then it's 11, 3, and 7. So it looks like we have a working method for remove. All right, now we're going to do reverse. And this is a very common interview question, to be able to reverse a linked list. And this one is complicated. So it's pretty straightforward what we're going to try to do here. It's just going to be a method called reverse, and it's going to reverse the linked list. So I'm just going to jump into this. So it's going to look something like this. We're going to take head and tail and switch it like that. And then we're going to, one by one, take the arrows and point them the other way. So I want you to notice that there's a gap here. And this is the hard part of reversing the linked list, is making sure that you keep track of where everything is while you're introducing all of these gaps all the way down the linked list and continuing to reverse this until it's completely reversed. All right, so I'm going to move everything back and move this down so we'll have a little bit more room for code and whatnot. In order to switch head and tail, we're going to need a variable that we set equal to head. And then what we can do is just say head is equal to tail. And now it points to the other end. But you need that variable to get tail over to the beginning. So we set tail equal to temp. Okay, so let's walk through what we just did here. We created a temp variable. We set it equal to head. Then we said head is equal to tail. And we said tail is equal to temp. Okay, let's look at this code with the rest of our code here. This is what we have so far. And this is really the easy part, just taking head and tail and switching them. Reversing all the nodes is going to be the hard part of reversing the linked list. All right, so let's bring this up. And we're now going to create a couple more variables. We need to have something after temp. I'm just going to call it next. And it'll point to the next node after temp. We'll just set it equal to temp.next. So it'll point to the next node. And then we're going to have one that we call previous, and we'll start that out by being equal to null. So we're going to have a loop that is going to move these through the linked list as we're reversing everything. So I'm just going to move this back. And we need to create these variables. So next equals this.temp, like we just mentioned. And previous is just going to be set equal to null. So let's put these back in the diagram like this. Okay, now let's look at the code that we have created so far. We have reversed head and tail, and we have created our variables. So now we can create our for loop. So we can say next equals temp.next, and that already does equal that in the first iteration of the for loop. Temp.next equals previous. Okay, so temp.next, I just highlighted it there. We're going to set that equal to previous. So in this case, that's just going to point it to null. Previous equals temp. That's going to move that up. And temp equals next. See, this is why you need that next variable there, is it's going to enable you to cross this opening. So you have to have something on the other side of temp to be able to cross the opening. But look at now, the opening is on the other side of temp. So that's why you need previous. So let's just walk through this. We're going to say next equals temp.next. And we have to do that first because the next thing we're going to do is we're going to flip that arrow over on that node. And next is going to allow us to be able to cross that gap the next time we loop through this. Previous equals temp. And let's just keep running through this. We'll say temp.next equals previous, previous equals temp, temp equals next. And this will be the last time that we run through this. We're going to say next equals temp.next. Well, temp.next is null. Temp.next equals previous. That'll be our last one that we flip over. Previous equals temp, temp equals next. And that is our for loop. So let's put this in with the rest of our code like this. And then we're going to return the entire linked list. So we'll look at this code in a second. This is going to be the linked list we create when we go over to Chrome DevTools, and then we're just going to take it and reverse it. All right, so let's flip over to DevTools. There is our code there. And here's our linked list, just 1, 2, 3. And we'll zoom out and run this. Now let's have a look at this linked list. Head is pointing to 1. If we open this up, the next value is 2. If we open this up, the next value is 3. And next points to null, which means we're at the end of the list. So that's our 1, 2, 3. And let's clear this. And we can run our reverse method. All right, press enter. And let's open up this linked list. Now head is pointing to 3. We open that up. The next item is 2. And the next item is 1. And that is our method for reverse. Welcome to doubly linked lists. So I'm going to just jump right into creating a constructor for this. And I'm going to start out by comparing this to a singly linked list. It is just like this, except we have an arrow that goes the other way. For now, I'm going to convert this back to a singly linked list and just look at one of the nodes like this. Remember, it was just a value and next. And our constructor looked like this. We just had to create value and next. So let's convert this back into a node and now a doubly linked list node. This is just going to have value and next and previous. The only difference being the previous value. So our constructor is going to look like this, and the only difference in the constructor is going to be this line. Now let's look at the linked list class and how it is that we built the constructor. I'm going to focus in on the constructor like this. And we built a new node. And this is going to be the same for a doubly linked list. This line of code doesn't change. It's just that the node class changed. So when we create this node, it's going to have next and previous. And there's our node, except it's going to have another arrow. Then we had head point to the new node with this line of code. And then we had tail set to this dot head. So it's just pointing to the same thing head was pointing to. And we made the length equal to 1. There is nothing that changes in the constructor. The only thing that changes is in the node itself. In that first line of code, when we create the new node, it is calling a different node class. So let's bring back in these lines of code. The only change that we would make here is to name this doubly linked list instead of linked list. So we'll look at this code in a second in Chrome DevTools, and then we will also create a new doubly linked list starting with a node with a value of 7. Okay, so there is our code. And like I mentioned, the only difference is that the node has previous and that we change the name from linked list to doubly linked list. So we'll create our new linked list down here. And I'm going to run this. And it has returned our linked list with a value of 7. The difference here being that each of these nodes has next and previous. Okay, so it looks like we have a working constructor. Okay, so now let's look at our push method. I'm going to compare this to a singly linked list. Remember with this, we just created a node, pointed the last node to the new node, moved tail over to the new node, and that added that into the list. It's going to be almost the same for a doubly linked list. The only difference is going to be that green arrow there. So we're still going to point the last node to the new node. But the difference here is that we need to take new node previous and point it to that last node. We still move tail over, and that adds that into the list. And just like with a singly linked list, you can have an empty list, in which case you're going to set head and tail equal to the new node. So if you want to code this, go ahead and pause it here. Otherwise, we'll get into the code. So we're going to say push, pass it a value, and then create a new node. So far, this is all the same. So then we'll start with an empty linked list. So I'm going to say if this dot head is null, we'll have this dot head equal new node, like this for a singly linked list, and like this for a doubly linked list, but the code here is going to be the same. And this dot tail equals new node, which will do that. So let's add this if statement in with the rest of our code, like this. This is what we have so far. So this if statement is if we have an empty list. Otherwise, else, we have one or more items. So let's build this else statement out. So we'll say this dot tail dot next equals new node. So that's tail dot next equals new node. And that connects that arrow. And we'll say new node dot previous equals this dot tail, which is going to connect that over there. Then this dot tail equals new node, which moves that over and adds that into the list. So let's take this else statement and put it in with the rest of our code like this. The only things left to do are to increase the length by 1 and then return the linked list. So the only line of code that is different between a doubly linked list and a singly linked list is this one line of code right here to connect that arrow from the new node back to what had been the last node in the linked list. So we'll look at this code in a moment in Chrome DevTools. And when we do, we're going to build a linked list with numbers 1 and 2, and then we're going to push a 3 onto the end. Okay, let's flip over to Chrome DevTools. Okay, there is our push method, and this is where we're building a linked list with the numbers 1 and 2. Let's zoom out and run this. So I'm going to expand this. And we have a linked list with head pointing to 1 and tail pointing to 2. So I'm just going to clear this. And we'll run my doubly linked list.push with a value of 3. And press enter. And now the length has been increased to 3 in our linked list. And we open this, and tail now points to 3. And it looks like we have a working method for push. Now let's build out our pop method. I'm going to bring up a singly linked list here. And if you'll recall, with a singly linked list, to pop an item off the end, it was an O of N operation. Because in order to move tail over to here, we had to start at head and iterate through the entire list until we got to this point, and then we could set tail equal to this node. But because all the arrows pointed forward, we had to do that entire process of iterating through the list. But with a doubly linked list, this is different because we do have arrows pointing backwards. So what we can do is this. We know that since we're going to pop that off, we're going to have a temp variable pointing to that last item and return that. So I'm just going to bring that up here. Now, instead of having to iterate through the list to have tail go back one item, we can just say tail is equal to tail.previous and move that right over. Once that's moved over, we can say tail.next, we'll set that equal to null. And then temp.previous, we can set that equal to null, and that pops that off the end of the list. And then we just return temp, like that. But one of the things that is similar between a doubly linked list and a singly linked list is that we have an edge case if there is only one item. We're going to have to write some code for that. And then, of course, if there are no items, you cannot pop an item off the end of the list. If you want to give this a shot, go ahead and pause the video here. Otherwise, I'm going to get into the code. So the first thing we're going to code for is if we have an empty linked list. So we can do that like this. And this is the way we've done it before. But we could also say if tail is null. We could also say that the length equals 0. This is the one I'm going to use here. And we're going to return undefined. So let's bring up our doubly linked list here. We need to create our variable. So we'll say let temp equal this.tail, like that. And in order to move the tail over, we can say this.tail equals this.tail.previous. And that moves that over. Tail.next equals null. Tail.next equals null, and that breaks that off from there. And temp.previous equals null. So temp.previous equals null. Then we just need to decrement the length by 1. Okay, so let's look at this in with the rest of our code. Looks good so far. We need to also write the code for when we have only one item. So if you'll recall, it looked like this in a singly linked list. It would be the same here. And if this looks unfamiliar to you, we went over this in detail in the pop method of the linked list. And remember that this is 0 after we have decremented the length. So this applies to when we had 1, we decremented the length, and the length became 0. Then we just need to return temp. So I'm going to do something different with this code. And the reason is this could be a little confusing when you're reading it, because you have if this.length equals 0 here, and then we have if this length equals 0 here. Now, granted, this one happens after we decrement the length, but it still may not be easy to read. So what I'm going to do is I'm going to take this whole if statement here, and I'm going to move it up above where we decrement the length. Now, I'm going to remove some lines of code here. I'm going to remove 5 lines, and I'm going to bring them all back here in a second. I'm just going to rearrange the code. So I'm going to take these 5 lines out. They're all coming back in a second. So this if statement is for when we have one item in the list. So I'm going to change that 0 to a 1 when I move it up here. So we have if statements for when there are 0 items or 1 item, or we could say else there's 2 or more items. We can bring these lines of code back in for when there are 2 or more items, and then decrement the length and return temp. So all I've done here is rearrange the code to make it easier to read. When we wrote this the first time in the linked list section, I did that in a particular order so I could explain the concepts in the order that I wanted to explain them. But a lot of times, as you are figuring out how to code something, you will get to the end of it like we did here and go, that's not that readable. Maybe this could be done in a different way. So I just wanted to show that here, that we can move this stuff around and still have this work the same way. Now it's much easier to read from top to bottom. We could say if there's 0 items, do this. If there's 1 item, do this. Else 2 or more items, do this. So now I'm going to put the code back to the way it was and just watch how everything moves here. It's the same code. And then I'm going to move it back. The only thing that I've added here is an else. Other than that, it's all the same code. So we'll look at this code in a moment in DevTools. And when we do, we're going to start with a linked list that looks like this. We want to make sure our pop method works with 2 or more items. And then we'll pop an item off, and we'll see if it works with 1 item. Pop that off. And then we'll see if it works with no items. And this is where we would expect this to return undefined. Okay, so let's flip over to DevTools. Okay, so there is our pop method. And this is where we build the linked list with 1 and 2. So let's zoom out here. We'll run this. And just have a look at this linked list. We have value of 1 and 2. I'm going to clear this. And I'm going to run pop. That returns the value of 2. And if we say my doubly linked list, you can see the length is now 1. I'm going to clear this. We'll run pop again. And it returns the node with the value of 1. If we look at my doubly linked list, you can see the length is 0. I'm going to clear this and run pop one more time. And it returns undefined. Okay, so that is our method for pop. Okay, so now we're going to do unshift. So it's going to look like this. We're going to have a new node that we create, and then we'll have the next arrow on that one point to the first node in the list. Then we'll have the first node point back to it, move head over, and that adds it into the list. We can also have an empty list, in which case we just set head and tail equal to the new node. So if you want to code this, pause it here. Otherwise, I'm going to get into the code. So we start it with unshift. We're going to pass it a value. And then we will create a new node with that value, like this. Then we will start with adding this into an empty linked list, where we just set head and tail equal to that node. So with this dot length equals 0, we're going to set head and tail equal to the new node. Else, there is 1 or more items, and we'll expand this else out, and we'll bring up this list. So we'll have the arrow from the new node point to that first node. We'll do that with this line of code. New node dot next equals this dot head. And then we'll have the other arrow reach back over to the new node with this line of code. This dot head dot previous equals new node. Then we'll move the head over with this dot head equals new node. And that adds that into the list. So let's put this code in with the rest of our code so far. Now we just need to increase the length by 1 and then return the entire linked list. So we'll look at this code in a moment in DevTools, and we will create this linked list with 2 and 3. Then we will unshift on a node with the value of 1. So let's flip over to DevTools. So there is our unshift method there. And we're going to start out with a list with the items 2 and 3. Let's zoom out here and run this. I'll just open this up. You can see we have values of 2 and 3 and a length of 2. So I'm going to clear this, and I'm going to unshift on a node with a value of 1. So now let's open this. And now you can see that head points to the value of 1 and our length is 3. So that is unshift. So now we're going to do our shift method. Shift is going to look like this. We're just going to remove that item from the beginning of the list. And just like with a regular linked list, we have an edge case of 1 item, and then we also have to write code for if we have no items. So if you want to code this, pause it here. So now I'm going to start with the code. So as usual, when we're going to remove an item, we're going to start with the case of when we don't have any items in that list. So if this dot length equals 0, we're going to return undefined. So the next situation is for when we have 1 item. And it doesn't matter if we have 1 item or 2 or more items. We are going to need the temp variable. So I'm going to declare that here and just set that equal to head. But when we remove the 1 item, we do have to set head and tail equal to null. And I'll do that like this. If the length is equal to 1, we're going to set head and tail equal to null. So now we've written code for 0 items and 1 item. Otherwise, there's 2 or more items. So else, and we'll build this else statement out. And we'll bring up our list like this. So the first thing we're going to do is move head over 1. And we'll set head equal to head dot next, like this. And that moves head over. And then we want to remove this item. In order to do that, we need to take those 2 arrows and set them to null. So head dot previous equals null. We'll do that. And then temp dot next, we'll set that equal to null. And then that breaks that connection there. And at the end, we will return this temp node. But for now, I'm going to put this code in with the rest of our code like this. And then we're going to decrement the length. And then we will return that item. So we'll look at this code in DevTools in a moment. And we will build this linked list because we want to make sure that this is going to work with 2 items, that shift is going to work with 1 item, and then it's going to work correctly when we don't have any items. So let's flip over to DevTools. Okay, so there is our shift method, and this is the 2 and the 1 for our linked list here. So I'm going to zoom out. I'm going to run this. This linked list has head equal to 2, tail is equal to 1. So I'm going to clear this, and I'm going to run shift. So that returns that 2 node. And then if we look at our linked list, we should just have 1 item in there with a value of 1. And we open this, and head and tail are both equal to 1, and we have a length of 1. And now we know that this works with 2 items. So we'll do this again to make sure this works with 1 item. That returns that 1 node. And then we can look at the linked list itself. And we don't have any items in the linked list. Head and tail is null, and length is 0. So I'm going to clear this. And now we'll run it one more time, and we would expect this to return undefined. And it does indeed return undefined. All right, so that is our method for shift. Okay, so now let's do the get method. And with this one, we're just going to get a node at a particular index. So if you want to code this, pause it here. Otherwise, we'll start building this out. So I'm going to start with a singly linked list, and we'll walk through this, and then we'll look at the differences. So with a singly linked list, you could have something at the index of 0, 1, 2, 3, but you can't have an index over here. We could say an index less than 0. Or over here, we could say an index that is greater than or equal to the length. And this is going to be the case whether you have a singly linked list or a doubly linked list. You have to say if either of these are true, then we're going to return undefined. Let's bring our list back up here. And we're going to set temp equal to head. We'll do that like this. And I'm going to remove head and tail from the diagram here and just keep temp there. And then if we were going to iterate through the list, we're going to do that with a for loop like this and say temp.next. So let's say we're going to find something at the index of 2. We're going to go 1, 2 times through the for loop, and then we're going to return that item. So let's put this in with the rest of our code. This was the entire method for get for a singly linked list, but we're going to make some changes to this for a doubly linked list. So let's bring this up. Let's turn this into a doubly linked list like that. And let's say we're going to get this 3 node here, the one at the index of 1. We would start at head and we would get to this node. Then we would return that node. But what if we wanted to get this node? The quickest way to get there wouldn't be to start at the head. It would be to start at the tail and go this way. And that's going to be the difference when we use a doubly linked list, is we can use this efficiency. So let's bring back our code here and we're going to optimize this. So this for loop, we only want to use this if we're in the first half of the list, because this just moves forward by going temp.next. So we're going to wrap this with an if statement that says if the index is less than the length divided by 2, in other words, it's in the first half of the list, then we will use that for loop. Else, we want to create a different for loop that goes the other way. The first thing we have to do is say temp equals this.tail. And that's going to do this and move temp to the other end of our linked list. Then we're going to have a for loop that is just the opposite of the one above. So we're going to start this with I being equal to the index of the last item in the list. And we're going to say while I is greater than index instead of less than. And then we're going to decrement I. And then we're going to go the other way and use the previous arrows instead of the next arrows. All right, so that is all of our code for get. So we'll look at this in a moment, and we will create this linked list, and we're going to run get on the index of 1, which should return the node with the value of 1, and then we'll run it on the index of 2, which will return the node with the value of 2. That way we can see if our method works if our node is in the first half, and then see if it works when our node is in the second half of the list. So let's flip over to DevTools. There is our get method, and this is where we create our linked list that goes 0 through 3. I'm going to run this. Then I'm going to say my doubly linked list.get with a value of 2. And that works. It returns the 2 node. And then let's try this with the value of 1. And it returns the 1 node. And that is our method for get. Okay, so now let's do our set method. And what we're going to do with this is we're just going to go to a particular index and set the value of the node at that index equal to the value that we passed to the set method. So if you're going to code this, go ahead and pause it here. Otherwise, I'll start coding this out. Okay, so just like we did with our singly linked list, we're going to say let temp equal this dot get, and then pass get the index that we passed to set. And let's say we're going to have that index be 2. That's going to point temp to the index of 2. And we're going to let the get method do all the work for us there. So there's a couple of options here. Temp can either be pointing to a node when we do this, or it could be that we pass it an index, say like the index of 4, that's not a valid index. And in that case, get is going to return undefined. So we have to determine, did the get method return undefined? or is it equal to a node? So we're going to use this if statement here, if temp, which means if it is pointing to a node, we're going to say temp.value equals value, the value that we passed to the set method. And let's say that value was 99. That's going to change the value of this node to 99. And then we'll just return true that we were able to change that value. Otherwise, we're going to return false. Now, this is exactly the same code that we used in a singly linked list. Exactly. But the difference here is the get method that we're calling is written in a different way in doubly linked lists than it is with singly linked lists. When we call this get method, if the item we're looking for is in the second half of the list, it's going to start at the tail and work backwards, which is going to be more efficient. So even though the code is the same here, this is going to run in a more efficient manner than it would if it's a singly linked list. But the actual code that we're writing looks exactly the same. We will look at this code in a moment in DevTools. We will create a doubly linked list that looks like this. Then we will change the value at the index of 2 to 99. Okay, so let's flip over to DevTools and take a look at this code. Okay, so there is our set method there. And this is where we create our linked list with the values of 0, 1, and 2. And I'm just going to run this. So I'm just going to open this. And you can see head is equal to 0, tail is equal to 2 with a length of 3. I'm going to clear this. So I'm going to run set at the index of 2 with a value of 99. We get true. Now let's take a look at our linked list. And tail is now equal to 99. I'm going to run this one more time, except instead of having the index of 2, I'm going to do an index of 10 because that's not a valid index. And it returns false. So that is our method for set. All right, so now let's write our insert method. We're just going to insert a new node of a particular value at a particular index. So if you want to code this, go ahead and pause it. Otherwise, we'll get into this. So a lot of the concepts are going to be the same as with a singly linked list. So I'm going to bring up the new node here. And remember, if we were going to put this in at the index of 0, we were going to use the unshift method like this. The index equals 0, return this dot unshift. And remember, you have to use that return keyword. Or we could add this to the other end of the linked list like this. That's the equivalent of just doing a push. Also need to use return. And it's also possible for there to be an index that is out of the range of possible indexes. So let's look at all 3 of those lines of code there. These are going to be the same with a singly linked list or a doubly linked list. The difference being that the unshift method here is going to be a different unshift method. This will be a different push method. And of course, this line will run the same either way. Let's bring back up our linked list here. Let's say we want to insert this somewhere in the middle. We're going to insert this at the index of 2, like that. In order to do that, we're going to have a couple of variables. We will call these before and after. So let's go ahead and write the code for creating this new node and these 2 variables. So there's our code for the new node. And for the 2 variables, for before, we'll say before equals this dot get of the index where we're inserting it -1. And then for after, instead of using the get method, because remember, get is going to be an O of n because it's going to have to iterate through the list to get to the particular index. With this, we'll set after equal to before.next, and that'll be an O of 1. So let's put everything back like that. And then we're going to move a couple of arrows here. We're going to take that arrow from the 3 node, instead of having it point at the 23, we're going to have it point down here. And we'll do that with this line of code. And then we'll have the arrow from the new node point up to that 23 node with this line of code right here. New node.next equals after. And that adds that into the linked list. And this is going to be very similar when we do a doubly linked list. But let's look at our code so far. We've created those variables and then redirected those 2 arrows. Now we just need to increase the length by 1 and return true that we were able to insert that. So this is for a singly linked list. There's just going to be a couple of changes for a doubly linked list. So let's bring this up and turn this into a doubly linked list. So one of the things that we did before is we pointed this arrow down here with this line of code. We've already written this. And this arrow here pointed up to the 23 node. And we've already written this line of code. The only difference is we have these 2 arrows that I just highlighted in green there, and we need to redirect those arrows. So new node.previous equals before, and after.previous equals new node. And I'm going to leave these previous pointers as green, like this. But first, let's look at all of this code in with the rest of our code. So I'm going to bring a couple of orange arrows in here. These are the ones that we already wrote the code for. And those are represented with the orange arrows in the diagram as well. These 2 are the only 2 new lines of code. Otherwise, this is completely the same as the insert method for a singly linked list. We'll look at this code in DevTools in a second, but we're going to start out by creating this linked list with 1 and 3, and then we're going to insert a node at the index of 1 with the value of 2, just like that. So the new linked list will be 1, 2, 3. So now let's flip over to DevTools. Okay, so there is our insert method. And I'm going to scroll here a little bit. And we're going to create this linked list here with a value of 1 and 3. So let's just zoom out. I'll run this. And I'm just going to open this up. And you can see we have a linked list with head equal to 1, tail is equal to 3, with a length of 2. I'm going to clear this. And then I'm going to run my doubly linked list dot insert, and this is an index of 1 and a value of 2. And it returns true. So I'm just going to type my doubly linked list. And here's our new linked list. Has a length of 3, and head is pointed to 1. That is pointed to 2. And that node, when we open this up, you can see that the one in front of it, next, has a value of 3, and previous has a value of 1. So I'm going to clear this. And the other thing I'm going to do is I'm going to try to insert this at the index of 10, which is not a valid index, just to make sure that it returns false. All right. That is our method for insert. And for our last method for doubly linked lists, we're going to do remove. So for this, we're just going to remove a node at a particular index and return it. So that's a pretty simple concept. If you want to code this, go ahead and pause it. Otherwise, let's get into it. So just like with a regular linked list, we saw that if we remove the first item, we could say if the index is 0, we'll just return this .shift. If we're going to return the last item, we could just say return this .pop. And then, of course, we can't have anything that is not a valid index. So anything that's less than 0 and anything that is greater than or equal to this .length. Like that, we return undefined. So let's look at all of these so far. And if it's not one of these, and say we're going to return the one at the index of 2, we would set a variable equal to that node. And what we saw before is we had a before variable before the item we were actually going to remove. And that was because all of our arrows were pointing forwards. But because we have arrows going the other way, we don't need that variable. And I want to show you something a little bit different here with what we can do with these variables. First, we need to declare the variable like this, and we're going to get that variable to the appropriate node using the get method. Let's look at this with the rest of our code like that. Okay, now we'll bring back our list like that. And since this is the one we're going to remove, I'm just going to push it up here like this. So what we need to do is we need to have the arrow that goes from the 3 to the 23, highlighted in green there, and point that to the 7 node. Then we need the one that's going from the 7 to the 23 that I have highlighted there, and have that point over here. In order to do that, watch what we're going to do. We'll say temp.previous.next is equal to temp.next, like that. And that will point that to that node. Similarly, we can say temp.next.previous is equal to temp.previous, like that. And that will move that arrow down. The only thing we need to do now is to say temp.next and temp.previous are both equal to null. And that will break that off the list like that. So let's put this in with the rest of our code like that. The only things left to do are to decrement the length and return that item that we removed. So we'll look at this code in a second in DevTools. This is the linked list that we'll create with a length of 3, and we will remove the item at the index of 1, which also has the value of 1. So it will return the node with the value of 1, like that. Then we'll be left with a list where head points to 0, tail points to 2, and has a length of 2. So let's flip over to DevTools. So there is our remove method. And I'm going to scroll up a little bit. And this is where we create our list with 0, 1, 2. I'm going to zoom out here and run this. And I'm going to open this. And you can see that head points to 0, tail points to 2, and the length is 3. So I'm going to clear this and run the remove method. Okay, so it returned the node with the value of 1. Now let's look at the linked list. And I'll open this up. And head points to 0, tail points to 2, and it has a length of 2. And that's our method for remove. Welcome to stacks. So in the stacks and queues section that we're doing now, there's going to be a lot of borrowing from the linked list section. We'll be able to reuse a lot of code. So this section is relatively easy if you've already gone through the linked list section. So what is a stack? My favorite analogy for a stack is a can of tennis balls. Okay, so let's remove the balls, add them one at a time. When we add something to a stack, we say that we are pushing an item onto the stack. That's the terminology. And if we remove it, that is called popping an item from a stack. So let's say this is tennis ball number 1, and then we push another tennis ball onto the stack. At this point, you can't get tennis ball 1 out without removing tennis ball 2. You can only remove the top item. Let's say we push another item onto the stack. Now the only tennis ball that can be removed is this one. This is called LIFO, last in, first out. So let's remove that top one, and we would say that we're going to pop that from the stack. Now we can remove the second one, and because we have removed that one, now we can remove the last one. So now let me give you an example that we would use in computing. Let's say you're surfing the web and you go to Facebook, and then you go to YouTube, and then you go to Instagram, and then you check your email. What we've created over there on the right is a stack, and when you hit the back button, you're popping that top item from the stack to go back to Instagram, to YouTube, and to Facebook. There are all kinds of examples of where we use stacks in computing. And one of the ones that we're going to look at in some detail later in this course is going to be a call stack. So a very common way of implementing a stack is to use an array. And remember, with a stack, we just are going to add and remove from the same end. It doesn't matter which end that is as long as it's the same end. So we're not going to use an array in this course because it's already included in JavaScript, and that would just be too easy. So we want to do something where we're going to write some code. But I do want to talk about this a little bit, because if this comes up in an interview and they ask you how would you implement a stack with an array, it does matter which end you use. So when you add something to the end of the array or you remove it, remember this is O of 1. Whereas if you do it on the other end, remember you have to reindex everything to take that off, and then reindex everything again to bring that item back. That's O of N. So if you're going to do a stack with an array, always do it on the end, not the beginning. And then you can just think about the stack like this. Also, an easy way to remember this is with a stack, you pop something from the stack or you push something onto the stack, and that's exactly what those two things are called with an array. And like I said, we're not going to use an array. We're going to use a linked list. Now we're going to alter this a little bit to turn this into a stack. But unlike an array, when you create a stack with a linked list, you're always going to use the left side of the linked list as the top. In other words, the null terminated end is going to be at the bottom. You never want to do it like this, where the null terminated end is at the top. Now let's turn this back into a regular linked list and look at why. When you remove an item from a linked list on the end, it's O of N. To add it back in, this is O of 1. So we have 1 O of N, 1 O of 1. Whereas on the other end, it's O of 1 to remove and O of 1 to add. And like I mentioned before, it doesn't matter which end you use as long as it's the same end. So for a linked list, this is the better end for adding and removing because they're both O of 1. So that's why our stack, if we use a linked list, is always going to look like this. When we created our linked list, we had a method that we created to remove the first item called unshift, or to add something in as the first item called shift. So we can use those for creating methods for pop and push with some alteration. Also with the linked list, we had a head and tail. We'll rename these for the stack as top and bottom. And we actually don't even need bottom, so I'm going to remove that. So our stack is going to look like this. All right, that is our overview for stacks. So now we're going to build our constructor for our stack. So just like with linked lists, our first step is that we need to create a node. And the node looks like this for the stack, which is identical to what the node looked like for a linked list. And that means that our node class and the constructor in that class doesn't need any changes to it. This is identical to the node class that we used in a linked list, because that's essentially what we're using here. It's just a modified linked list. Now we're going to see what else we can take from the linked list class. So I'm going to start this out by saying class linked list, because we can just take that out of the linked list class, but we would want to rename this to stack. Now let's see what we can take from the constructor from the linked list and what we can leave the same and what needs to be changed. So here's our constructor. And the first thing that we had to do in our linked list constructor is the same thing that we need to do here. We need to create a node. So up to this point, the only change that we've made is changing the name of the class from linked list to stack. So just like with the linked list, up to this point, we have created a node. In the linked list, the next thing we had was head and tail equal to the new node, like that. But we don't call them head and tail in a stack, so I'm going to remove these. And these would be called top and bottom. And I'm not going to use bottom, so I'm just going to go ahead and remove this, and we'll just use top. And then I'm going to say the length is equal to 1. And you could say height, but I'm just going to leave it at length. One other change that I will make is that that icon for the 11 that we have on the lower right should point down instead of across. And there we have our code for a constructor for stack. And there was a lot that we were able to reuse from the linked list constructor. Now let's go over to DevTools and run this code. This is where we create our new stack called myStack. And then the stack class, of course, is calling the node class to create that first node. Now let's go over here and run this. And then I'm just going to type in myStack and press enter. And there's our stack. We have a stack where the top points to a node. Length is equal to 1. Let's open this up. And top is pointing to a node with a value of 11 where next is null. So it looks like we have created a working constructor. Now we're going to create our push method for our stack. So it's going to look like this. We have that new node up there with the 11, and we're going to push that on. We're going to move top up to point at that. And remember that this looks an awful lot like an unshift from a linked list. So we can borrow from that. So we had unshift. We'll replace this with push. So not to be confused with the push method for the linked list that happens at the other end of the linked list. We are renaming unshift to push because this is a stack. Just like unshift with a linked list, our first step with push is going to be to create a new node. Once we create that new node, we need to figure out what kind of stack are we pushing this onto. Is it a stack that has any items in it, or is it an empty stack? Because those are going to be two different situations that we're going to have to code for. So then we're going to say if this dot length equals 0, in other words, we have an empty stack. In the linked list, we said this dot head and tail was equal to new node. Here, we're going to say that this dot top equals new node, which does this and would give us our first item in the stack. So the other scenario is that we're pushing this onto a stack that already has items in it. So we're going to say else new node dot next equals this dot top. New node dot next. Okay, so let's look at that. New node dot next equals this dot top. And that adds that in there. Then we say this dot top equals new node, which moves this up here. And now we've added that into the stack. Couple steps left though. We're going to increase the length by 1. And then we're going to return this, with this being the entire stack, because the push method is part of that stack class. So now let's go over to DevTools and look at this code. So there is our push method there. Let me scroll up a little bit. It is part of our stack class that we've created. We have a constructor there. Let me scroll back now. So what we've done down here is where we said let my stack equal new stack with the number 7, and then pushed on the 23, the 3, and the 11, is we've created this stack here. So we started with the 7 at the bottom and pushed on the 23, the 3, and the 11. Let's flip back over here, and we will run this. Then we'll come down to the console down here, and I'm going to type in my stack and press enter. And you can see that we have a stack with a top that is pointing to a node. Length is equal to 4. And we'll open this up, and top is pointing to a node with the value of 11. And next for that node is pointing to another node. So if we open this up, we can see that the next item has a value of 3, which is exactly what we had in our stack over here. The 11 points to the 3. And we go back. And you can, of course, keep expanding this out and look at all the rest of them. And that is our method for push. Okay, so now we're going to build our pop method for our stack. So it's going to look something like this. We're going to pop that 11 node off of the top and then move top down to the next item in the stack, which is 3, and then 3 will become the top of the stack. Okay, so let's start coding this. So the first thing we're going to have to determine is, does this stack have items in it like this, or is it an empty stack like this? Because you can't pop anything off of an empty stack, obviously. So we're just going to say if this.length is equal to 0, then we're going to return undefined. Then we're going to need a variable to point to the item that we're going to return. So we'll say let temp equal this.top. That's going to look like this. We're going to have the temp variable point to the node that we're going to return. Let's go back over here. Then we're going to say this.top equals this.top.next, which will look like this. This.top equals this.top, like that, dot next, and that moves top down to point at the 3 node. We say temp.next equals null. Let's take a look at that. Temp.next equals null. And that breaks that off from the rest of the stack. Then we're going to decrement the length by 1, and we're going to return temp. And when we return temp, we are just returning this node that we popped from the stack. So there's our code. And let's look at this in DevTools. Okay, there's our pop method. And down here, we've created a stack with 7, 23, 3, and 11. So if we go back over here, that has created this stack. And I'm going to run pop from the command line, which should return this node. So let's go back over here. And I'm going to come down to the command line here. And I'm going to type in mystack.pop. And I'm going to press enter. And there's the 11 node. Now the next node that was in the stack was the 3 node. So if we just type in mystack, this will return the remainder of the stack. So I'll press enter. And the top item in that stack should be the number 3. And you can see here that the top node has a value of 3. So looks like we have a working method for pop. Okay, so now let's look at queues. So a queue is just like when you get in a line. And when you get in the line, this is called in queue. And you can in queue somebody behind them. And when you remove somebody from the line, that is dequeue. It is FIFO, first in, first out. And we can in queue a couple more people here, and then we'll dequeue them. Now let's look at a couple of data structures that we could use for a queue. Let's start out with an array. So remember, with arrays, to pop or to push is O of 1. To shift or unshift is O of n. So with a queue, you need to add at one end and remove from the other end. And it doesn't matter which end you use for adding or removing, so long as they are opposite ends for those two purposes. So let's look at an array. We could say we're going to add from this end, that's O of n, and remove from this end, that's O of 1. Or we could do it the other way around, add from this end, O of 1, remove from this end, O of n. So there's no way to get around having one of those be O of n. Let's compare this to a linked list. So with a linked list, when you pop an item from the end, like this, it is O of n. But to push it is O of 1. On the other end, shift is O of 1, and unshift is O of 1. So what you don't want to do with a linked list is dequeue from this end, because that's O of n. What you want to do is enqueue from this end and dequeue from this end, and they're both O of 1. With a linked list, we called these head and tail. For the queue, I'm just going to change the names to first and last. So what we're going to do is we're going to start with a linked list and modify it to build our queues. So now we're going to create our constructor for our queue, except our queue is going to look like this. So the first thing we have to do with our constructor is to be able to create a node. And our node is going to be identical to a linked list node, value and next. So our constructor for nodes in a queue will be identical to what we used in a linked list. And there are going to be other similarities to a linked list. Let's start out with a linked list class like this. We can borrow from this. But instead of calling this linked list, we'll call it queue. So let's start building out the constructor here. The first thing we need is to create a node. And the next thing in the linked list class is we said set head and tail equal to the new node that we just created. But in the queue, instead of calling this head and tail, we're going to call it first and last. And then we just say the length is now 1. So we'll look at this in a moment in DevTools, and when we do, we'll create a node with the value of 4. Okay, so let's flip over to DevTools. Okay, so there is where we create our node. That's identical to when we create a linked list. And in our constructor, right here, instead of having head and tail, we have first and last. So let's zoom out and run this. I'll expand this. And there is our node with a value of 4. And that is our queue constructor. Now let's build out our enqueue method. Enqueue is when we add someone to the line. Except our line is going to look like this. And we're going to add that 7 node into our queue. That's what it's going to look like if we have one or more items in our queue. If we don't have any items in our queue, we're going to set first and last equal to that new node. And as we have discussed, we're going to be able to borrow heavily from the push method from the linked list. So if you want to code this, you could start by looking at the push method to get an idea of what you're going to do here. The best thing to do is try to code this from scratch. So I'm going to go ahead and get into the code here. First thing I'm going to do is I'm going to change this from being push to enqueue. And the first thing we'll do in this method is to create a node like that. And if the length equals 0, in other words, we have an empty queue, we're going to set first and last equal to the new node. So that would be a queue that looks like this, and we'll have first and last point to that node. Then we'll say else, and this is for if we have one or more items. Then we'll have these two lines of code. I'm going to focus in on these two like this. That first one, last.next equals new node. We'll do that. And then last equals new node. We'll point that last pointer over to the new node. And that adds that into the queue. Now let's put this code back in with the rest of our code. We will increase the length by 1. And then we'll return the entire queue. So that's all of our code for this. We'll look at this in a moment in DevTools. And when we do, we're going to create this queue. Then we're going to enqueue a node with the value of 7. Then we'll look at our queue to make sure that last is pointing to the value of 7. Okay, so let's flip over to DevTools. And there is our enqueue method. And there's the queue that we're going to build, 11.3.23. I'm going to run this. And it returns our queue. I'll just open this up, take a quick look. First is pointing to 11, and last is pointing to 23. Then I'll clear this. Then I'll say myQueue.enqueue with the number 7. Now let's open this up, and last is pointing to the value of 7. Okay, so it looks like we have a working method for enqueue. Okay, so now let's write our dequeue method. Dequeue is just going to be removing that first item in the line. This is very similar to shift with a linked list. And remember with shift, we had an edge case for if we had one node in our linked list. Same is going to apply to queues. And then we have to return undefined if there aren't any items in the list at all. So like I mentioned, it's like the shift method, and you can copy a lot out of this. Once again, I'll recommend that you try to write this from scratch. And the first thing that you would do if you did that is you would change the name to dequeue. And as always, when we're going to remove something from a data structure, if it is empty, we can't remove that item, so we'll return undefined. Otherwise, we will need a variable to point at the item that we're going to return. So we'll say temp is equal to this dot first, like this. Then we'll say if the length is 1, we'll have first and last equal to null. That is this situation where you have one item, we remove it, we set first and last equal to null. Then we say else first equals first.next. That just moves first over to the next node. And then temp.next equals null. So that is temp.next equals null. Then we'll decrement the length, and then we'll return temp. So that's this item here, we'll return that. So we'll expect to get the number 11 back. So we'll look at this code in a moment in DevTools, and then we'll build out this same queue that we've been using in this video and remove this item. So we should see the number 11 returned, and then we'll look at our queue, and first should be pointing to the node with the value of 3. So let's flip over to DevTools. And there's our dequeue method. And this creates our queue with the values 11, 3, 23, and 7. So I'm going to zoom out here and run this. And I'm just going to open this. And the first node, that's the one we're going to dequeue, has the value of 11. So I'm going to clear this. Then I'll run our dequeue method. And it returns the node with the value of 11. Now let's look at the queue, and we'll open this. And now first is pointing to the node with the value of 3. So that is DQ. Welcome to trees. I think this is a fun data structure. So what is a tree? Well, we've already seen a tree, and that is a linked list. A linked list is actually a form of a tree. It's just a tree that doesn't fork. So we can use this node here as our starting point for creating a node for a tree. So remember, it looked like this. We had value and next. So let's put this back, and we're going to turn this into a binary tree node. So I'm going to change the color to blue since we're moving on to a new data structure. And a binary tree is going to have 2 arrows. So this is going to look like this: value, left, and right. So it's not all that much different than what we created for a linked list. We have left and right instead of next. So let's turn it back into this and bring in a couple of nodes for that to point at. So from an object perspective, it looks something like this. It's not that much different than what we had with linked lists. We just have a left and a right instead of just having next. Let me put this back. And there's no rule that a tree has to be binary. You could have it point to 3 items or 10 items or however many you want. But for what we're creating here, because we only have left and right, it is by definition a binary tree. Then, of course, each of these 2 nodes that we added can point to more nodes. So let's look at a little terminology here on different kinds of trees. This is a full tree. With a full tree, every item either points to 2 nodes or 0 nodes. So if we add a node here at the bottom, this is no longer a full tree. We remove it, it is a full tree. So then I'm going to remove these 2 nodes, and now this is still full because everything is pointing at 0 or 2 items, but it is also perfect. A perfect tree means every line that has items in it is completely filled all the way across. So this is perfect, and this is also perfect. But if we remove a couple of these items, it's still full, but it's not perfect. Let's bring those back so it's full and perfect. It's also one more thing, and I explained this one last because it's easier to explain with an example here. It is also complete. So if we add an item down here at the bottom, this is still complete. And if we keep adding items across that row, it remains complete. It's basically as compact as you can make it, given the number of nodes that you have. But it's no longer full because you have something pointing to 1 item. That entire line is not filled, so it's not perfect. If we add an item here, it's now full and complete, but it's not perfect. And if we fill this all the way across, it's full and perfect and complete. So a perfect tree will always be full. It will always be complete. Okay, so let's move this over now, remove some of these nodes, and we'll look at a little bit more terminology. This top item here is a parent of these 2, which are children. These 2 children, because they have the same parent, are also called siblings. Every child node has 1 and only 1 parent. You can't have more than 1 parent in a tree. So you will never see something like this and have it be a valid tree because that 4 node can't have 2 parents. Let's bring that back. So these 2 child nodes can also be parents of these nodes. Now these are children of the 3 and the 23 nodes. So with this bottom line of nodes here, they don't have any children, and a node that doesn't have any children is called a leaf. These are leaf nodes. And that is our intro to trees. So now we're going to talk about a specific type of binary tree called a binary search tree. So what we saw in the last video, we created a binary tree, but it was not a binary search tree. So the best way to explain them is to just build one out and show how we build this. So let's say we have a tree that only has one item in it at the top, and then we're going to add an item to the tree. We're going to add this node down here. So with a binary search tree, if this new node at the bottom, the 76 node, if it is greater than the 47, it's going to go on the right. If it's less than, it's going to go on the left. And of course, 76 is greater than, so we're going to put it on the right. Now let's add another node. So when we add the next node, we are also going to compare it against that top node. The 52 is greater than 47, so we are going to go to the right. But because there's an item there to the right, the 76 node, we now have to compare that to the 76 node. And when the node is less than, we go left and we place it there. Let's just add a few more. 21, we always are going to start at the top. It is less than the 47. The spot to the left of the 47 is open, so we're going to place it there. 82, we're going to compare it to the 47, go right. Compare it to the 76, we're going to go right again, and that spot is open, so we place it. 18 is less than 47, we go left. It is also less than 21, we go left again. That spot is open, we place it. And 27, we start at the top with the 47, we go left, compare it to the 21, it's greater than the 21, and to the right of the 21 is open, so we place it there. So one of the things I want to point out here is that all of the items to the right of the 47 are greater than 47. All of the items to the left are less than. And then also, if you look at the 21, everything to the left of the 21 is going to be less than, and everything to the right is going to be greater than, no matter how big this tree gets. And that is the structure of binary search trees. Okay, so now let's look at binary search tree big O. So I'm going to bring up a node here, and we're going to do some math. It's very simple math here. You could say that this is one node, or this is also 2 to the 1 minus 1 node. So 2 to the 1 is 2, minus 1 equals 1. And you'll see why I'm doing this here in a second. Because when we build this out to another level, this is 2 to the 2 nodes minus 1. So 4 minus 1 is 3. We have 3 nodes there. This is 2 to the 3. This is 2 to the 4. Now you can see as this grows and it becomes 2 to the 10, 2 to the 20, the minus 1 is irrelevant. So I'm just going to remove this, and we'll say this is approximately 2 to the 4 nodes, and 2 to the 3, and 2 to the 2, and 2 to the 1. So if we're going to find something in this tree with just one node, it would take one step. If we're going to find something in this tree, let's say we're going to find the number 76, it would take 2 steps. If we're going to find the number 27, it is 1, 2, 3 steps. And let's say the number 49, it's 1, 2, 3, 4 steps, and so on. So that's to find the item. If you're going to remove the item, you'd have to iterate through the tree, get to that item, and remove it. It would also take 4 steps. If you were going to add something below the number 49, you would iterate through 4 steps and add an item. It doesn't matter if you are finding, removing, inserting. This is all going to be 4 steps. So you could call this O of log n. So this is our best possible scenario, and that's not an O, but I'm just going to put this out here and say, roughly speaking, it is O of log n. And remember, O of log n is very efficient. And the term that we used with O of log n was divide and conquer. So I'm going to show you the divide and conquer aspect of a tree. If we're going to find that number 49, and we start at the number 47 and move to the right, because it's more than 47, to the 76, everything that's to the left of the 76, we're not going to have to look at. We're not going to have to iterate through. We can completely ignore it. Like this. We have cut the tree in half. And when we move down one level again, we are doing that again until we finally get to the item that we're looking for. So the vast majority of the items in the tree, we didn't even have to look at, and that's what makes it so efficient. I'm going to bring our tree back here. And like I said, this was our best possible scenario, which would be omega. We're more likely to see something like this. This would be theta. But we could still say that this operates like a log n. But this is not our worst possible scenario. Our worst possible scenario is like this. Let's say we have a node, and the next one is larger than that one. And the next one is larger than that one. And the next one is larger than that one. And it just never forks. So you never get that advantage of divide and conquer when you go to find something. It's just operating in a straight line. And we've seen a data structure that looks like this. It's a linked list. And if you were going to find that 91 node in a linked list, you would have to iterate through the entire list. That is O of n. Well, if you have a binary search tree that looks like this, and you're going to find the 91 node, you have to iterate 1, 2, 3, 4 through the list to get to that node. There are 4 items, and it took you 4 steps. That is O of n. And since big O is a measure of your worst possible scenario, technically the big O of a binary search tree is O of n. Our best possible scenario is O of log n. And since we're probably going to be somewhere in the middle, we treat this as if it is an O of log n data structure. So for lookup, insert, remove, this is effectively O of log n. Now let's compare these 3 to a linked list. First, we'll start with lookup. If you're going to look for the number 91 in this linked list, you would have to iterate through the linked list. That is O of n. And this is going to be closer to a log n with a binary search tree. So the advantage goes to the binary search tree. What about if we're going to remove? Same thing. If we were going to remove the node with the value of 91, we're going to have to iterate through the linked list. Like that. And that's O of n. Binary search tree is going to be log n. But what about if we're going to insert an item? See, there's no advantage with a linked list of keeping the list in order, because you're still going to have to iterate through the list when you go look for something. So you may as well just put it on the end, and this is an O of 1. So this advantage goes to the linked list. So let's just look at all of these like this. Insert is better for a linked list because it's O of 1 to put something on the end. But lookup is going to be better for a binary search tree as well as remove. You're giving up some efficiencies putting the items into the tree to make it faster to look up items later. And the same goes for an array. Because an array, it's O of 1 to add something, but if you're going to look up by value, that is going to be O of n, just like a linked list. Okay, so that is our overview of binary search tree, big O. Okay, so now let's build our constructor for our binary search tree. So we have a node that is going to look like this, which looks like this. So this is going to be the constructor for the node. So instead of having value and next, like we did in the linked list, we have value left and right. So now let's start with our binary search tree class and the constructor. And let's just focus in on the constructor code here like this. And as we have seen before, the first step is to create a new node. And then we're going to pass the node class this value, just like that. So I'm going to show this in a tree like this. And so far we just have the one node. We don't have the rest of them. Because these are objects, they all need to have something pointing to them or they get garbage collected. And everything does have something pointing to it except that top node. This is why in a linked list like this, we had to have head pointing to that first node. Similarly, in the binary search tree, we have to have something pointing to that top node, and we're going to call that root. So we need it to look like this, root pointing to that first item. So this dot root equals new node. And since we don't keep track of the length in a binary search tree, this is all we need to do. So this is a working constructor, but I'm going to completely rewrite this. Let's take a look at what we've done here. We have root, but we've also created the first node at the time that we created the binary search tree. You don't have to do that. You don't have to create this with a node. You could just start out by saying root is null. You just create the framework for a binary search tree, and the first node that you insert into it, you do it with the insert method. And I'm going to bring the code back and change it to make it where we don't add a new node at the time that we create the tree. So line by line, we'll go through and change this. First, we're not going to need to pass this a value because we're not creating a node at the time that we create the tree, so we can remove this. This entire line here is just to create the node. We can remove that. And this line, this dot root equals new node, well, we're not going to create that node, so we can remove that and just say this dot root equals null. And that becomes the entire constructor. So let's bring back the rest of our code here. And now let's look at this code in DevTools. Okay, so there is our node constructor and our binary search tree constructor. And then we'll just create a new tree. And I'll run this. And now when we open this, all we have is root equal to null. So that is our binary search tree constructor. So I'm going to break insert up into two videos. This is a fairly complex method. So in this one, we're just going to walk through the steps that you would need to do to insert an item. And then in the next video, we'll actually write the code. So I'm going to bring a tree up here. And what we're going to do is we're going to insert a node with the value of 27, and that open spot to the right of the 21 there. And I'm going to try to replicate the process of walking through the logic that you would have to do to be able to code this. So normally you would sit down with a piece of paper and you would write out all the steps to kind of get an idea of what you need to do to code this, and then you start coding. And that's what we're going to do here. So the first thing we did here is we created a node. So I'm going to add that on the upper left-hand corner here. I'm just going to say create new node. And so we have more room for these nodes. So I'm just going to move everything over to the right like this. And the next thing we're going to have to do is take that 27 and compare it to this item here. And when we compare it, if it's less than, we're going to go to the left. If it's greater than, we're going to go to the right. So we'll add that to our notes. And I'll just say if it's less than, we're going to go left, else it's greater than, and we're going to go right. Now, once we've made the decision, in this case, to go left because it is less than, there are a couple of possibilities. Either we can insert this because that spot is open, or that spot isn't open because there's already a node there. In which case, we need to compare the new node to this node. So I'll make another note here. We'll say if this is null, we're going to insert the new node there, else we have to move to the next node. Now we're going to compare the new node to this node. We're going to say if it is less than, we go left, else it's greater than, we go right. In this case, it is to the right. Then we're going to say if it's null, insert the new node, which is what we have going on here, and we insert this. So the thing that should jump out at you here is that these two if statements were used at the very top, and then when we move to the next node, that's an indication that these must be inside of a loop. And we don't know how many times we're going to loop through this, so it makes sense for this to be a while loop. So the other thing that you might notice is that we had an arrow pointing to this node here that started up here, and we're going to need to have a variable attached to that pointer. And we'll just call this temp, since that's what we've been using in all of the other data structures. And then as you move through the tree, temp is just going to point to the next item that we're comparing the new node to. So I'll bring this back up to the top. And when we initialize this, we're going to have to set it equal to root. And that's going to have to happen before the while loop. So we'll put that in right there. Say let temp equal this dot root. One of our other possibilities is that 27 node, instead of being plugged into a tree that already has nodes in it, we could have a situation like this where the root is equal to null. In other words, an empty tree. In this situation, we just set root equal to the new node. And this is something that we would do before we would declare a variable or do that while loop. So that even goes above the variable, like this. And we do have one other edge case. So I'm going to bring this down here, and I'm going to replace this 27 node with a 76. And you'll see why here in a second. I'm going to bring back the tree like this. If you have a 76, we're going to start at the 47, and we're going to go right. And now we have a node that is equal to a node that's already in the tree. And you can see that everything that we've done so far is either been greater than or less than. We cannot have a value that is equal to a value that is already in the tree. Now, there is a way to get around this. If you're in an interview and they say, hey, what if we do want to have duplicates in there? How might you do that? So I'm just going to take a little tangent here and talk about that. I'm going to focus in on this node. And remember, the node is like this. So what you can do is add something like count. And the count is 1 when you insert the first one. And if you insert another one, you could say the count for the number of 76 nodes that you have is set to 2. We're not going to do that here. So I'm going to take this back out. And because we don't have something like that, we cannot have a duplicate. So let's put this back in to our tree like that. And you're having to compare the new node to each node that you're looking at to see if it's equal. So this is going to have to go inside the while loop like this. We're going to say if the new node is equal to temp, return undefined. All right, that is all the steps that we're going to have to do to code this out. So in the next video, we're going to pick up right here, and then we're going to code insert. Okay, so now we're going to code our insert method. And like I said, we're going to pick up right where we left off in the last video. So I'm just going to take these notes and move them to the bottom and put the code in at the top. So we're going to start out with insert, and we're going to pass this a value, and then we're going to start working through our list. So first thing is to create a node. We do that like this, and now we can remove this from the list. The next thing, if root is equal to null, then root equals new node. That is this situation where root is null. In other words, we have an empty tree, and we set root equal to the new node, and we do it like this. Now remember, we have to have a return in there, because if this is the case, we don't want to run any more code in here. So now that is done, and we can remove that item from the list. So then we set our variable temp. We don't need to make any changes to this. We can just put this right in like that. And then we go into our while loop. So for our while loop, we're going to say while true. So this is always going to be true and keep running unless it hits a return statement. That's how we'll break out of this while loop. So we'll remove this. Then we can say if the new node equals temp, return undefined. That is this situation where we're trying to insert a node that is the same value as a node that we already have in the tree. So we'll do that like this. And we'd have to say dot value in this case, because we are comparing the values, new node dot value, if it equals temp dot value, at any time as we're iterating through this tree, we're going to return undefined. And we'll remove that. And then we have this part. This is where it gets interesting. If it's less than, we go left, else if it's greater than, we go right. So we have to have an if statement that's going to start with one or the other. I'm going to start with left. If new node dot value is less than temp dot value, and what I'm going to do is this is where we're going to have to build out quite a bit of code here, and I'm going to focus in on this if statement and remove the rest of the code for now. So I'll move this up here so we have more room. And this other if statement here is really nested inside of this if statement. We're going to say if it's less than, we go left, and then we have to look to see if that spot is open or not. So it's really a nested if statement. And so now that we understand that, I'm going to remove this, and then we'll just build out the code. So since we are starting out with the less than, in other words, we're going to go to the left, I want to start with a tree where everything is open to the left. And I'm going to bring in a new node. I'm going to point temp to that 47 node. So now if you look at the if statement, we have new node dot value, and we're comparing this against temp dot value, which is 47, which means that we're going to go left. So there's two options. Either that spot is open like that, and we're done, or it's not open. So we're going to assume to begin with that this is open. And we'll say if temp.left equals null, which means that it's open, we're going to set temp.left equal to the new node like that, and then we'll return this, which returns the entire tree. And we have to have a return statement here because once we insert this, we have to be done running code. Now, if that is not open, and it's like that, we're going to set temp equal to temp.left, which moves temp down to there. And we do the whole process again. So in this case, temp.left does equal null, and we would put that right there. Okay, so now I'm going to move temp back up to the top, and we'll write the code for doing something on the right. And I'm also going to just move that tree over a little bit so we have a little room to work over there. And we're going to say else, and this else would be it's not on the left, so it's on the right. And I'm just going to remove that 82 node from the tree over there, and we can see what it's like to insert something where all of the decisions are going to go to the right. And it's going to be just the reverse of what we did above. So just like we had above, either there's a node there to the right of the 47, or there isn't. So the code is going to be very similar. We're just going to say if temp.right is null, in this case it is null, we're going to make temp.right equal to the new node. And then we'll return this because we've placed that. Otherwise, we have items there, and we need to say temp equals temp.right and move temp down. So in this case, we will run the while loop again and then we'll say temp.right equals null, and then finally place that there. Okay, so that is all of the hard code for this method. Okay, so let's remove our tree like this. So now let's walk through what we're doing when we run through this code. We're going to say, is the new node less than the node that we're comparing it to? If it is less than, we are either going to insert this because the next spot is open, or we're going to have to move to the left, which is going to cause us to run through the entire while loop again. Else, it's greater than, and we're either going to insert this on the right, or we're going to have to move to the next node on the right and go through the entire while loop again. So let's take a look at this code with the rest of the code in the while loop. And remember, there was an if statement that we already put in there. I'm going to bring all this back in here. That top if statement was for the situation where the new node was equal to something we already had in the tree. So now let's take this while loop and look at it with the rest of the code for the method. And that is our entire insert method. So we'll look at this code in a moment in DevTools, and we will build this tree. Then we're going to insert a node with the value of 27 right there. So when we insert this, we'll be able to start at the head at 47, go to the left, go to the 21, go to the right, and that node should be there. Okay, so let's flip over to DevTools. And there is our insert method. And then I'll just scroll up a little bit like this. This will build our tree. And in this spot right here is where the 27 would have gone, but we'll insert that separately here in a moment. I'm just going to run this. And then I'm going to open this binary search tree. So we start at the root with the value of 47 there. Let's open this. And left is 21 and right is 76, just like we had in the diagram. And you can see that when we open up the 21, the left node points to the value of 18, but right is pointing to null. That is that open spot. So I'm going to clear this. And I will say myTree.insert with the number 27, like that. And that returns our entire tree. So let's open this up. The root is 47. You can see to the left is that 21 node. We'll open up this 21 node. And now the 21 points to 18 on the left and 27 on the right. So that is our method for insert. So now let's build out our contains method. So I'm going to bring up a tree here, and I'm going to do the same thing I did with insert, where I write out all the steps and then we code it. So let's say that we're trying to find out if this tree contains the number 27. Well, if we're looking for the number 27, we're going to start at the root, and either we're going to have a tree like this that we iterate through and see if it's there or not, or root is equal to null. So the first thing we'll do is we'll just say if root is equal to null, we're going to return false because that is not in the tree. So that'll be our first step there. If root equals null, return false. Otherwise, we have a tree that we can go looking for the node. If the tree does have items, we're going to need a temp variable and say we're looking for the number 27. We're going to compare the number 27 to each node until we find one that is equal. We'll move this back up to the top, and we can say let temp equal this dot root. So the other possibility is that we're looking for a number that is not in the tree. So let's say we're looking for the number 17. We're going to go to the left, and that's not equal to 17. And we go to the left again, and that's not equal to 17. And we go to the left again, and now temp is equal to null. So binary search trees are null-terminated lists. And as we're moving through this, we already know that we're going to need a while loop, but now we're going to say while temp. So basically, while temp is not equal to null, we're going to keep going. But if we hit null, we know that that number is not in our tree. So inside the while loop, we can say if it's less than, we're going to move temp to the left. If it's greater than, we're going to go to the right, and then there's a third option. It could be equal to, in which case we would return true that that item is in the tree. And if temp ever becomes equal to null, it'll break us out of this while loop and will return false. Okay, so let's take these steps and build out our code. I'm going to move these to the bottom like this, and we'll start building our contains method. We're going to pass it a value, the value that we're looking for. And step 1, if root equals null, return false. That's this situation where root is just pointing to null. It's an empty tree. And we'll say if this.root equals null, return false. We'll take that off of our list. And we'll say let temp equal this.root. We can actually just move that up because that's as the code would be written. Likewise, while temp, we can just move that up because that's how you would write your while statement. We will need the curly braces here, so I'll bring those in. If it's less than, we're going to go left. So we'll write an if statement. If the value is less than temp.value, we're going to say temp equals temp.left. So the value there is the value that you passed the contains method. If it's less than temp.value, the item that temp is pointing to, then we move it to the left. So to put this another way, we are comparing the value that we pass the contains method to the value of the node that temp is pointed to. And if it's less than, we're going to say temp equals temp.left, which moves temp to the left. And we can remove that from our list and say else if it's greater than, go right. So that is to say that the value that we pass the contains method, if it is greater than temp.value, we're going to say temp equals temp.right, and that moves temp to the right. And we can remove that item from our list. Then we say else if it's equal, we're going to return true, and that code looks like that. We can remove that from our list. Otherwise, if temp is ever equal to null, it'll break us out of our while loop, and we will return false. And we can just move that up. Okay, so that is all of our code for that method. Okay, so I want to walk through this code to make sure that it's clear what all this means. Obviously, if we have an empty tree, we're going to return false. And let temp equal this.root, that just is going to start temp at the top. And I want to focus in on the rest of the code here, the while loop on down, and just walk through a couple of examples of how we would loop through this. So I'm going to bring up a tree, and we're going to look for, in this case, the number 27. So temp is starting up there at the top, and we would say while temp, and temp is pointing to a node, so our while loop will run. And this if statement, the value is less than temp.value, so we're going to say temp equals temp.left, which moves that down. Then that's going to cause us to run our while loop again. This time the number we're looking for is greater than. So else if the value is greater than, we're going to say temp equals temp.right, which moves that down to there. That's going to cause us to run the while loop again. In this case, it's equal, and we're going to return true. So let's look at another scenario. Let's move this back up to the top like this and look for the number 17. We'll say while temp, this is less, and we're going to move it to the left like this. That causes us to run our while loop again. It's less than again here, and that's going to move us to the left. And now we're going to run the while loop again. It's less than again, and we're going to go to the left again. But now it's going to make temp equal to null. And when we go to run our while loop, this equates to false. So it breaks us out of this while loop, and then we return false. Okay, so let's bring the rest of our code back in here. We'll look at this in a moment in Chrome DevTools, and then we will build out this tree, and we will look for the number 27, just like we did here. That should return true. And then we will look for the number 17, just like we did here as well, and that should return false. Okay, so let's flip over to DevTools. And this is our contains method here. And then I'll just scroll up a little bit. And this is where we build the binary search tree that was in the diagram that I just showed. Okay, so I'm going to zoom out here. And I'm going to run this. And this is our binary search tree. And you can see 47 is at the root here. I'm not going to go through opening all of these. I'm just going to clear this. So the first one I'm going to bring up here is mytree.contains with the number 27. Press enter, and you can see that that's true. And then I'm going to do it with the number 17, and it returns false. All right, so that is our method for contains. Welcome to hash tables. So there's actually a built-in hash table in JavaScript, and that is objects. But what we're going to do here is we're going to build our own. So imagine that this is an address space, and this is actually just going to be an array that we build, and then we're going to put items into this array, but do so using a hash. And what I'm going to do is I'm going to build an inventory for a hardware store, okay? And the first item we're going to have in our hardware store is going to be nails. We have 1,000 of them. And this is what's called a key value pair. Nails is the key, 1,000 is the value. And we're going to run this through a hash. It is only the key, nails, that gets run through the hash. So all letters have an ASCII numerical value. And it's just going to run those letters through a math equation and create a number. So we're going to put this into the hash generator, and we will get our object back, but it's going to do a calculation on that key, nails, and give us an address. Let's say the address is 2. That is where we'll put that object. So that hash function is going to determine where we put that, but also when we go back to look this up, we'll say, where is nails in memory? We'll run it through the same hash function, and we can go straight to the address in memory where that is being stored. So it's very fast. So let's talk a little bit more about hashes. There are 2 characteristics that you need to know about hashes. First, they are one way. So if you take nails and you run it through the hash and it gives you the value of 2, what you cannot do is take the number 2 and have it produce the string nails. It is one way only. The other thing about hashes is that they are deterministic. What that means is if you run nails through this equation and it produces the number 2, the next time you run nails, it will produce the number 2. It will always produce the same number. So these are the 2 important characteristics of a hash. So let's bring back our hash table. And when we build a method like set, this is going to put something into the hash table. We'll have a key and a value. Let's say the key and the value is nails and 1,000. We're going to run this through the hash, and it's going to give us this array that we're going to put into the array that is our hash table over there that's labeled 0 through 7. But it's also going to give us an address based on a calculation it does on that string nails, and it produces 2. So that array is going to go right here. And let's just add a couple more here. Let's just say we have some screws in our hardware store. There's 800 of them. And this is going to map to the address space of 6, like that. And we'll just do one more here, run it through our hash. And this gives us an address space of 2. So that's going to go right there. But there's already something in that address space. And we don't want to just overwrite the last thing in that address space. What we want to do is to be able to have both of them in here. This is what's called a collision. And there are multiple ways of dealing with this. And in the next video, we will talk in detail about how we deal with collisions. Okay, so let's just do one more. We're going to put bolts in here. It's going to be at an address of 4, and we're going to put that here. Now we're going to do a different method. This one's going to be get. We're going to pass that string bolts into our hash function. It's going to produce the value of 4, and we go directly to this address space. And what we'd want to do here is when we are looking for bolts, we want to know the quantity and just have it return that value. And we'll put that back. But if we say something like get nails, and we run this through the hash function, that's going to produce the address of 2. When we go to here, we're going to have to go through the different arrays that are stored at that address space and find the one that is nails and then return that value. And we'll talk about that in some more detail in the get method. But for now, that is our introduction to hash tables. So now let's look at a couple of ways that we can handle collisions. So I'm just going to bring up our address space here and put some items into it. So a collision is when we have an item that maps to that same spot in memory. And I want to point out that these two arrays that we're putting in here, these key value pairs, are actually being stored at this address space like this within another array. So there's the array that's the address space. Then there's the array that holds the key value pairs at that particular address. But I'm just going to show them like this. So this process of putting all of the key value pairs that map to a particular address in the same address space is what's called separate chaining. And separate chaining is what we're going to use in this course. But let's look at another approach. Let's take that back out. And another approach would be to say, hey, if there's already an item at this address space, let's go to the next one and see if it's open. And if it is, put it there. Then if you have another item that maps to that address space, we go to the next spot to see if it's open. And if it's not, we go to the next. And if it's not, we go to the next. And we put it in here. This is what's called linear probing. And it is a type of open addressing. And there are multiple ways of doing open addressing. And there are all kinds of ways of dealing with collisions in a hash table. The two most common are going to be linear probing and separate chaining. So let's remove this and put everything back to a separate chaining format like this. This is what we're going to build in our hash table in this course. So I'm going to show one other way of doing separate chaining. I'm going to remove these. Another way is to have a linked list at every one of these addresses. And then we just add to the linked list when we have multiple items that map to that address. So I'm going to change this back to the way we're going to do this in this course, which is going to be separate chaining with arrays. And that is a few ways of dealing with collisions. Okay, so now we're going to build our constructor for our hash table. And in this video, in addition to the constructor, we're also going to build out our hash function. So I'm just going to bring up an address space like this, and I'm going to make a change to this because this is 0 through 7. There are 8 address spaces, and you get a more randomized distribution of the items you add to your hash table, which is optimal, if you have a prime number. So I'm going to remove that last item and just make this 0 through 6. So it's going to have 7 items in it. And then we can start building out our class for the hash table, beginning with a constructor. And if you haven't seen this before, this, where you have an argument equal to a particular value, this is the default if you don't pass it a value. So you could pass this the number 11 and it will give you an array with 11 items in it. But if you don't pass it anything at all, it's going to give you an array with 7 items in it. So that next line there, this.datamap equals new array of that particular size. And that is all there is to the constructor. So now let's build out our hash function. And I'm just going to bring in the whole function and then we'll walk through this. So here is the function. So let's take a look at the name here. It has an underscore. So this tells other developers that might be using your code that this is a method that should only be called by other methods. You should not be calling this directly. And then you pass it a key. So that's in our key value pair. Let's say you have paint, you have 50 gallons, paint is the key, 50 is the value. So you're going to pass it the string paint. So in the next line here, we're going to declare a variable hash, set it to 0, and then we're going to have a for loop. So the way this for loop works with the key.length, remember key was paint, dot length, it is 5 characters long. So this for loop is going to run 5 times. And we're going to set hash equal to hash plus this. And what this is every letter has a particular numerical value. So we're going to be iterating through the word paint in this case. The first letter P has a numerical value, and then the next letter has a numerical value. And every time we loop through this, we're going to multiply this by 23. And the reason I picked 23 is it is a prime number, and it makes this more random. And you can just put any prime number there you want. And the modulo operator, what this is it gives you the remainder when you divide. So you're going to divide whatever this is going to come up with by datamap.length. And remember, the data map is our address space. And the remainder, because this is going to be 7, the remainder will always be 0 through 6. And that is what's going to determine what address space a particular string is going to go into. And then we're going to return hash, and this number is always going to be 0 through 6 if you have an address space that is 7. And that is how that hash function works. And you can do this math however you want, so long as, in this case, there are 7 address spaces, 0 through 6, it just has to always return something that is going to be 0 through 6. So there is our code. So let's go over and look at this in DevTools. So there is our constructor there. That's just going to create our empty array. And there is our hash function there. We're not going to use that here. We're only going to use that when we create other methods that put things into the hash table or remove things from the hash table. And this is where we create our hash table. And I'm going to zoom out and run this. Okay, let's zoom in on this, and I will open this and open this. And you can see that data map is just an array with a length of 7. All right, so that is our hash table constructor. Okay, so now we're going to do our set method for our hash tables. And we're just going to bring up this address space and our hash function. And then we'll set an item, in this case, bolts. That key, bolts, is going to get run through our hash function, and it's going to produce the number 4. Also, our set method is going to produce this array with the key and the value, and we're going to put that at the address of 4. So I'm just going to remove this, and then we'll get into the code. So our set method, we're going to pass it a key and a value. And the first thing we need to do is figure out the index where we're going to store this key value pair. So we're going to have a variable that we call index, and then it'll be equal to this dot hash. We pass it the key, which gets run through that hash method. That is going to produce the number 4, and that's going to be our index. So that variable index will be set to the value of 4. Okay, so the next thing we need to do is build this empty array that we will push the key value pairs into. And we'll just do it like this. So this line here, this dot data map, at the index of 4, we want to create this empty array like this. And this is a step that we only want to do if there isn't already an empty array in there. So if we were going to insert something else at the index of 4, we wouldn't want to do this step. So we'll wrap this in an if statement like this. So this is basically saying if this is completely empty, only then will we do this. Now we can push in our key value pair, and we'll do it like this. We'll walk through this. This dot data map index, and this is the index of 4, we're going to push the key value pair, the array with these two items. So that gets pushed into there. Now let's look at adding another key value pair to the same address. We'll run the set method, pass it a key and a value. In this case, it's going to be washers. First thing we have to do is run the hash to see what address it is going to be. And the index for washers with the hash method that we're using is also going to return 4. So index is going to be set to 4. Then we move to this if statement. Is there already something at the address of 4? There is, which means we are not going to do this step, and we're going to move to this step. And it's going to push this key value pair into there. And then I'm just going to add one more key value pair. This will go at the index of 6. There is one more line of code that we need to add, and that is to return the hash table. When we move over to Chrome DevTools, we're going to use this code, and we're going to build an empty hash table with 7 items in it, just like this. And then we're going to use the set method to put all 3 of these key value pairs into the hash table, and then we'll take a look at the hash table. So let's flip over to DevTools. Okay, there's our set method that we just created. And then the hash table that we're going to create here is just going to be an empty hash table. So let's zoom out here. I'll go over here and run this. And I'm just going to open this and show that this is an empty hash table with a length of 7. And I'll clear this. And I'll just use the up arrow. I've got these saved here. We have lumber, that's going to go at the index of 6. Washers. And bolts. Okay, so I'm going to clear this. Then I'm just going to say my hash table. And I'll press enter. Now when we open this up, you can see that we have 2 items at the index of 4 there. I'll open this up. And those are our washers and our bolts. And down here at the index of 6, we have lumber. And that is our method for set. Okay, so now that we're done with set, now we're going to write get. So I'm going to start by bringing up this address space here. I'll bring it up on the bottom this time with bolts and washers. And this to represent our hash method. So if we say get washers, it's going to go into the hash method, and it's going to return the number 4, just like it did in the set method. And then we can go to the address of 4, search through these key value pairs at that address, and what we want to do when we look for washers is we want to return the number of washers that we have and return the number 50. But if we say something like get lumber, and we put it through our hash method, it's going to return the number 6. We go to the number 6, lumber isn't there, and this will return undefined. So let's shrink that down here and start writing the code for this. So we're going to say get a particular key, and just like we did in the set method, we have to get something by the index. So we're going to have a variable called index, and we're going to use the hash method to determine what that index is going to be. So we pass that the key. It's going to calculate what the address is, and then we can go directly to that address and search for our key value pair. Okay, so the next thing we have to do is determine if there's anything at that address. So we'll say if this .datamap at that particular index, so if we're talking about the index of 4, there is something there. If we're talking about the index of 6, like when we looked for lumber, there is not. If there is not, we're going to say return undefined. But if there is something there, that's where we're going to have a loop to loop through the key value pairs to look for the key. So for that, we're going to use a for loop. So this part right here, this length, is the length of this array here. So that has a length of 2. It has 2 key value pairs in there. So as we're looping through, we're going to say if, and we'll walk through this line, the index is 4. And I is going to be this first key value pair. And then 0 is going to be bolts, the first value in that array. So say we're looking for washers, we'll have to do this again, where we say index is, once again, 4, but I is going to be this next key value pair. 0 is going to be washers. Now it is equal to the key, and what we want to do is return the value that is associated with washers. So we just do it like this. And that is going to return that number 50. But if we go through this for loop and we don't find what we're looking for, then we are going to end up returning undefined. So that is all of the code for this method, and we are going to build this hash table just as you see it on the bottom here with bolts and washers. And then we will use the get method to get these items, but we'll also look for an item that's not in there, just like we did here. We're going to look for lumber. Okay, so let's flip over to DevTools. Okay, so there is our get method, and this is the hash table we just showed a second ago with bolts and washers. So I'm going to zoom out here. I'm going to come over here and run this. And this hash table here, I'll just open it. We have our data map. And you can see here at the index of 4, we have 2 items. And at the index of 4, we have 2 key value pairs, bolts and washers. Okay, so now I'm going to say get bolts, and that gives us a quantity of 1,400. Washers is 50. And then if we do lumber, we get undefined. So this works for all of our test cases here for bolts and washers and lumber, and that is our method for get. In the keys method, what we're going to do here is take all of the keys that are in the hash table and return them in an array. So I'm just going to bring up our hash table here. We're going to have a couple of items in here, bolts and washers. So in order to return all of the keys, the first thing that should be obvious is we're going to have a loop that's going to start at the beginning and then start going through looking for items. And when it gets to an address that has items, we're going to need another for loop to go through this array to return the keys from these key value pairs. So I'm going to put that back, and we can start coding this out. Okay, so the first thing we have to do, we know we're going to return an array with these items. We have to create that array. I'm just going to call it all keys. Then I also mentioned that we're going to have 2 for loops. So the first for loop is going to go 0 through 6 through the length of the array that we have called data map. Then we're going to have a second for loop to go through these items. And that's going to look like this. So as we're going through that first for loop, we're going to start at this 0. And that doesn't have anything at that address space. So we don't want to run the second for loop at all. So what we're going to do with the second for loop is we're going to wrap this with an if statement. We're only going to run that if there is something at that address. So then we're going to move across until we finally get to that index of 4 where we have a couple of items, and this if statement is going to be true, and then we're going to run that second for loop. And when we do, we will push those items into that all keys array with this code here. Then the only thing left to do is to return the array. So we will look at this code in a moment, and DevTools, we will also build out this hash table just like you see it here. All right, so let's flip over. Okay, so there is our keys method there. And this is going to build the hash table that we just saw. So I'm going to zoom out here, and I'm going to run this, and I'm going to open this hash table. So you can see here at the address of 4, we have 2 items. I'm going to open this, and we have bolts and washers. Okay, so I will close this and run our keys method. And this returns an array with bolts and washers. So I'm just going to set one more item here. I'll put lumber in there with a quantity of 70. And I'll clear this. And now we'll run our keys method here. And now we get bolts and washers and lumber. Perfect. And that is our method for keys. Now let's look at the big O of hash tables. So I'm going to bring up a hash table here, and each address has a linked list instead of the arrays that we've been using, just because this is easier to look at and present graphically. And I'm going to bring up this box, which represents our hash method. So when we run a hash on one of these keys, that equation is going to be the same number of operations, which means it's constant time. So the hash itself, the hash method, is O of 1. So if we're going to set a new item, a key and a value, and we run that key through the hash method, and we get a particular address, say 2 in this case, and we push that item on, that's an O of 1 operation. Also, if we do a get, like get screws, in this case, we put that into our hash method, it's at the index of 6, and we can find that in one operation. But what if screws is not down there where we can find it in one operation? Say we have a situation like this. Now when we say get screws, it's very quick to get the index of 2, but then we have to go through the entire linked list to get to what it is that we're looking for. So you might say that this is O of n as our worst possible scenario. But when we're dealing with a hash table, especially the built-in hash table, which is objects in JavaScript, there's going to be a much larger address space. The hash function is going to be very efficient at randomizing the addresses where things get assigned. So it's going to look something more like this. You might have some collisions, but it's going to be rare. And because of that, finding something by the key of the key value pair is O of 1. And that is the important thing to understand for hash table, big O. So now we're going to look at a very common interview question, and it may not be exactly like this, but it'll be some variation of what I'm about to show here. So I'm going to bring up two arrays, and our objective is to write a formula that returns true or false as to whether these two arrays have any items in common. And you can see that last item, number 5, they have that in common. And we're just going to assume these arrays are the same length. And let's just walk through how we would do this if we were just using for loops. So we'd have a for loop for that first array that starts with the first number, and then a nested for loop that goes to the second array that checks to see, does that match? Does that match? Does that match? And if none of these match, we go to the next number in the top array, like that, and do the same thing on the bottom array. And then we move again on the top array and move through the array on the bottom. And then in this case, we find this matching number and we return true. But because this has nested for loops, this is going to be O of n squared. That is very inefficient. And so let's just quickly walk through the code of doing it this way. This should be pretty simple by now. We'll have a function, we'll call it item in common, and we will pass it each of these arrays. And we'll have a for loop that goes through the first array, a nested for loop that goes through the second array, and if at any time these match, we'll return true. Otherwise, if we go through these for loops and don't find any matches, we'll return false. So let's just flip over to Chrome DevTools and take a look at this. So there is the function we just wrote. These are the two arrays, and we will run the function here. So when I run this, we'll either get true or false. And we'd expect true because we have those two 5s that are items in common. So I'll run this, and sure enough, that is true. And then on array 2, I'm going to change that 5 to a 6. And then I'll run this again, and we get false. So this works, it's just not super efficient. Okay, so now let's flip back. So this is where we left off here, but there's a more efficient way to do that, and that is with an object. So this is what we're going to do. We're going to loop through that first for loop, and each of these numbers, 1, we will add this to the object, that's the key, with a value of true. And we'll do that for the next item in the array, set that to true, and the next item in the array, and we'll set that to true. So now what we can do is just loop through the second array and say, is 2 in this object as a key? And that is an O of 1 operation. And then we can check the number 4, and then check the number 5, and it's finally going to come back true. But the difference here is that the number of operations is far less. We went through each array one time only. So you could say that that's O of 2n, but of course we drop constants, which makes this O of n, which is much more efficient than O of n squared. So the interview question is not so much about can you write code to make this work, it's really about can you write code that is more efficient. So now let's look at coding this using an object. So we'll create an object like this, just an empty object. Then our first for loop is going to loop through the first array just like we did last time. But instead of the nested for loop, we're just going to move all those values from the array into that object. Then we'll have a second for loop. Now the for loops are one after the other instead of one inside of the other. And then we just check to see if any item in that second array matches an item in that object. And if it does, we'll return true. And then if it doesn't, we return false. Okay, so now let's flip over to DevTools. And there is our new function that uses the object. It has the same name. You're passing it the same arguments. We will use the same arrays here. and we will call the function here. So when I run this, we should get true. So that works all the same way. Then if I come up and change this second array to be 2, 4, 6, now when we run the code, it returns false. So these functions are going to do exactly the same thing, but can you make it efficient is the real interview question. Welcome to graphs. So we're going to go over a little terminology here before we get into this. This, in a graph, you'll hear this referred to as a vertex or a node. Vertex is actually the proper terminology, but you will hear people refer to this as a node sometimes. And I'm going to bring up another one of these. So now let's connect these two. And this is called an edge or a connection. Edge is actually the proper term, but you will hear people say connection. But this should be called an edge. So I'm going to bring in another vertex here. And one of the things about graphs is this new vertex can connect to this vertex, it can connect to this vertex, or it can connect to both. There's no limitation to how many other vertices a particular vertex can connect to or have edges with. So what do we use these graphs for? Let's say that we want to go from here to here. This would be like a Maps app, like a GPS on your phone. Well, obviously, the wrong way to go would be to go this way and then up this way, because there's a much faster way to just go one hop like that. But one of the things about graphs is we can weight these edges like this. Now, the most efficient way to go, because you want to go the least cost path, would be to go this way. You don't want to go this way because there's probably traffic on that road. This is something we also use in routing protocols on a network. You might have two very fast links and one very slow link. It would be better to have that extra router hop to be able to send your data. That's another example of a graph. So there's another aspect of edges that we're going to look at here. Let's say this is Facebook and you have you and a friend. The friend is friends with you, and you are friends with them in Facebook with normal accounts, not like celebrity accounts or things like that, but just a normal friend. You are friends with each other. So that is a bidirectional relationship. And if you have all bidirectional edges, it is generally represented with a line without arrows. It's assumed that if there aren't arrows, that it's bidirectional. So now let's change this. Instead of you and a friend, let's say it's you and a celebrity on, say, Twitter or Instagram. This is a one-way relationship. On those platforms, you can follow someone without them following you back. In fact, in this situation, it is most likely that they are not following you back. So that is a one-way relationship. Now, in this course, the way we are going to build our graphs is that all of the edges are going to be bidirectional, and they are not going to be weighted. But I wanted to show you that those are possibilities, and those are things that we do with graphs. I also wanted to point out that we have seen a couple of graphs in this course. A binary tree is a type of graph that just has the limitation that it can only point to two other items, and each of the connections are directional. And in the tree section, we mentioned that we had seen another tree, and that was a linked list. So linked lists are trees, and trees are graphs. Therefore, a linked list is also a graph. But typically what we think of is something that looks like this when we think of graphs. So there are a couple of ways we can store a graph. One is an adjacency matrix, and the other is an adjacency list. So let's look at the adjacency matrix first. Let's say we have this graph here. The adjacency matrix for this would look like this. So let's build this out. Let's start with A, and A points to E and B. So in the adjacency matrix, A points to B and E. We would put 1s in those spots. And then A can't possibly point to A, so we'll put a 0 there. And it also doesn't point to C and D. So that's how you represent A in the adjacency matrix. Then we have B, it points to A and C, and that would be B pointing to A and C, and everything else is 0. And then I'll just build out the rest of these like this. That is what our adjacency matrix would look like for that graph. So on this axis here, that is the vertex, and this is what it points to or not. And like I mentioned before, A can't point to A, and also B can't point to B, and so on. You're going to have this 45-degree line where there are always zeros in an adjacency matrix. If the graph has all bidirectional connections, the matrix is going to be symmetrical across that 45-degree line. It's going to be a mirror image. But let's see what happens when we make one of these connections directional instead. We'll just take the one that is between A and B and focus in on that. So first, let's look at what it means for this to be bidirectional in this matrix. If we say A connects to B, that's that one there. We have a 1 there. And then if we have a connection going back from B to A, that is the other connection in the matrix there. B is connecting to A. But if we just say that A connects to B, then in the matrix we have to do the one from B to A and change that to a 0. So as soon as we have any of these connections that are directional, the matrix is no longer symmetrical. So I'm going to change this back to being bidirectional in our graph, and then I'm going to change the matrix to reflect that as well. So now everything is symmetrical again. Also, if we wanted to make this graph weighted like this, instead of having the matrix be all 1s, we can change it to where we store the weights in the matrix. So I'm going to change these all back to 1s and remove those weights from the graph. And that is our quick overview of an adjacency matrix. Now that we've looked at the adjacency matrix, let's build out an adjacency list. I'm going to bring up the same graph that we used before. I'm just going to represent this in an adjacency list instead of an adjacency matrix. And this is going to be very simple. So we're going to store this in an object. So we're going to start at the top there with A. It is connected to B and E. And in the object, we will represent the vertex A and its edges like this. So A is the key. The edges will be B and E. Now let's just move around this graph. Let's look at B. It is connected to A and C. C is connected to B and D. D is connected to C and E. And E is connected to A and D. It's as simple as that. And because this is so simple, this is what we're going to use in this course to represent our graph. And that is our very quick overview of an adjacency list. Okay, so now let's look at the big O of graphs. So we're going to represent this graph as an adjacency matrix and an adjacency list. And then we're going to look at the difference in big O for doing various things with an adjacency matrix versus an adjacency list. So the first thing we're going to look at is space complexity. So with an adjacency list, we're going to store the vertex and the edges. Now I'm going to highlight these two edges, B and E, in the adjacency matrix over here in green. We are going to store those. But with an adjacency matrix, we are also storing everything that A is not connected to. You have to store both. So that makes the adjacency matrix very inefficient when it comes to space complexity. So let's look at what the space complexity is on each one. So for the adjacency matrix on the left, it is the number of vertices squared. So we have 5 vertices, we have 25 entries here. Whereas with the adjacency list, you can see we are storing all of the vertices and then all of the edges. So it's the vertices plus the edges. And that's the space complexity of the adjacency list. Now let's bring back our graph. If we're going to add a vertex, let's look at how we do this in each one of these. We'll start with the adjacency list. If we're going to add a vertex, we're just going to slide it in like that. So it's very easy to do with an adjacency list. Now let's look at the adjacency matrix. We have to change the matrix to look like this. It would be the equivalent of having to create a new matrix. So when we look at the time complexity, it is the number of vertices squared for the matrix, but it's O of 1 for an adjacency list. Okay, so let's bring our diagram back here. And if we want to create an edge between B and F like that, let's look at each of these, starting with the list. Remember, this is between B and F. We just push something onto this array, the F onto that array, and we push a B into this array. Okay, so now let's look at the matrix. With the matrix, we're going to change this value here. We're going to change this value here. It's also very simple with the matrix. So the big O on each of these is O of 1. Let's bring back our diagram here. And let's say we want to remove the edge. We'll look at these, starting with the list first. Remember, that edge was between B and F. So we're going to start at B, and we're going to have to go completely through that array and look for an F. And that array can be pretty large. A particular vertex can be connected to a lot of items. And we're going to have to iterate through that array to find the value that we're looking for and remove it. Then we're going to have to do the same thing for F, and we only have one value here, but once again, there could be a lot of values. We have to find B and remove that. With an adjacency matrix, we're just going to go here, change that to 0, go here, change that to 0. So the advantage on this one actually goes to the adjacency matrix. It's O of 1 versus O of the number of edges that we would have to iterate through on the adjacency list. Let's bring back our diagram again. The next thing that we can look at is removing a vertex. Let's bring these both back up. We'll start with this one. So it's very easy to remove this vertex like this. The problem is you have to go into each vertex like this and say, hey, in the list of edges that I have, do I have any Fs? Then you go into this one, and then you say, in this list of vertices, do I have any Fs in here? And you're going to have to touch every vertex, every edge, to be able to remove all of those Fs. Now, if you have bidirectional, there is a shortcut that you can use to make this a little bit more efficient, but still you're going to have to go and look at a lot of different vertices and iterate through the arrays with the edges. With a matrix, when you remove this, it is going to be also very inefficient. It's going to be O of V squared. With the adjacency list, it's O of V plus E. So you're going to have to touch every one of these, which is going to be better than the adjacency matrix. Now let's do another comparison on these. So I want to talk a little bit more about this adjacency matrix. As we discussed before, not only are you storing all of the ones, you're also storing all of the zeros. And the larger this gets, the bigger the problem becomes having to store all of this. So imagine this. Your Facebook, and let's say you have 1 billion users, just to use a nice round number, and you're going to have a matrix that is 1 billion across the top and 1 billion down the side. Even if each person in Facebook had 1,000 friends, the number of zeros in this matrix would outnumber the ones 1,000,000 to 1. And that's a lot of zeros to store. So it's very inefficient when this becomes very large. And that is why we are going to use an adjacency list in this course. It's a lot more efficient. It's a lot simpler to code. All right, that is our overview of graphs, big O. Now we're going to add a vertex to our graph. Vertex is going to look like this. And eventually we're going to have something that looks like this. But in order to be able to have this, we're going to have edges, and that will be a different method for creating edges between the vertices. So we'll start with this, which is actually going to look like this. So I'm going to bring this down to the bottom, and we can start writing our code. We got to start with the class graph, and I'm going to write out the constructor here as well. The constructor is simple enough that it doesn't make sense to do a separate video for it, so I just included it in this one. This is the entire constructor. We're just creating an empty object. I'm calling it adjacency list, and that's it. So the constructor is just going to create this. The add vertex method is going to do this and put it into that empty object. So I'll remove that, and let's build the add vertex method. So we'll pass it, in this case, the letter A. Then we add it to our adjacency list object like this. We set it equal to that empty array, and that creates that vertex. But we're not allowed to have duplicate vertices, so we do have to wrap this in an if statement that says if there isn't already a vertex with this value, then we can add that. Also within the if statement, we will say return true, that we were able to add that. Otherwise, we will return false. We'll take a look at this in DevTools in a moment, and we will create that vertex with a value of A. So let's flip over to DevTools. Okay, and there is our constructor that creates that empty object and our add vertex method. Then down here, we're just going to create a new graph, and it will be empty. So let me run this. And then let's come down here and open this. And you can see that this adjacency list is empty. So let's clear this. And then we will add a vertex with the value of A. It returns true that we were able to add that. I'm just going to try to add this again to show that it is going to return false the second time, because second time around this is a duplicate. So I'm going to clear this. I'm going to say my graph and press enter. And now let's open up the graph. And now we have that new vertex with a value of A. And that is our method for add vertex. Now that we're able to create vertices, let's add edges between them. So let's say we have these two vertices, 1 and 2. That's going to look like this. And we connect them with a new edge like this. It's actually going to look like this. That would be 1 and 2 connected to each other. So let's remove this edge for now and actually build this with our code. We'll say add edge. We're going to need a vertex 1 and a vertex 2 that we're connecting to each other. And in this case, vertex 1 is going to be the value 1. The key is going to be 1, and vertex 2 is going to have the value of 2 to make things easy. Then what we'll do is say vertex of 1, the array that's attached to it, we're going to push onto that array the value of vertex 2, which in this case is actually 2. And then we'll do it the other way, where we say on the vertex 2, we're going to push on the value of vertex 1, which in this case is the value of 1. And that adds the edge. But one of the things you can't do is create an edge between vertices that don't exist. So if you try to add an edge between 1 and 3, that's not going to work because we don't have a vertex with the value of 3. So we'll wrap this in an if statement like this. And we have to make sure that vertex 1 and vertex 2 actually exist. And then we can do those two other steps to actually push those values into those arrays. And then inside of the if statement, we'll say return true. Otherwise, we're going to return false. So let's take a look at this code in DevTools. So there is our add edge method. And we're going to create a new graph down here and create those two vertices 1 and 2. So I'm going to run this. And then I'm going to open this. And you can see we have our two vertices 1 and 2, but they are not connected to each other because those two arrays are empty. So I'll clear this. So I'll say mygraph.addEdge with the numbers 1 and 2. I'll press enter. And it returns true. I'm also going to run this with 1 and 3. And you can see that this returns false because the 3 vertex does not exist. So I'm going to clear this. And then I'm going to say my graph and press enter. Let's open this up. And now each of these nodes are connected to each other, and we have been able to add an edge. So now that we have added an edge, let's look at how to remove an edge. So that's going to look like this. On the diagram, we'll just remove that line. In the object above, that's the equivalent of doing this. So I'm going to bring these back for now, and we'll write the code to actually remove those. So we'll say remove edge, and it's going to be between vertex 1 and vertex 2. So I'm going to do something we haven't done in this course to this point. Okay, so I'm going to say adjacency list vertex 1 equals adjacency vertex 1 dot filter. And you can wrap these onto separate lines like this, or you could have it be on all one big line. So filter is a method that is built into JavaScript for working with arrays, and you pass this as an argument a function. This is called a callback function. So what we're doing here is saying return everything in the array that is not equal to vertex 2. So in this case, that's just going to remove this item. But if we had 100 items in here, it would return the 99 that are not equal to 2. And then we're going to do the same thing for the second vertex, like this. And we'll say dot filter, and we want to return everything that is not equal to vertex 1, which removes the 1 from that array. So just like we had in the add edge method, we couldn't add an edge between two vertices that didn't exist. We can also not remove an edge between two vertices that don't exist. So we're going to wrap this in an if statement that says only do this if vertex 1 and vertex 2 both exist. And if they do, we'll remove those items and then we will return true. If vertex 1 and vertex 2 don't both exist, we will return false. So we will look at this code in a moment. In DevTools, we will build this graph and we will look at it. Then we will remove the edge between A and B like this, and then we will look at that to make sure that that worked. Okay, so let's flip over to DevTools. And there is our remove edge method. And then down here is where we're creating that new graph, A, B, and C. And we have edges between all of those vertices. So we'll zoom out here, and I'll run this. And we'll open this. And there is A, B, and C. And then you can see that they are all connected to each other. So I'm going to clear this. And I will say myGraph.removeEdge. I'll pass it A and B. It returns true. I'm also going to try this with A and D, since D does not exist in this graph, and it returns false. I'll clear this, and we'll say myGraph, and I'll press Enter. And now when we open this, you can see that A and B are no longer connected to each other, which means we have been able to remove the edge. So now we are going to remove a vertex. So if we have this graph and we're going to remove D, not only do we have to remove that vertex, we have to remove each one of these edges. So we remove the edges first, then we remove the vertex. So I'm just going to bring this back, put the edges back the way they were. So we represent this with this. This is the same thing. So I'm going to focus in on this because this is what we're really going to be dealing with when we write our code. I had mentioned in the Big O video that there is an efficiency that we can use in removing a vertex if everything is bidirectional. And the information that we need to make this more efficient is all contained in this array right here. Because what we can do is we can pop this item from this array. We'll set it equal to a variable. And we know, because it's bidirectional, that C has an edge with D, and then we can go find that and remove it. And then we can do the same thing for B and come up here. We know there's a D in here. We can find it and remove it. Then we do the same thing for A. Come up here and remove the D here. In this case, D is connected to everything else in the graph, but you could have 1,000 other vertices, and you'd only have to go to these three to remove the edges with D. So that's a huge efficiency. Once this array is empty, all of the edges have been removed, and now you can remove the vertex itself, and you'll be left with this as your graph, which would also look like this. So let's get into the code. We'll say remove vertex, and we have to pass it whatever vertex we want to remove, like this. So I'm going to use a while loop here to loop through that array that is associated with the vertex that we're going to remove. And we'll say, while this .adjacency list for that vertex .length, which means while the array still has length. To put it another way, as long as the length of the array isn't 0, we're going to run this. Then we'll have a temp variable here, and we'll set it equal to whatever we pop from that array. And once we have that piece of information, we can actually use the remove edge method that we just created in the last video. And we can do this. So you need to have the two vertices that you're going to remove the edge between in order to use the remove edge method. So there's the vertex that you're removing, and then there is the item that you popped off of that array. That's all the information you need to be able to remove that edge. Then you can just go through this while loop until you remove all of those from the array. So it would look like this. We're going to pop that C. So temp is going to be equal to C, and then the vertex that we're removing is D. So if you have C and D, you can remove that item with the remove edge method. Same thing here. We run it again when we loop through again, and same thing here when we loop through it the last time. And now we have an empty array. And when we have an empty array, that is going to break us out of this loop then the only thing left to do is to delete the vertex. So that's going to look like this. And that's going to leave us with this, which is going to look like this. So let's bring our code back here. So one of the things I haven't done to this point, and I did this on purpose, and see if you caught this, you cannot remove a vertex that doesn't exist in the graph. And that needs to be the first thing that we do here. If this doesn't exist, we're going to return undefined. We're only going to be able to do this while loop and then delete that vertex if it actually exists. Assuming that it did exist, and we have gone through all of this, we are going to return the graph. So when we go over to Chrome DevTools, we're going to look at this code, and we are also going to build this graph and remove the D vertex and all of the edges that go with it. And we will be left with this graph, and we will go check this, and we would expect to see something that looks like this. So let's flip over to DevTools. And there is our remove vertex method. And this builds out that graph that we just showed in the diagram with A, B, C, and D vertices and the appropriate edges. So let's zoom out here, and I will run this. And we'll zoom back in and open this. And we open this adjacency list, and that's what it looks like before we have removed the D vertex. And when we're done, that'll be gone, but also all three of these edges where the other three nodes connect to D. So I'll clear this. So we'll say myGraph.removeVertex with the value of D, and we press enter. Then it returns the graph. But I also want to make sure this works when we have an invalid vertex. We'll try this again with E, like that, and I'll press enter. And that returns undefined, just as we would expect. And now I'm going to type in my graph, and I'll press enter. And we'll open this. And we can see that the D vertex has been removed and all references to it. And it looks like we have successfully removed the vertex. So now we're going to do recursion. And this is a very cool topic. And we will use this quite a bit in the algorithms section of the course. So my favorite definition of recursion is that it is a function that calls itself until it doesn't. So let me show you what I mean. I'm going to start with a gift box here. And let's say in order to open the gift box, we have to run the open gift box method. And there's one of two things that we're going to get when we open this gift box. We're either going to get a ball. I'm going to make it an orange ball because that's my son's favorite color. Or we're going to get another gift box. And if we get a gift box, we need to open it, and we open gift boxes with the open gift box method. And when we run this, we are either going to get that orange ball, or we're going to get a new, smaller gift box. And we'll run the open gift box method again to open this one. And let's say this time we actually get a ball. So let's walk through what this code might look like. And I want to emphasize here that this is pseudocode. This isn't real code that you can run. This is for example purposes only to simplify this. So please don't go write this code and expect this to work, because it won't. So this is the function that we're going to use for this, the open gift box function. So let's walk through this. We'll say if it is a ball, then return the ball. Otherwise, it's another gift box, and we're going to need to run the open gift box function, which means the function is going to call itself. So there are two key rules that you have to understand with recursion. First, the process of opening each new box is the same, or the process of doing whatever you're doing with recursion has to be the same. You're doing the same thing. So in this case, we are constantly opening gift boxes. The other thing is that each time we open a box, we make the problem smaller, or whatever you're doing with recursion, each time you have the function call itself, it has to be operating on a smaller and smaller problem. So let's walk through this function. In this case, we have a gift box, so we're going to run the function open gift box. And then we're going to say, is this a ball? If it is, we're going to return the ball. Otherwise, we know it's a gift box like this, and we're going to have to run the open gift box function, which is going to create another instance of this function to open the second gift box. Now we're going to say, is this a ball? In this case, it is not. It's another gift box. So we have to open the gift box, and we create another instance of the open gift box function. And this time, when we run this if statement, this time it is a ball. And that causes us to not run this line of code. So we stop creating new instances of the function open gift box. And we do that because this was finally true. So I'm going to remove this. We'll talk about another concept here. When we open a box and it has the ball in it, this is what's called our base case. This is when our if statement was true. If it is another gift box, this is what we call a recursive case. In this case, we need to have the function call itself again. And when we have another gift box, that's a recursive case. Then when it is finally the ball, that is the base case, and that is when we stop opening gift boxes. So let's bring this code back here, and let's focus in on this if statement. You always have to have some conditional that at some point is going to be true and cause you to stop having the function call itself. If you don't have this if statement here, you end up with a situation where you call the function, and then that causes you to call the function again, which causes it to call itself again, and so on, and you end up with an infinite loop, and you have what is called a Stack Overflow. So let's bring that if statement back. It's very important. A couple of key mistakes that people will make in a recursive function. They will have an if statement that is never true. So like in this case, 1 is never greater than 2. So the if statement is never going to be true. So you are going to end up in that infinite loop where you end up with a Stack Overflow. And this one's obvious. You can just look at it and figure out that that's never going to be true. But sometimes we have things in an if statement that are much more complex. And if you end up with Stack Overflows, this is one of the places to go troubleshoot. So let's bring this back. So one of the other things that you have to have with this if statement is you have to have a return in there. So let's say you don't have that, and you have something like console log hello. So you run this until the if statement is finally true. It console logs out hello, but because there's no return statement, you go to the next line of code and go back into that infinite loop of adding new instances of the gift box function, and you end up with a Stack Overflow. So it is required that you have a return statement in there. Okay, and that is our overview of recursion. So now I'm going to talk about call stacks. This is an important subject to understand if you want to wrap your head around recursion. So we had a data structure called a stack, and we used the analogy of a can of tennis balls. It's only the top tennis ball that you have access to at any one time. So you remove that one. Now the second tennis ball, we can remove that one now. And it's only when those have been removed that you can get to the one on the bottom. So I'm going to keep this structure of a stack here, and I'm going to move it over to the right, and we're going to use it as a call stack. So I'm going to explain the call stack with code that is not recursive, just to explain the call stack. Then we will get into some recursive code that uses the call stack in the next video. So I have some code here. I'm going to call this function, function1, and it's just going to console log out the string 1. So when you run this function, it goes onto the call stack. That function does. And when it runs, it's going to console log out 1. Once it's done doing that, function 1 is done running and will be removed from the call stack. So I'm going to bring this back and I'm going to change this function where before it console logs out the number 1, it is going to run a different function called function2. And function2 is going to look like this. It is just going to console log out 2. But before it does, we're going to have it run another function. We'll call it function3. And when function3 runs, that gets pushed onto the call stack, and it looks like this. Now, function3, we're just going to have it console log out 3. We're not going to have it call another function. But when it gets done writing the 3 to the console, this function is done running. And once it's done running, we can pop that from the call stack. Now you can see that function 2 is the top of the call stack. You can look at it like this. We were waiting for this line of code to complete, function 3, before we move to this line of code. Now we can console log out that 2, and now function 2 is done, and we can remove that from the call stack. Likewise, function 1 was waiting for function 2 to be done, and it can now console log out the 1, and now we can remove function 1 from the call stack. So notice we called function 1 first and function 3 last, but the 3 printed to the screen first and the 1 printed to the screen last. They're in reverse order of which they were called. And that is due to the order that these were put on the call stack. That's going to determine the order that these are going to be console logged out. So let's bring our code back up here. We'll look at this in DevTools. There is our code here, our 3 functions, and this is where we call function 1. So I'm just going to zoom out here real quick, come over here and run this. And you can see that we have 3, 2, 1, just like we would expect. And I'm going to clear this. So the real thing that I want to show here is this. Up here in the upper right-hand corner, this button right here, it says Show Debugger. I'm going to click on this, and we get this screen here. The thing I really care about, I'm going to close some of these, is call stack and breakpoints at this point. Then I'm going to come over here to where it says function 1. See, it highlights that number next to it. I'm just going to click on it, and it creates a breakpoint. And we can see that because it's highlighted, but we can also see it here. I'm just going to close this. And when I hit run snippet, that breakpoint is going to make it where that line at 15 is now highlighted. And what it allows us to do is walk through the code one step at a time instead of all of it just running. So up here, that button is for us to step through. Down here, function 1 is highlighted in green. That means that is the next line of code that is about to run. And when I click on the step button, it's going to run that one line of code. So I'm going to click on this, and on the call stack is function 1. Then over here inside of the function, it is about to call function 2. I'm going to click step again right now. That puts function 2 on the call stack. And the next line that's about to run there, this in green, is about to call function 3. So I'm going to click on step, and now function 3 has been added to the call stack. And you can see that console log now is the next thing that's about to run. So I click on step, and now it console logs out 3. When it gets to the curly brace at the end of the function up here, that means that we're about to end that function and remove function 3 from the call stack. So I'll click this again, and function 3 is now gone from the call stack. Now the next thing is we're going to console log out 2. I'm going to click this. Now we have console logged out 2. Now we're at the end of function 2. I click this again, function 2 will pop from the call stack, like that. Now we're at console log 1, and we click this. It console logs out 1 down here. Now we're at the end of function 1, and when I click this, function 1 will be removed from the call stack. So I'm going to click this, and now that has been removed. And that is our overview of the call stack. Just about any course that you're going to see that talks about recursion is going to use factorial as an example of how to use recursion. So what is a factorial? This is 4 factorial, is how this is pronounced. And what it is 4 times 3 times 2 times 1. So let's bring this up here and look at why it's such a great problem for recursion. These last 3 numbers, 3 times 2 times 1, is equal to 3 factorial. So you could say that this is 4 times 3 factorial. And 3 factorial, that's the same as saying 3 times 2 factorial. And 2 factorial is the same as saying 2 times 1 factorial. And 1 factorial, well, this is just 1. This one's different. This is our base case. Once we get to 1, we can stop doing this breakdown that we just did here. One of the things we've already said about recursion, and we saw this in the gift box example, is that each gift box has to be getting smaller and smaller until you finally get to what it is that you're looking for. So getting to that 1 would be the equivalent of getting to the ball. So I'm going to shrink this down here so we have some room for some code. And I'm just going to bring the code in. It's kind of hard to go through a recursive function line by line. So I'm just going to bring this in, and then we can talk through how this is going to work. So our function is going to be factorial. We're going to pass it the number 4. That's going to be the n. If we ever get to the point where n is equal to 1, we're just going to return 1. So n equaling 1 is this right here. N equals 1. We return 1. Otherwise, we're going to return n, in this case 4, times factorial of n minus 1, which is going to be 3. So we could look at it like this. It's 4 times 3 factorial. So I'm just going to put this code up in the corner right here, and then we will walk through this step by step. We're going to run the factorial function, and we will pass it the number 4. Then we're going to go back up to our function here and look at that if statement. If n equals 1, we're going to return 1. That's not the case. N is not 1, it's 4. We're going to return n times factorial of n minus 1. And that is going to look like this. And we're going to put the 4 and the 3 in there like that. And then we're going to do it again. Is n equal to 1? Well, it's equal to 3 now. So we're going to do the same thing, like that. And now we're going to have 3 and 2. Then we look at our if statement again. Is it 1? Well, we're getting close because it's factorial of 2 there. And now we're going to have to do this again. And we're going to have 2 and 1 in there. Now when we look at this if statement, n is equal to 1, so we can return 1. So the 1 is this 1 here. So I'm going to remove this, and we're going to look at these steps here. So the return 1, that's being returned to this function. It's been waiting for this to return. Now this can calculate 2 times 1, and it can return 2 to here. And that becomes 3 times 2. Then we can return 6 to here. And then 4 times 6 can be returned to the original function call, which is 24. Now let's just walk through this. 2 times 1 is 2, and we return that here. 3 times 2 is 6, and we return that here. 4 times 6 is 24, and we return that here. And that's our answer for factorial of 4. So let's look at this yet another way, the gift box method. This was factorial of 4, and that called factorial of 3, and the boxes get smaller and smaller, and instead of having a ball, we have 1, and we return the 1 up to here like this. We return 2 up to here like this, and 6 up to here like this, and 24. And I'm going to go over this one more way because recursion is one of those things that you have to look at it a few times to be able to get it. This is with the call stack. We're calling the call stack with factorial 4. And then we have factorial 3. And then 2. And then it's calling it with 1. So then 1 is going to return an item to 2, which means it's done running. And 2 is returning something to 3, and then when it's done, it pops from the stack. Now 3 has that value. It does what it needs to do, passes that to the 4. That gives you the 24, and that one gets popped from the stack. So now let's go over and look at this code in Chrome DevTools. Okay, so there is our code there. We're calling this with the number 4. We can zoom out here, run this, and then down here we get 24. I'm going to clear this. And then what I'm going to do here is I'm going to open the debugger, and I want to show something. And that is when I create a breakpoint here. Now I'm going to run this. So our call stack, as we step through this, we're going to have factorial put onto the call stack. That's factorial. And you can see up here that n equals 4 up here. But on the call stack itself, it just says factorial. And then we run through here, and it's going to call another instance of the function. So I'm going to click this, and now we have factorial on the call stack a second time. It will show you that n is equal to 3 this time. But the call stack itself is just showing factorial twice. And I'm just going to step through this. N equals 2. N equals 1, and we have factorial on the call stack 4 times. So you can't tell by looking at the call stack which one of the factorials it is because they all just say factorial because we're calling the same function over and over. But watch this. If I click on this, n equals 1. If I click on this one, n has been changed to 2 and 3 and 4. So they do include that on what the argument was that you passed to this. So we'll just step through this. Now you can see that it's highlighting that if statement is going to return 1. And we have popped that first item off the call stack. So the one at the top of the call stack is the one for the number 2 now, and 3, and 4. And then when we pop this one from the call stack, the only thing left is to return the number 24 down here at the bottom. Okay, so I wanted to do one more thing here. And factorials, it's amazing how fast they grow. So factorial 4 is 24. But if you go to factorial of 8, this goes all the way to 40,000. If you go to factorial 20, you get this really huge number here. So they grow very, very fast. So it's a fun function to play around with and see how fast those numbers grow. And that is our overview of factorial. So bubble sort is going to be our first sorting algorithm. It's probably the easiest one that we're going to do. So I'm going to bring up an array like this, except I'm going to show it like this. And I had previously shown arrays as being green. And what I'm going to do with the sorting algorithms is I'm not going to show them as green until they are sorted. So anything that's unsorted, we will make blue. So I'm going to go ahead and put this back to explain bubble sort. So it works like this. We're going to start with the first item. I'll highlight that in orange, and we're going to compare the first item with the second item. And if the first item is bigger than the second item, we're going to switch them. Now we're going to compare the second item with the third item. And if it's bigger, we switch them, but in this case, it's not. So now we move to the third item, and we compare it to the fourth item, and it's bigger. And we compare it to the next one and the next one. And now the 6 is sorted. That is the correct spot for the 6. Whatever the largest item is, we're going to bubble that all the way up to the top. So that took 5 steps to get that all the way to the end in a 6-item array. Then we start over and we compare 2 to 4, 4 to 5, 5 to 1, 5 to 3, and now the 5 is in the correct spot. So now the second biggest item has been bubbled up to the top. But that only took 4 steps. So each time we go through this, it will take fewer steps, but it is still pretty inefficient. So we'll do this again, 2 to 4, 4 to 1, compare 4 with 3. The 4 is in the correct spot. The next round will only take 2 steps. So we'll compare 2 with 1, and then we'll compare 2 with 3, and now 3 is in the right spot. And on the last one, we just compare these two, and if they need to be switched, we switch them. If not, these two are now in the correct spot. So I'm going to go ahead and mix these back up like this. We will pick up here in the next video where we code bubble sort. So now we're going to code bubble sort. We're going to pick up where we left off in the last video, and I'm going to shrink this down into the corner here so we have room for our code. And we're going to say function bubble sort, and we're going to pass it the array that we're going to sort. And as we discussed in the last video, this is obviously going to be a for loop inside of a for loop. So here's the first for loop. So we're going to set I equal to the length minus 1. So remember, the first time we went through it was 5 times, even though we had 6 items. And then we're going to decrement each time, because the next time we want to go through 4 times, then 3 times, etc. And this second for loop, we're going to go while j is less than I. So this makes it where the first time through, we're only going through 5 comparisons, and then the next time 4 and 3, because we're doing it while j is less than I. So for the comparisons, we're going to say if the item at j is greater than j plus 1. So this is going to be j the first time through our loop, and this is j plus 1. And in this case, we are going to switch them. And this is what we'll use to switch them. Let's walk through this. We're going to say let temp equal array j. So that's temp is equal to this value. J equals j plus 1 is going to take that 2 and move it over. And then j plus 1 equals temp is going to put that value there. So that's going to switch those 2 values. And then after we get done running through these for loops, the only thing left to do is to return the array. So let's go take a look at this code in DevTools. And for the array that we're going to pass it, I'm just going to put this back the way it was. It's going to be the array in this order. So let's flip over to DevTools and take a look at this. So there is our function there, and that's the array that we're going to sort. So the only thing we have to do is to hit run, and then we come down here, and this is the array that gets returned 1 through 6. And that is how we code bubble sort. So now we're going to look at selection sort. And once again, we'll start with an array that looks like this. But with selection sort, there's something different we have to do here. We have to keep track of the indexes. So I'm going to bring up indexes for each of these. So this is what we're going to do. We're going to start with this first item. And we're going to have a variable called min for minimum. And we're going to store the index of that first item. Then we're going to start comparing that item to everything else in the array. So we'll go to the next item here, 2 is smaller than 4, so we want to store the index of 1 in min. Then we move to the 6. That one's not lower, so we'll skip that and that. And then we move to the 1. And now that one is lower than the item that is stored in min. So we'll store the index of 4 in there. And we move to the end, and that one's not lower. So once we've moved to the end of that loop, we're going to take that minimum and that first item, and we're going to switch them. And when we do, the item at the index of 0 after the switch is sorted. So I'll color that green. Then we start with the next item in the array, set min equal to that, and do the same thing and compare it to everything else. And you can see that 2 is the lowest number remaining, so we'll loop through this, and we're not going to change that min item at all. And now that item at the index of 1, we know that is in the correct place, so I will color that green because it is sorted. Then we're going to start with the 6 and store that index in min. And I'm going to move that variable over to the left like this, since all of the large items are going to start being moved over to the right. So we compare it to the 5, that's lower, so we'll store 3 in there. And the 4 is lower, so we'll store the index of 4 in there. And now the 3 is lower, and we'll store the index of 5 in there. So the smallest number was at the index of 5. We switched these, and now we have the third one in there. And these last few will go pretty quick here. So the next item is at the index of 3. We compare it to the 4. That one's lower. That last one isn't. So we take these two and switch them. And now we look at the 5, store that in min. The next item is not smaller, so we know that these last two are sorted. And I'll color those green, and we have a completely sorted array. So I'm going to mix these up back like this. And this is where we'll start in the next video, when we'll code selection sort. Okay, so now we're going to code selection sort. We're going to pick up right where we left off in the last video with this array. I'm going to shrink it down into the corner here so we have room for our selection sort function. So we're going to pass this an array, and I'm going to create that min variable that we used in the last video, and then we're going to have our for loop. In this 6-item array, we only had to go through this 5 times. So we're going to have it run the length minus 1. So let's bring this back up here. I is going to be 0 when we first start. It's going to be that first item. So when we set min equal to 0, when we're walking through the example, we were really setting it equal to I. So the first thing that we're going to do is set min equal to I, and this is the I from the for loop. And now we're going to do our for loop that is inside of the for loop. So we're going to let j equal I plus 1. So I'm going to just bring this up. This was I. This is I plus 1. That's going to be j. So we're going to set min equal to I, which is, in this case, 0. Then we're going to say if the item that's at the index of j, if it is less than the item at the index of min, we're going to set min equal to j. So let's code that and bring our code back like this. It's going to be this if statement. If the value at j is less than the value at min, we are going to set min equal to j. So let's put this back like this. In this case, j is going to be 1. Then as that second for loop runs, j is going to move across the array like this until it finds an item that is less than the value that we have stored at the index of min. So in this case it is, so now we're going to make min equal to j again, which is equal to 4. And then we go to the end, and we're done looping through the array for that first time. Then we set min equal to 4, and then we need to swap I and min. Then that item at the index of 0 is sorted, so I will color that green. So I'm going to shrink this down and add the code to be able to swap those two items after we run through the for loop like this. And this is similar to the swap that we did in the bubble sort, so I won't walk through this in any detail. But there is something that we need to add to this. And to illustrate that, I'm going to bring this back up. And on the second time through this, this is going to be I, and this is going to be J. Now you can just look at this and see that the 2 is going to be the lowest item there. So we're going to start out setting min equal to I, which in this case is going to be 1, and then the J is going to loop through the rest of the items, but nothing is going to be lower. So when this is done, min is 1, and I is equal to 1. So now we know the item at the index of 1 is in the correct spot, so I'm going to color that in green here. But what we don't want to do is run these 3 lines of code that swap I and min because they're the same item. We only want to run these 3 lines of code when I and min are not equal. So we'll wrap this in an if statement that says if I and min are not equal, then run these 3 lines of code. So let's bring back the rest of our code here. The only thing left to do is to return the array. But of course, once we get down to this line, we will have run through all of this and have a completely sorted array that looks like this. So we'll look at this code in a moment in Chrome DevTools, and we will look at the 6-item array that we started with that looked like this. So now let's flip over to DevTools. Okay, so there is our selection sort function, and we're going to run selection sort on this array here. And we'll zoom out and run this. And there is our sorted array. And that is our function for selection sort. So now let's take a look at insertion sort. So I'm going to bring up an array here, and insertion sort always starts with the second item, and then we compare it to the item before it, in this case, the 4. If it is less than the item that is before it, we switch them like this and drop that in there. Then we move to the next item. In this case, the 6 is not less than 4, so that's going to stay put. And now the 5 is less than the 6. We will move that over, and then we'll compare the 5 to the 4. It's not less than the 4, so that's the spot where that goes. And now the 1 is less than the 6, and the 5, and the 4, and finally the 2, and we drop that in there. And then one more item. This is less than the 6, and the 5, and the 4, and we drop that in there. And now they are all sorted, so I will color them green. So in the next video, we're just going to start with an array that looks like this. I'm only going to have 2 that are out of place, so we can go through this a lot faster. And we will pick up here in the next video when we code insertion sort. Okay, now we're going to code insertion sort. So we're going to pick up where we left off in the last video with this array, with only these 2 items out of order. I'm going to shrink this down like this, and we will start our function. And of course, we're going to have a for loop. So we're going to set I equal to 1. Like we talked about in the last video, you start with the second item, and then we're going to move through to the end of the array with this for loop. In this item, we're going to set temp equal to it. We're going to declare it outside of the for loop, but set temp equal to array at the index of I, that value. So whatever item that we're working with that we have up above the array in the display below is going to be what is set equal to temp. We'll put that back. And then we're going to have our second for loop. This is the one that we're going to compare everything before that item with. And I want you to notice that I use var instead of let. If we use let to declare the variable, we can only use the variable inside the for loop. We are going to need to use this outside of the for loop. So I'm going to use var, and this is I, the item I just popped up there. So j is going to be I minus 1. So j is going to point to the item before that. Now let's say we're working with this 3. Since it's the only one that's out of order, we know how this is going to go until we get to 1 where we need to actually move it. So we'll start with this one for our example. This is going to be j here. So what we're going to say in the for loop is, while j, the value at j, the 4, if it's greater than temp, and this is the j, and this is temp, in this case it is greater, what we're going to do is we're going to move that 4 over 1. So we're going to set the next index equal to what was stored at j. Then we're going to say j minus minus, which is going to move that arrow over 1. Now we'll run through the for loop again, and now the item that's at the index of j is not greater than temp. That breaks us out of the for loop. Then we say at the index of j plus 1, that's going to be that open spot. We're going to set it equal to temp, which drops that item in there. So there is one other thing that we do have to account for, and to explain that, I'm going to switch the 1 and the 2 in our array like this. So let's say we're starting with this number. We're going to compare it to the 2. We're going to set j equal to the 2. Then we're going to look to see if the value at j is greater than temp, and in this case it is. So we're going to move that 2 over like this, and then we're going to run through the loop again, and when we do, we're going to get this j minus minus, which is going to move j over to the index of -1. And obviously this is as far as we want to go with this loop, so we have to add something to this for loop, and that is this. We have to say also j has to be greater than -1. If we ever get to the point where j is equal to -1, we stop running the loop. And that brings us down to this line, which says at the index of j plus 1, and now j is -1, so j plus 1 is the index of 0, set that equal to temp, and now that puts that in the correct spot. The only thing left to do now is to return this sorted array. So we'll look at this code in a moment in DevTools, and we are going to use an array that looks like this. Okay, so let's flip over to DevTools. So there is our function, and we're going to run insertion sort on that array. So let's zoom out here, and we'll run this. And there is our sorted array. Okay, so it looks like we have a working function for insertion sort. So I want to touch on the big O of insertion sort. Obviously, because it has a for loop inside of a for loop, it is O of n squared. That's for its worst case. That is the true big O of this would be O of n squared. But let's look at a situation where something is almost sorted. We're going to start here, and we don't do anything else because the item before it is less than. We put that back. And this one, everything before it is less than, so we're not going to do anything. And this one, we're just going to move it over 1 and drop this in. And then we go to the next one. And then we keep going through to the end of the array. And you can see that we basically just made one pass. This would be n complexity, not n squared. And I wanted to point this out because the next couple of sorting algorithms are much more efficient. They are O of n times log n. They're more complex to write, but they are faster. But they're not going to be faster if you have almost sorted data. You can use one of these sorting algorithms that are more primitive, like insertion sort, that is O of n squared typically, and have it actually run faster. So I just wanted to touch on this aspect of the insertion sort, big O. So merge sort is going to be our first sorting algorithm that uses recursion, and it leverages the idea that if you have two sorted arrays like this, these are two sorted arrays, combining two sorted arrays is fairly easy. So what merge sort does is this. Let's mix this up like this and move this to the top of the screen so we have more room. It will take this array and it will cut it in half. And then it will cut it in half again. And then it'll keep doing this until we have single item arrays. Because a single item array is by definition sorted. Then what we can do is take two of these and combine them into one larger sorted array. And then we continue doing this all the way across like this. Then we'll take these two arrays and combine them. And then we'll combine those two. Now we can take these two sorted arrays and make one big sorted array out of these. When you first look at this, you think, wow, that looks really inefficient to break all of this down into single item arrays. But it is actually an incredibly efficient sorting algorithm. It's as efficient as you can make a sorting algorithm, actually. So that is our quick overview of merge sort. So in this video, we're going to do a merge intro. So merge is going to be a helper function that we're going to use in merge sort. So merge is going to look like this. We have two sorted arrays, and then we're going to put them into one big sorted array. But let's look at the steps we have to do to make that happen. One of them we're going to use I, and the other we're going to use J. And we're going to compare I with J. And whichever one's lowest, we push that into the new array. We're going to call that array combined, the combined array. And then we do it again. We compare I and J. In this case, J is going to be lower. And we just keep doing that process. So J is going to be the lowest here all the way to the end. And we're done running through that array. So this is going to break us out of that loop. If either one of these get to 0 items, we're going to break out of that loop. And then we're going to have a different loop that says, while just this one array has items in it, we're going to just push all of the items on until that array is empty. And then, of course, we'll have another one that says if the other one has items in it, we will do the same thing with the other array. And that is our quick merge intro. So now we're going to code our helper function, merge. Here are the two sorted arrays that we're going to combine into one array. I'm just going to shrink these down here so we have room for our code and bring this in. So we're just going to say merge and pass it the two arrays. Then we're going to create our new array that we're going to put these arrays into called combined. And I'm going to create two variables, I, and I'll bring an arrow in for that at the bottom here, and J, and I'll bring another arrow in at the bottom for that. And what we're going to use here is a while loop. So this is basically saying while either of these arrays have length, while either of the arrays have a length that is greater than 0, we will run this while loop. Then we're going to say if I is less than J, and I'm just going to highlight that in the diagram below, and in this case it is less than J, we're going to push I into that new array that we're calling combined, like that. Then we want to increase I by 1, which will move it over to the next item. So when we look at I and J again, J this time is less than I. So for that, we're going to say else, and then we're going to push that item into the new array, like that. And we also need to increase J by 1, which will move that arrow over 1. So we can run through this code and add that item and the next item from J and that one and that one. And now one of the arrays is empty, which is going to break us out of this while loop. Then we just need to finish looping through array 1. So let's remove this code and bring in another while loop to loop through that array. And we'll push I into the new combined array, and then we need to say I++, which moves I over to the next item in that array. And now that one has been pushed into the combined array, and that breaks us out of this while loop. So the other possibility is that instead of array 1 still having items in it, it was array 2. So we'll just do a while loop for that that's the opposite of the while loop above it. Then we're going to return that combined array. And then we'll just have this closing curly brace. I didn't have that on the other page because this was going to get distributed across 2 pages. So let's flip over to DevTools. And there is our function. And these are the 2 arrays that we are going to merge. So let's zoom out here. I'm just going to move this up here like this and hit run. And there is our combined array 1 through 8. And that is our function for merge. So now that we've written our merge helper function, now we're going to go through the steps of writing merge sort. So the big thing merge sort is going to do is break items in half. And break them in half, and break them in half. Now the putting it back together, that's what we just wrote the code for in the merge function. So that's going to take care of doing this and this all the way up after these items have been broken apart. And merge sort is going to do this recursively. So there are 2 big things that have to be true when we do recursion. First, it has to do the same thing over and over. In this case, the same thing is going to be breaking arrays in half. And the next thing is that there has to be a base case. And the base case is when the array.length is 1. And once we have gotten to this base case, that's where we use the merge function to put the arrays back together. So with that, see if you can code this. And that is our quick intro to merge sort. So now let's look at coding merge sort. So I'm going to bring up this function here, merge sort, and we're just going to pass this an array. And as we discussed in the last video, the base case is when we reach an array that has a length of 1. So we're going to say if array.length equals 1, we're going to return the array, and that's going to be that array with a length of 1 that we're returning. So now that we have the base case out of the way, the other thing we said merge sort does is it breaks arrays in half. So now we're going to write the code to break arrays in half. So I'm going to create a variable here called mid, and we're going to set it equal to math.floor, and then we're going to pass it the array length divided by 2. So if you haven't seen math.floor before, all it does is makes this into a whole number. So for example, if the array.length was 3 and we divided it by 2, that would be 1.5. Math.floor is going to change that into a 1 because obviously the index always has to be a whole number. Then we're going to create 2 new arrays. One we're going to call left with the left side of the array, and one called right that contains the right side of the array. And this is all we need to do to break arrays in half. So let's say we have this array here. These 3 lines of code would do this to this array. If these were sorted, we could return merge of left and right, these 2 new arrays that we created. But the problem is they are not sorted. These need to be broken in half again. Well, merge sort is the function that we use to break arrays in half. So we take both of these arrays, left and right, and we run merge sort on each of them. And this is the part that is recursive. And that will break this in half on the left, and then do this on the right. Then we have reached our base case, and it starts returning these one-item arrays. Now merge can work with these. These two will get combined first, and the reason for that is they were the last to go onto the call stack. So that is going to get run first. That gets popped from the call stack, and then we run it on this side, and then it runs again, and these are combined. And that is all of our code for merge sort. So we'll look at this in a moment, except we will start with the array looking like this. So now let's flip over to DevTools. So here is that merge helper function that we had written previously. And then I'm going to scroll up. And this is our merge sort function here. And we're going to call it with that 4-item array that we had just seen. So let's zoom out here, and I will run this. And here is our sorted array, 1 through 4. And that is our function for merge sort. Now let's talk about the big O of merge sort. I'm going to bring up an array here. The first thing I want to talk about here is space complexity. Because with merge sort, you have this original array like this, but when you break this down into 2 arrays like this, you've actually created 2 new arrays, left and right. You still have the original array, and now you have these 2 arrays. So you've just doubled the size in memory that this is taking up. And as you break this down, you still have these 8 items in addition to the original array. So the space complexity is O of n. You originally had 8 items in an array, then you had to create 8 new items, and that is O of n. Now let's look at the time complexity. When you break these down like this, you have 1, 2, 3 steps to break this down. So we've seen this before. If you have 8 items and it takes you 3 steps, that is a log n operation. But when you put them back together, if you think back to our merge function, you're having to iterate through each array to put these back together. So like if you have this, you have to loop through both of these to put them back together as a sorted array. So breaking this apart is O of log n. Putting it back together is O of n. And that's where we get the O of n times log n. And it looks like this on the graph. I'm just going to gray out the 3 that are over to the right, because when it comes to sorting algorithms, O of n squared and O of n times log n are pretty much your 2 options. There are exceptions to this with sorting algorithms that sort only numbers, because there are some efficiencies with just numbers. But if you have an algorithm that is going to sort all different types of data, O of n times log n is as good as it gets. Now, it doesn't look like there's a huge difference between these, because on the axis on the left, it only goes up to 75 here. But if you start having it go to 1,000 or 1,000,000, there's a huge difference between these 2 lines, which makes this much better for most situations than bubble sort and insertion sort and selection sort, the original ones that we did that were O of n squared. And that is merge sort, big O. Okay, this is going to be our introduction to quick sort. So I'm going to bring up an array here like this, except I'm going to show it like this. And the way quick sort works is we're going to have a pivot point, and we're going to make that first item, that 4, the pivot point. And we're just going to compare every item in the array to that number. So we'll start at the 6. That one's greater. I'm going to color that gray because it's greater than. and the 1 is less than. So if we find an item that is less than, we're going to exchange it with the first item that is greater, like this. Then we move to the next one. That's greater. This one's less than. We exchange it with that first greater than item. And we do this again and exchange that. And then the 5 is greater than 4, so we'll color that one in gray. And we have one step left. We're going to swap that 4 with that last item that is less than, like this. And now the 4 is sorted. So I'll color it green because that's going to be where it is after we sort everything. And everything that's less than the 4 is on the left. Everything that's greater than the 4 is on the right. So now what we're going to do is run quicksort again on just this section of the array. And we're going to do it on the other side as well. So let's focus on the left side first. The 2 is going to be our pivot point now. We'll compare the 1 to the 2, it's less, and the 3 is greater than. And now we're going to exchange the 1 and the 2, and now the 2 is sorted. And then we'll run this recursively on these 2. And because there's only one item in each of these, we know that those are in the correct spot. And I'll mark those as sorted. On the other side, we're going to have the 6 be the pivot point. 7 is greater. 5 is less, so we'll exchange these 2. And then we'll exchange the 6 with the 5. So the 6 is sorted, and now the 5 and 7 are sorted as well. And that's our overview of the workings of quicksort. So now we're going to do our pivot intro. Pivot's going to be a helper function, much like the merge function was a helper function for merge sort. Pivot is going to be a helper function for quicksort. So I'm going to bring up an array here and do it like this. And what the pivot function is going to do is this. We're going to have our pivot item, and we're going to highlight that 4 there. It's going to sort all of these and do this swap like that. That's all it's going to do. So let's put this back like this and go through the steps that we need to go through to make that happen. So I'm going to go into a little bit more detail in this intro video than I normally do in an intro video because it's going to be difficult to explain without bringing in the variables. So we have our pivot point here. And then we're going to loop through this from the next item over. That's going to be I in our loop. We're going to have a variable called pivot that points to this item, and another one called swap that's going to start out being set to pivot, but this one will move. So we start out by looking at that first item that I is pointing to there. The 6, it is greater than, and we'll move I to the next item. Anytime you have something that is less than the pivot variable, we will move the swap up to here, and then we will use that to swap these 2 items. And then I will move forward, that one's greater than, and this one's less than. So we move swap up first, and then we swap these 2 values. Same thing here, swap moves up, we swap these 2 values. Then we move I to the last item, it's greater than, and we are now done with that loop, so I will remove that arrow. And the last thing we need to do is swap these 2 items. And we're done with the pivot variable. And normally, when we're working with an array, at the end of the method or the function or whatever we're doing, we return the array. But that is not what we're going to do here. We need to return that swap variable. Now, this is everything the pivot function is going to do, but I'm going to show you why we need to have that swap variable. Because when we run quicksort on this side, we are going to be running this on the index of 0 through swap minus 1. When we run it on this side, we're going to run it on swap plus 1 to the end of the array. So that's why we have to know what that index is. And that is our overview of pivot. Now we're going to write our pivot code. So we're going to use this same array like this, and I'm going to shrink it down so we have room for our code. Now, one of the things that we're having to do in a couple of different places in pivot is swap two items. So you can do that with 3 lines of code like this, but since we're going to use this twice, I am going to make it its own function. We're going to pass it an array and the first index and the second index of the items that we're going to swap, and this is going to take care of that. So this is going to make our pivot code a little bit cleaner. So let's start the pivot code itself. Now we have 3 arguments here. The only one that you have to pass it is the array, because these 2 are going to default to what they're going to need to be when you pass it the array anyway. The index of the first item in the array is going to be 0, and the index of the last item in the array is going to be the length -1. So you don't have to worry about these when you are passing the array to the pivot function. But the reason we have this is we saw that we're going to run quicksort after the first time through on a subsection of the array, and we have to know the first and last index of that section of the array that we are working on then, and that's why we have to have this here. So I'm going to bring in our first variable pivot. That's going to be this. So the variable is pivot index to emphasize that this is an index, but on the arrow, I'm just putting pivot to make that easier. Then we're going to start out with the swap index being equal to the pivot index, like this. Then we'll have our for loop. And here is I from the for loop. It's going to be the pivot index plus 1. And we're going to run this loop until we get to the end index. So then we start doing comparisons. If the value at the index of I is less than the value at the pivot index, we're going to do something. So in this case, that's not true. I'm just going to color this in gray and move the I over. In this case, it is less than. And when that is the case, we're going to do 2 things inside of this if statement. We're going to move swap over like this, and then we're going to use that swap function like this, where we pass it the array, the swap index, and I, and it will swap those 2 items. And then we're going to keep going through this for loop until the array is going to look like this. And the next thing is we're going to call that swap function and switch these 2 items. And now there's one thing left to do, and that is to return that swap index, which means this function, in addition to rearranging all of the numbers to be like we have at the bottom of the screen, it is also going to return the value of 3. So that is our code for pivot, and this is going to be the result that it returns, but we're going to start like this. Now let's go over and look at all of this in DevTools. So there is our swap function, and our pivot function is here. And we're going to run pivot with myArray, which is the array that we had just looked at. And I'm going to zoom out here and run this. And it's going to return the number 3. That's that index. But let's also look at myArray. And there is the array with the 4 in the middle, and everything on the left is less than 4, and everything on the right is greater than 4. And that is our function for pivot. Okay, so now let's code quicksort. I'm going to bring up our array like this. So right out of the gate, when we run pivot, we're going to have our pivot item like this, and it's going to sort it like this, and it's going to return this index. What we have to do with quicksort is to continue doing that on this side and this side, and keep breaking this down until we have sorted everything. So I'm going to put our array back the way it was and then shrink it down into the corner like this. So I'm going to bring the function in like this. Just like with pivot, you only have to pass it an array to begin with. It is only when we start calling this recursively that you have to worry about that left and right up there. So in our first line of code that I'm going to bring in here, we're going to store that index that pivot returns, like this. And we are passing pivot these three pieces of information, and it's doing two things. It is rearranging our array like that, but it's also returning that index, and we are storing it in pivot index. And with that piece of information, we can call quicksort recursively like this. So if you look at our diagram at the bottom, it is these three items that it's being called on in this situation when we have it call it again, because left is 0 and pivot index -1 is that last index in that bracket. And then we also need to call this on the items on the right, and then we would do that like this. And I'll bring up that bracket to represent that. So let's bring this up and look at this a little bit further. We're going to start on the left, and we're going to have our pivot, and that's going to be less than, and that's going to be greater than, and then we switch these two. And then we're going to call it again. But in this situation, you don't want to call quicksort again because you already know that these are in the right spot. That's going to be our base case. And let's do this over here as well. That's going to be our pivot. That's greater than, and that's less than. We switch these, and then we switch these. And now we know that these two are in the right spot, so we don't want to call quicksort on these either. Also, that is our base case. So let's shrink this down. The thing that we need to do here is have some kind of if statement. So to make this work, we're going to need this if statement where we say left has to be less than right. So in what we just saw here, what was left and right were the same item because there was only one item left. And when that happens, we're not going to continue having quicksort call itself. And now once we get to that point, we can just return the array. So we'll look at this code in a moment, except we'll start with an array that looks like this. Okay, so let's flip over to DevTools. So there is our swap function that we wrote in the last section and our pivot helper function. And I'm going to scroll up here. And there is quicksort. And we'll run it down here with that array. And I'll zoom out and run this. And there is our sorted array. And that is quicksort. So now let's look at the big O of quicksort. So I'm going to bring up an array like this. And when we run pivot, it brings us to a point like this. So the first thing I want to point out about this is we didn't have to create any new items here. We just move things around within the same array. So this is different than merge sort that creates new items and therefore doubles the amount of space that it takes up in memory. With this, you are working only within the original array without duplicating any data. So from a space complexity perspective, this is O of 1. And this is an advantage of quicksort over something like merge sort. From a time complexity perspective, in order to move all of these items around like we just did here, that was O of n because we had a for loop that went from the beginning of the array all the way through to the end. And if you look at how many times we had to do this, this was 1, then we did it 2, 3. That is going to be log n. So what we just did here is O of n times log n. And we'll look at this on the graph like this. It's much better than O of n squared. But the problem with this is what I just showed you is actually the best case for quicksort. The worst case is not O of n times log n. So now let's look at the worst case. The worst case is if you have already sorted data. So if we take that first item there, we make that our pivot point. We're going to compare that to all the other items in the array, and that is not going to move. So I'll color that in green. But what we normally do with quicksort is we run quicksort on all the items on the left of it, all the ones that are less than, and then run it also on everything on the right. It is that splitting of the array that makes it efficient. But in this case, there are no items on the left. There are only items on the right. So there is no splitting of the array. And the same is true when we look at 2. We compare it with everything else, and there are only items on the right. And for 3 as well, and so on, all the way to the end. So in this circumstance, this is actually O of n squared. That is our worst possible scenario, and that is what big O measures. So our best case or average case would be O of n times log n, but our worst case is O of n squared. So if you have sorted or almost sorted data, this is not a good sorting algorithm. But if you have random data, this is an excellent sorting algorithm. It's very fast, and the space complexity is O of 1, which is better than merge sort. If your data is sorted, it would be better to use something like insertion sort, even though that's O of n squared is its worst case. If you're using sorted or almost sorted data, it is very efficient. It actually runs at O of n. Okay, and that is our overview of quicksort, big O. So welcome to tree traversal. We're going to look at a couple of different ways of doing that. And first, we have to talk about what tree traversal is. So traversing, if you had something simpler like a linked list, would just be going through each item from beginning to end, and you might take all of these values and add them to an array, and then return that array. But if you have something like a tree, it's more complex. There's different ways that we can approach this. So one of the common ways of doing this is we just start at the top node, then we go to the next line and we do the 21 and the 76, and then we go to the next line and we go across here. This is what's called breadth first search. Another approach that we could have is instead of starting at the top, we go all the way to the bottom. And in this case, we're going to go all the way to the bottom to the left and do that 18 node first. And we've gone as far left as we can, so we'll go up, and then we will go down to the right. And we've done everything on that side of the tree, and we come back up to the 47. And because we're doing left first on that other subtree that we haven't visited, the deepest node that we can get to, that's to the left, is the 52 node. We'll do that one next, and then come up, and then finally come down and do the 82 node. This is what is called depth first search. And we're actually going to write 3 different depth first search functions. Each one is going to return these in a little bit different order. But breadth first search and depth first search are going to be the 2 broad categories of tree traversal. So in this video, we'll walk through the steps of doing breadth first search, and then in the next video, we will code it. So I'll bring up our tree, and in breadth first search, we're going to start at the top, and then we're going to fill these in across each row like this, and push all of these into an array and return that array with those items returned in that order. So I'm just going to move this over here, and I'm going to bring in a couple of arrays, one that we're going to call Q and one that we're going to call results. And the results array is going to be the one that we return at the end of this. So in order to get these in the right order, we're going to need to use both of these. And we're going to push that top node first into the queue. And I want to emphasize that this is the entire node. This is not just the value from the node. I'm not going to store it like that. I'm going to store it like this. I'm going to keep it blue so we emphasize that it is the node, since that's the color of the nodes. Then we're going to shift that item out of the queue, and we're going to take the value and push it to the results array. When we put this in the results array, we're not putting the entire node in there, we're just putting the value. But because we put the entire node into the queue, we have the value, and we have right, and we have left. So we can say for the 47 node, what is to the left? Well, that's going to be the 21, and we can add that to the queue. To the right is a 76, and we add that to the queue. So we're going to have a loop that removes items from this queue until this queue is empty. When the queue is empty, we will have visited every node in the tree. So the next step here is we are going to remove that 21 node from the queue. We're going to shift that off, and we're going to do three things. We are going to take the value and put it in the results array, and then we're going to look to the left of the 21, which is the 18. We will push that into the array. We will look to the right, that's the 27. We will push that into the array. Once we're done going left and right, the next step is we are going to shift off that 76. The value goes into the results array, and then we're going to go to the left of the 76, which is the 52, push that onto the array, and go to the right. That's the 82. So now when we remove the next item from the queue, we shift off that 18. The value goes there, but left and right is null. There isn't anything below that 18 node. So then we go to the 27. There's nothing to the left or the right. And the same thing for the 52 and the 82. Now the queue is empty. We can remove the queue array from the picture here. And what we're going to return is that results array. So let's look at the order that these numbers came up. The first one is the 47. The next two are the 21 and the 76. And you can see that this tree exactly matches the other tree. And that is breadth first search. Now let's code our breadth first search method. So I'm going to bring up our tree like this, and I'm going to put this down in the corner there, and we'll start writing our method. So we'll say breadth first search, and we will need a variable for whatever the current node is that we're popping off of that array that we talked about in the last video. We are going to set that equal to the root to begin with. And we're going to need our queue array like that, and our results array like that. So one of the things we have to do before we even get into that loop where we're looping through and putting things in the queue is we need to push the current node, which is the root, into the queue. And remember, we're pushing the entire node with the value and left and right into that queue. I'm just going to represent it like this as a blue number so we can remember that that's actually the entire node. Now we'll start our while loop, and we'll say while queue.length. In other words, while the queue has length, or you could say while the queue has a length that is greater than 0, because once this is 0, that'll equate to false. And I'm just going to focus in on this while loop like this as we build it out. We'll say current node equals queue.shift. So when we shift this out of the queue like this, I'm going to make this green to match the 47 in the diagram there. That makes that the current node. And we're going to do a couple of things. First, we're going to take the value from that current node, and we're going to push it into the results array. And then we're going to go left and we're going to go right. But we have to say, if there is something to the left, then we will push that node that is on the left, current node.left, into the queue. And then we'll say, if there is something on the right, we'll do the same thing there where we say, push the current node that is on the right, which in this case is the 76. And that's everything for our while loop. So let's run through this while loop a few more times here. So let's look at these two steps here. We will shift off the 21 And then we're going to take that value and move it into there. From this point forward, I'll just take these two lines and combine these into one step and just move that value from Q straight down to results. Then we'll say if there is something on the left, and there is something to the left of the 21, that's the 18, we push that into the Q. If there's something to the right, and there is, we'll push that into the Q. And the next one we remove from the Q is going to be the 76. I'm just going to put that value straight into results. That is those first two lines there in the while loop. Is there something to the left of the 76? There is. That's the 52. And to the right, we have the 82. And then it gets really quick from here, because when we do the 18 and remove that from the Q, push that onto the results array, there is nothing on the left, there is nothing on the right. So then we do the same thing for the 27, same thing there, nothing on the left or the right, and then the 52, and then the 82. So now that Q is empty, and we stop running the while loop, because it only runs as long as the Q has length. So we'll remove that, and the only step that's left is to return that results array. So let's bring the rest of our code back here. This is the entire breadth first search method, and we'll look at this code in a second in DevTools. And when we do, we will build this binary search tree, and we will expect to see this array returned. So let's flip over to DevTools. So this breadth first search method is going to be part of the binary search tree class. So let's scroll down to the breadth first search method. So there is that code there. This is the tree that we will build. I'm going to scroll up a little bit further here. So this array here that I have commented out is the order that we will expect to see from the breadth first search. I just want to point out here that the order of this array and the order here is exactly the same. So I'm going to zoom out here and run this and zoom in down here. And our binary search tree has 47 at the root. It has 21 and 76 at the next level, and I won't open it up further than here. So I'm going to clear this. So I'm going to run mytree.bfs and press enter. And that is our array, which exactly matches this array. So that is our method for breadth first search. Now we're going to look at our first depth first search algorithm. This one is going to be pre-order. Later, we're also going to look at post-order and in-order, but this one will be pre-order. So let's walk through what pre-order looks like. I'm going to bring up a tree here. And remember, we're just going to take these and write them to an array. It's just a matter of what order we do it in. So pre-order is going to start at the top and write that to the array. And then it's going to go to the left. It's always going to go to the left first if it can. It's going to write that 21 to the array, and then the 18. And once we've done everything we can to the left, we're going to come back up to the 21, and we're going to go to the right. So now 47, that top node, has done everything it can to the left. Now it's going to start going to the right. It's going to go to that 76 node. And the 76 node is going to go to the left, because we're going to go left first. Now that we have everything on the left that the 76 can do, we're going to come back up to the 76 and go to the right and add the 82 to the array. And that is pre-order for depth first search. So now let's code out our depth first search pre-order method. So I'm going to start out with a tree down here, and this time I'm going to have a call stack. Since we are using recursion, it's going to make this a lot easier to understand if we can track how this works with the call stack. So we'll start building this out. DFS pre-order is what we'll call this. And the first thing is we have to have a results array. And we'll just bring this up down here. So next, I'm going to bring in our entire recursive function and then just walk through it. So our function is going to be called traverse, and we're going to pass it a node, and we're going to kick this off by passing it the root node. And when we pass it the root node, the first thing we're going to do is we're going to say results.push. So into that results array, we are going to push current node.value. So the current node is going to be the root to begin with. Next, we have this if statement, and this is where we have the recursion. And it says if there is a node on the left of the current node, to begin with, that's going to be the root. If there's a node on the left, then call traverse on that node that is on the left. And there is one on the left, that's that 21 node. And then we're going to also say, if there is a node on the right, we will call traverse on that node on the right. So to kick this off, we actually have to call the function like this, and we will call it with the root, which pushes this function onto the call stack. Now remember, this function is going to be called traverse if you actually go look at the call stack in Chrome DevTools, but I'll say that this is the instance of the function traverse that has been called on the node 47. And that's how we'll keep track of these on the call stack. So that's going to run our function, and the first line of that function is going to be results.push the value of that current node. And the value is 47. We push that into the array. Then we come down to this if statement. If there's a node on the left, and there is that 21 node, we will call traverse on that node on the left, and that goes onto the call stack. So the first line that we're going to run in that instance of the traverse function is going to be results.push, and we push the 21 into the results array. So every time we push the value of a node into the array, I'm going to take that node and I'm going to color it orange. So the instance of traverse that is at the top of the call stack right now is still 21, and we go to the next line of code for the 21. And that is this if statement. Is there something to the left of the 21? And that's that 18. And we push that onto the call stack. So for the 18, the first thing we do is we take that value and we push it into that array. And then we say, is there something on the left of the 18? There's not. Is there something on the right? Now we're done with the function for 18, and we can pop that from the call stack. Now 21 is once again the top item on that call stack. The 21 has already gone left when it went to the 18. Now it's going to go right, which is going to add 27 to the call stack. And it is going to push its value into the array like this. And it doesn't have anything on the left or the right, so now we can pop 27 from the call stack. 21 is now the top item. The 21 has already gone left and it has already gone right, so it is done. So we can pop this. Now the 47 is the top item on the call stack. It still needs to go right, which is going to call traverse on the 76 node. The 76 is going to push its value into the array like that, and then it's going to look left. There is an item on the left, that's that 52. We push that onto the call stack. It's going to push its value into the array. It doesn't have anything on the left or the right of the 52, so now that one's done. The 76 is now the top of the call stack. It still needs to go right, so it will call the traverse function on that 82 node. That's on the top of the call stack now. We will push that into the array. The 82 doesn't have anything on the left or the right, so we can pop that off. The 76, we've already gone left, we've already gone right, we can pop that off. And the 47 has already gone left and right, and now that gets popped off. When we pop off that 47, that is the original time that we called this function. We are finally done with this function call. The only thing left to do at this point is to return that results array. And that is our code for pre-order. We'll look at this in a moment. And we're going to build this tree in DevTools. We will run this method, and we would expect to get this array back. So let's flip over to DevTools. There is our depth first search pre-order method. I'm going to scroll up here. There's our tree that we're going to build, and we would expect to get back this array. So I'm going to zoom out here, and I'm going to run this, and this is going to give us our binary search tree here. I'm not going to open it up, but I will run mytree.depthFirstSearch preorder, press enter, and we get this array, which does match this array up here. And that is our method for depth first search preorder. Now let's walk through the steps of depth first search post order. I'm going to bring up our tree here, and we're going to start at the root, but we're not going to write that number to the array. We're going to visit that one. We will come back to it. And we're going to go left to the 21, visit that node, go left to the 18, visit that node. Now the 18 is going to try to go left, and there's not an item there. Then it's going to try to go right, and there's not an item there. And finally, the 18 will write its value to the array. That'll be the first item in the array. Then we come back up to the 21. The 21 has gone left when it went to the 18. Now it's going to go right to the 27. The 27 is going to try to go left. It's going to try to go right. There are no items there, so it will write its value to the array. Now we come back up to the 21. It has gone left when it went to the 18. It went right to the 27, and now it can write its value to the array. Now we come back up to the 47. It's gone left, but it hasn't gone right yet. So we're going to go to the 76, and we always go left first, and it's going to go down to the 52. It's going to try to go left and right. It doesn't have any items there. So it will write its value to the array. We come back up to the 76. We will come down to the 82. It will try to go left and write its value. Now when we come back up to the 76, it has already gone left and right, so it can write its value. And now we come back up to the 47. It has gone left and it can write its value to the array. So when you compare post order, which is what this is, to pre-order, the one that we did previously, in pre-order, we wrote the 47 to the array first. In post order, we write the 47 to the array last. Okay, so that is our quick overview of depth first search post order. So now we're going to write the code for depth first search post order. We'll bring up our tree like this and our call stack and start writing our method DFS post order. The first thing we're going to do here is have our results array, just like we had in pre-order, and we'll bring that up like that. And I'm going to bring in the function that we had in pre-order. This is the one for pre-order. To change this to post order, all we're going to do is this. We're just going to rearrange the order that these get called. And just like we did with pre-order, we're going to call the function starting with the root. And we'll walk through this using that call stack. So at the root, we're going to put 47 on there. The first thing we're going to do is say, is there a node on the left? And there is. And we're going to go to the 21 node and push that onto the stack. And then the 21 is going to say, is there something on the left? And there is the 18, and it's going to go left and add that onto the stack. So the 18 is going to look left, and there isn't anything there, and then it's going to look right, and then it's going to push its value into the array. And the process of pushing that into the array is the last line of the function, which means we can pop that 18 from the call stack. So then 21 is the top of the call stack. It has already gone left, so now it's going to go right to the 27. That adds that to the call stack. The 27 is going to look to the left. It's going to look to the right. There are no nodes there, so it's going to push its value into the array. And we can pop that from the stack. The 21 is at the top of the stack again. It's already gone left, it's gone right, and now it can push its value into the array. And now we pop that from the stack. Now the 47 is the top of the call stack. It's gone left, now it needs to go right. And that's going to be the 76 node. We'll put that on the call stack. The 76 is going to look left, and there is an item on the left, and that's the 52 that gets pushed onto the call stack. The 52 is going to look left, it's going to look right, there are no items there, and it's going to push its value into the results array. Now we can pop the 52 from the call stack. 76 is at the top of the call stack. Now, the 76 has already gone left, now it can go right, which pushes the 82 onto the call stack. The 82 is going to look left and right. There's nothing there. It's going to push its value into the results array. We pop that from the stack. And now 76 is at the top of the call stack. It's already gone left. It's already gone right. And now it can push its value into the array. We pop that from the call stack. 47 is now the top of the call stack. It's already gone left and right. And now it can push its value into the array like that. And the 47 will pop that from the call stack. It was the node that we had called with the original function call here, which means we are done running those functions. The only thing left to do is to return the results array. So that is our code there. And we'll build our same tree that we've been building all along. And we will expect to see this array when we run the depth first search post order method. So let's flip over to DevTools. There is our depth first search post order method. Let's scroll up here. This is creating that same tree, and this is the array that we would expect that method to return. So let's zoom out here, and I'll come up here and run this. And this is our tree here. I'm not going to open that up this time. I'm just going to clear this, and I'll just do the up arrow here. And DFS post order returns this array, which does match this array. And that is our method for depth first search post order. So now we're going to do depth first search in order. So we'll bring up our tree here, and what we're going to do is we're going to start at the top as always, and we are going to visit that first node, and we're going to always go to the left first. So we're going to do the 21, it's going to go to the left, and we go to the 18. 18 is going to try to go to the left, there's nothing there, and the next step is that we're going to write the value 18 to our array. So I'm going to color that orange. Then the 18 is going to try to go to the right. And of course, there's nothing there. And we come back up to the 21. It has already gone left. Now we're going to write that value and then go right. It's going to go left, write the value, try to go right, and then we come all the way back up to the 47. It's gone left. Now it can write its value, and it goes right. And the first thing we always try to do, if we can, is go left. So we go down to the 52, and then it tries to go left. We write the value, tries to go right. We come back up to the 76 and down to the 82. It goes left, writes the value, tries to go right, and we're done. So I'm going to reset this all back, and let's walk through the order that these were written to the array. We started with the 18. That is the lowest number in that tree. And then it was 21, the second lowest. And it goes from lowest to highest. And that's why this is called depth first search in order. Okay, so now let's code depth first search in order. Just like we did before, I'm going to bring up our tree and our call stack and we'll start coding this DFS in order. And we're going to have a results array like that. Now I'm going to bring in the function that we use for pre-order. This is what it looked like for post order. This is what it looks like for in order. So it's all the same code, just written in a different order. Then I'll call this function with the root like this, which puts that on the call stack. First thing we do is go left, which means we're going to visit that 21 node and it gets pushed onto the stack. And then the 21 is going to go left and 18 gets pushed onto the call stack. It's going to try to go left. There's nothing to the left of the 18. So we move to this line here and we add that 18 to the array. The 18 tries to go right. There's nothing there. So we pop it from the stack. So now the 21 is at the top of the stack. We already went left. Now we're going to do the next line, which is to push that value into the array. And then we're going to go right. So that's going to push that 27 onto the stack. It's going to try to go left. We're going to write that value like this into the array. And it will try to go right. Now that 27 is done, we can pop that from the stack. The 21 is at the top of the call stack now. It's already gone left, it's written its value, it's gone right, and now we can pop that from the stack. The 47 is now the top item on the call stack. It has already gone left, now we can push its value into the array like that. And then it's going to go right. So we're going to visit that 76 node. It gets pushed onto the stack like that. It's going to go left first, which is the 52. That gets pushed onto the stack. So now 52 is going to try to go left. There's nothing there. We'll push the value of the 52 into the array and then try to go right. And now that one is done. We can remove that from the stack. 76 has already gone left. Now we can push the value 76 into the array like this, and then it will go right to the 82. That gets pushed onto the stack. The 82 is going to try to go left. We don't have anything to the left. We push its value into the array like that, and then we go right. There's nothing there, so we can pop that from the stack. The 76 has already gone left and written its value and gone right, so we can pop that. The same is true for the 47, and we pop that from the stack, and the 47 was the original function call, which was the root. The only thing left to do now is to return that results array. So there is our final code, and when we go over to Chrome DevTools, we're going to build this same tree that we've been using all along, and we will expect to see this array here. So let's flip over to DevTools. So there is our DFS in order method there. And I'll scroll up here. And this is going to create the same tree we've been using for the last few videos. And this is the array we would expect this to return. So I'll zoom out here and I'll come over here and run this. And that creates our tree. And now I'm going to run DFS in order. Okay, that gives us our array of those items in order, and it matches this array up here. And that is our method for depth first search in order.